Hello. Hello. Is it working now? Okay, finally. Let me send an email. Hello. Hello, madam. You can join now. So there was some issue.
Hello. Finally, I'm here. Can you hear me?
Hello, Professor Young.
Yes, hi. How are you?
Fine. Sorry, there was some issue with this link.
Yeah, no problem. Should I share my screen?
Yeah, you are very much there, Professor Yang. Welcome to this 5th International.
Can you see my screen?
Yes, we can. We can.
Okay.
So we are very happy to really host this session on synthetic materials. Pranab, would you like to say something first?
Hello, everyone. Yes. Hello, everyone. Welcome to this symposium on spintronics. There is some echo I am receiving. I am hearing my own voice. Let me see if some issue here. Is it fine from your end?
Yeah. We can hear you, Pranab, very well.
Okay. So let me introduce our chair of the session. Professor Ratnamala Chatterjee is a HOD of the Department of Physics.
Yeah. So shall I? Hello?
Yeah, madam, please take over.
Yeah, okay. So we are happy to host this session on topological spintronics. And we are very happy to welcome Professor Honshu Yang. He is a Global Foundries Chair Professor in the Department of Electrical and Computer Engineering at NUS. Professor Yang has completed his PhD somewhere around 2006 from Stanford University. He is very well known in this area of magnetic materials and devices for spintronics application. He has authored several, many, 200 journal articles, many invited speeches, Professor Yang, you have given. And you are the recipient of basically IEEE Magnetic Society Distinguished Lectures in 2019. So many of us are actually aware of your work, and we are eagerly looking forward to hearing from you today. So welcome, Professor Yang. Thank you.
Yeah, thank you very much, Chairman, and also the organizers of this conference. So I think we are a bit delayed, so let me just quickly start my talk. So today I'm going to mostly talk about electronics using topological materials. Okay, so if you look at the last few years, progress in terms of spin memory, ever since its debut in 2017 of this spin transfer talk technology, last few years, many companies commercialize this technology into the market. For example, 2018, IBM started shipping flash core module buffered with the STT MRAM. And last year, Everspin with the Global Foundry in Singapore, they show a demo chip of 1 gigabit MRAM. And last year, Samsung started to ship this 28 nanometer embedded MRAM application. And this technology is now, in this consumer electronics, such as, this e-watch. So we are really living in a world of magnetic memory, in the commercial application. And now we have to think about what will be the next generation technology in terms of magnetic memory. So nowadays, many people are excited about this opportunity using spin-orbit talk. The basic principle is once you flow current along the in-plane direction in a spin generation layer, we can generate the spin accumulation at this interface due to either spin Hall or Lashva, or probably together. The bottom line is there is enough strong spin accumulation at this interface, and due to those, we can exchange angular momentum to the above magnetic layer, and eventually we can even switch this layer. So that gives huge excitement into the community, which was initially shown by this paper by Pietro Gambardella group with Mihai Mylon, and then subsequently also Cornell showed in paper in 2012, and they attributed mostly this due to the spin Hall effect. So once I summarize this field, I can probably divide into three active layers. First one is generation of spin current, then absorption, then finally we have a capping layer. So in terms of the generation layer, traditionally people use mostly heavy metal base because we know spin-orbit coupling in heavy metal is large. Nowadays, people start to notice, interfacial spin-orbit coupling is getting more important. Two-dimensional electron gas can be one of the candidates also to generate strong spin current. But today, I'm going to mostly focus on topology materials, such as topological insulator and wire semimetals. So the goal of this field is basically to achieve low switching current and low switching power. In order to achieve those, basically there is a race to search for large effective spin Hall angle materials or large effective spin orbital field. So let me start with this three-dimensional topological insulator. One of the prototypical material is bismuth selenide. If you look at the band structure of this material, it has spin-dependent feature. So for example, if you look at the right branch, which are indicated with the blue color, so that corresponds to this, the electrons are moving in this direction, and supported spin is only 90 degree in a right angle with respect to this electron momentum direction. Now, once we inject electrons into opposite direction, you can see supported spin is exactly opposite to the previous case. So depending on the electron momentum direction, the supported spin is locked. So we call this is a spin momentum locking properties. And naively, we can think about very large effective spin or angle. So that is the motivation why people start to utilize these topological materials for some spintronic application. So first, we want to understand what is the spin texture in this material, current induced property. We noticed this interesting paper in 2015. They reported so-called UMR, unidirectional magnetoresistance. So in a case of bilayer cobalt platinum, and we saturate the cobalt layer into one particular direction, and depending on the current injection in platinum, we know we can, populate the spin accumulation from one direction to the other direction. So then we measure the longitudinal junction resistance. In typical, junction resistance, when we talk about, which is the current independent, linear junction resistance, do not change its value depending on the current flow direction. It should be same in these two cases. However, because of the spin dependent, this spin accumulation, people found the left case has a high resistance, but if you look at the right case, it has a low resistance. So how do we detect those? If we do a sinusoidal current injection into the junction and do a very simple, derivation, then we will find, if you look at this second harmonic component, the coefficient has, a component which scale linearly with the current. So this is called current-dependent nonlinear resistance. And using so-called this second harmonic measurement, we can easily find the coefficient. So basically, once we do this second harmonic measurement, we can find our current induced spin texture detection. When we apply the current into one direction, whether it's one particular direction or opposite direction. We try to apply similar principle to our topological material, and we found in case of a topological insulator, we do not need extra magnetic layer, not like the previous case. In this case, they had to use a cobalt layer. But in this bismuth selenide case, only single layer material, and then we apply magnetic field, for example, in plane direction and rotate. Once we apply charge current into one particular direction, for example, if you look at this case, we see the accumulated spin or supported spin is a right angle to this, red color. Then once we apply the magnetic field in parallel with this spin direction, we found in that case a high resistance, which corresponds to the 90-degree case. Now, once we apply the magnetic field opposite, which is a 270, degree, then we found that it has a minimum resistance because the spin accumulation direction and magnetic field direction is exactly opposite. So that is similar to this case. So now we replace this magnetization with magnetic field in a single layered material. So once we rotate, the magnetic field along the in-plane direction, we have basically this nice sinusoidal response that really mimic this spin texture of in-plane behavior. So basically, we can find in-plane spin texture by measuring this second harmonic resistance in this topological insulator material. We can now repeat this along the outer plane direction. For example, we start from the magnetic field along the Z direction, then sweep the magnetic field along this in GY plane, and we found the maximum it happened about 120 degree, So that means when we apply the field about 30 degree from below to the horizontal plane, we have a spin, accumulation direction. So that is corresponding to this K prime point, according to the topological, textures, the warping is supposed to have about 30 degree, below this horizontal plane. So basically, once we repeat this measurement along the outer plane direction, then we can find out also what is the outer plane spin texture in this material. This behavior is proportional to the intensity of current. That's what I showed earlier here. The current dependent resistance should be proportional to the injected current strength. But not only those, we also find this behavior is linearly proportional to the strength of magnetic field. So we name this as a BMR, bilinear magnetoelectric resistance. And this is quite different from the conventional UMR, in which people had to use a magnetic layer. And once you saturate the magnetic moment of the magnetic layer, in this case cobalt, basically is a second harmonic resistance also saturate. But however, in our case, it scales linearly. So that's the major difference. So we can now pattern the device into different crystalline direction and then measure basically XY magnetic field sweep or GY magnetic field sweep. Then we can extract what is the canting angle along the outer plane direction. Then we plot those, and you can see we can find a very nice threefold symmetry, which is supposed to happen in a topological insulator warped surface. So this is like a mini electrical Alpes measurement because we can find out the spin texture by just applying magnetic field and measure 2 omega signal in three-dimensional cases. One of the limitations of this technique is we basically ensemble average all the spin information in the channel. So once we want to know what is the specific spin texture in a particular point in the channel, we need to use some kind of imaging technique, which was initially shown by Santa Barbara group. So they use magneto-optical Faraday rotation at gallium arsenide at low temperature. So once we inject an unpolarized charge carrier, depending on spin scattering, we will have a downspin and upspin separated, left edge and at the right edge. And on the right side, you can see the beautiful data, red one representing downspins and blue color representing upspins. So we can clearly see this sort of, the location resolved spin accumulation. This technique is relatively easy to repeat in a semiconductor, but it was found very difficult for metal because a background charge carrier in a metal is huge. So even though you populate extra spins, it's not easy to appreciate, to measure those. So we try to develop a new technique called scanning photovoltaic microscope. In this case, we first apply DC current in the channel, then we can separate spin up and down in opposite edges. Then we use a circular polarized light, normal incident to the sample, and depending on the interaction of a spin, basically the magnetic circular dichroism will work, the amount of absorption will change, then we just measure the longitudinal voltage, and we subtract two cases, right hand and left hand circular polarized light. And then we have a chopper for the laser and measure this longitudinal voltage using the lock-in amplifier. Then piezo sample stage will just move around, then we can map the whole two-dimensional texture. So let's say, we shine the laser exactly in the middle of the channel. Then what will happen? The down spins and up spin population should be even in the middle. So once you subtract the voltage, it will be 0. Now we move our laser to one of the edge. Then we know there is a particular, spin population, either up or down. Then we just look at the polarity of this photovoltage. They could be positive or negative, depending on what is the local, spin population. So just look at the polarity of this photovoltage. We can find out, spin population information at that particular point. So one of the limitations of this technique is the light, the circular polarized light will be only coupled with up and down spins, outer plane spins. So what we are detecting is only outer plane information, not along the in plane. So we first apply to copper, which is known as a negligible spin-orbit coupling materials. No matter which current we inject, there is no clear signal as expected. So then we apply platinum. As you can see, once we at 0 current, nothing happened because there is no charge injection. As we increase our current to positive or negative, you can see and positive current, bluish and reddish color separated in opposite edges, indicating, we separate the up and down spins. Once we flip the charge current direction, then we also change spin accumulation direction. Then we apply to bismuth selenide at 0 charge current, nothing happens. But 1 milliamps, we can see blue and red separation with the opposite charge current, now red and blue. So which indicate this is really current induced phenomena. And this technique can work both metal and semiconductor. And eventually we can extract the spin or angle and spin lifetime, without a ferromagnet. So this is again one layer, measurement, without complication of spin mixing conductance, spin memory loss, and all those. As I mentioned, it should be much easier in a metal, it should be much easier in a semiconductor compared to metal because the background charge carrier is less. So as you can see, in order to see similar intensity of spin accumulation in a metal platinum, we need about 6 times more current compared to this semiconductor case. This is a quite controversial area. Using this magneto-optical curve effect measurement, two group inferred they were able to measure spin accumulation, but the other two group concluded it's not possible to measure spin accumulation using MOC. So in our lab also we try to image spin accumulation using MOC, and if you look at the first law, we found no clear signal regardless of the current injection amount. But using our photocurrent mapping technique, we were able to see clear spin accumulation, which really flip depending on charge current direction. So somehow we found, in our lab at least, photocurrent method is much better than conventional MOC-based imaging measurement. So once we know the spin texture, then we want to apply this for some memory switching. And one of the first steps to measure the efficiency is using spin torque ferromagnetic resonance. So we inject RF current in this bilayer. So we deposit the nickel ion on top. Then once we measure rectified voltage, and we can divide into symmetric and anti-symmetric component, and using the procedure of the fitting, we can extract the effective spin or angle. So we apply this to bismuth-selenide copper ion boron bilayer case, and then study as a function of temperature, and we found below 50 Kelvin effective spin or angle increase quite substantially, like from 0.1 up to like a 0.42. So this, very steep increasement below 50 Kelvin has some correlation with the resistivity of this material. So if you look at this resistivity measurement, you can see below 50 Kelvin, there is so-called plateau. And this plateau of topological insulator is an indication of more dominant surface transport compared to bulk at room temperature. So we can naively think about the enhancement of at low temperature of effective spin or angle is probably due to more surface dominant transport at the low temperature. Well, the other way to look at whether the bulk or surface dominant is changing sample thickness. So we started from 20 QL, quintuple layer. One QL is about 1 nanometer. So this is about 20 nanometer. And we found effective spin or angle is about 0.25 to 0.3. But as we go below 10 quintuple layer, we found effective spin or angle increase also very quickly. And then below 8 quintuple layer, we can see effective spin or angle can even reach about 1.0. This behavior is very different from conventional heavy metal. If you look at this platinum case, typically as you increase the platinum thickness, it saturates about several nanometer, then make this saturation behavior. So this is exactly opposite in the topological material. The region being at very thick films, basically there is huge bulk transport. So effective spin or angle is not very high because the spin momentum locking only happen at this surface state. But as we decrease the film thickness and more current start to utilize surface state, so effective spin or angle increase. So we can deduce, the thickness dependence data indicate surface dominant torque in these materials. So once we know, a strong torque, we choose about 8 quintuple layer, which is about 8 nanometer, because we need reasonably good spin torque efficiency. But at the same time, we always need to think about the device junction resistivity as energy consumption of this particular device. If we use a very thin layer, maybe efficiency is higher, spin torque efficiency. However, the total junction resistivity will be very large. then the total power consumption will be also very high. So we choose 8 nanometer and then deposit nickel ion on top and pattern into small different squares of nickel ion, so we can have various coercivity and anisotropy. Then we use microscopy to measure domain-wide basically change. So we inject charge current from left electrode. Initially, all the black color indicate nickel ions are saturated in this particular direction. As we increase charge current density, eventually we can switch all nickel ion into opposite direction. And from this configuration, by applying the charge current from the right electrode, we can go back to all the black domain state, indicating we can go back to the first state. This measurement, done at room temperature, and you can see the required charge current density is about 6 times 10 to the 5th ampere per square centimeter, which is about 1 to 2 orders smaller than the case of heavy metal, and the extracted effective spin-off angle is about 1.75. So we indeed show, this, laboratory interesting topological material can switch, conventional 3D ferromagnet. Again, these materials, were grown by molecular beam epitaxy, this bismuth-selenide, and that is not really industry friendly. So we tried to deposit this bismuth-selenide using sputtering. Initially, Minnesota group reported by sputtered bismuth-selenide, the effective spin-off angle is, even larger than 18, and required, switching current density is 1 order smaller than our MBE grown films. So in our case, we found the resistivity is 100 times larger than our MBE grown case. And the effective spin-off angle is kind of in the same order with the Minnesota group. We found about 45 for 10 nanometer bismuth-selenide. And again, we were able to switch clearly. You can see from black to white and white to black. And the required current density along the bismuth-selenide is order of 10 to 3. So it's about 100 times smaller than Minnesota case, because our resistivity is about 100 times larger. So then, people, you may ask, what is the role of surface state? Because using sputtering technology, this is no more single crystalline, it's a polycrystalline. Then, this surface state even exists in polycrystalline samples. So, those are, I think, still outstanding question in the community. And there was a report, even in the polycrystalline, inside the, each grain, you can preserve this surface state. So there are, many interesting reports are upcoming. So let's see how the field can evolve. Well, then, as I mentioned, again, one of the major issue in this material is very large resistivity. So we can mitigate this issue by utilizing another types of topological material, so-called wire semi-metals. In this case, even the bulk can support a very strong spin-orbit coupling. So we don't need to worry about current shunting through the bulk, because still we can generate reasonable amount of spin current in bulk. So one of the prototypical material of wire semi-metal is the tungsten ditelluride, WTE2. So we first try to understand is charge conductivity first. This material has a very unique atomic arrangement. If you look at this structure, you can see along the in-plane direction, when we inject the current along the A crystalline direction or B crystalline direction, you can expect conductivity is very, anisotropic. If we measure typical photovoltaic signal, this is unpolarized, so this basically only measure charge carrier properties in this case. MOS2 is one of the typical, 2D materials. So we tried as a control experiment. You can see typical photovoltaic signal happens around the contact, between the contact and the material, because the local electric field is the strongest here. And if you go to the opposite contact, because the electric field is opposite direction, you see basically opposite, polarity of the signal. This is very typical. No matter what you material measure, photovoltaic mapping, you will always see, because we don't apply any DC current here. But in this material, if you look at the data, tungsten ditelluride, we see this photocurrent everywhere in this film. very far away from the contact, we can still see. That indicates it has a very long carrier diffusion length. And we found it's about 3.2 micrometer, which is enormous. The other one is you can see across the contact, the signal distribution is not like a mirror image. If you look at the case of MOS2, it's basically a mirror image across this contact. But however, in this case, it's not. So that indicates it has a very anisotropic conductivity along the A direction or B direction, depending on the crystalline arrangement with respect to the contact location. So that basically gives us information. This material has a very elliptical Fermi surface, not like a typical circular Fermi surface. We were, able to also get a very large area samples from our collaborator. Then, it can be a centimeter scale of this 2D material using conventional CBD technique. So once we have very large area films, then we can do terahertz measurement, because terahertz wavelength is order of roughly a millimeter. So we need a very large sample. We can shine circular polarized light. Then, as I mentioned earlier, circular polarized light will be coupled with the spin up or down. Then we found that depending on the polarization, then we can excite only up or down, and that can be measured using basically terahertz emission from the sample. So you can see in this case, the full width half maximum is less than 1 picosecond. So we can basically generate spin current, it's a picosecond, basically terahertz spin current depending on the light polarization. The principle is this: if you inject, for example, right hand polarized, we only excite the positive momentum case. So the spin will move one particular direction. But once you excite with the left circular polarized light, then we excite the other branch, which has a negative momentum. So excited carrier will move to the opposite direction. So basically, this experiment indicates this material has out-of-plane spin texture. And this is particularly important for modern spin orbital device, because in order to break the symmetry, to switch the perpendicular anisotropy material, we had to apply external small in-plane magnetic field. But this is not very preferred in real application. We had to eliminate this external magnetic field. So once we can have this out-of-plane spin texture material, we can generate, spin accumulation, tilted along the out-of-plane direction. Then we can directly switch out-of-plane anisotropy materials. First, we tried the in-plane anisotropy material like we did in topological insulator. So we deposit permalloy on top of tungsten ditelluride. Depending on charge current flow direction, we were able to switch from black to white and white to black. And you can see the necessary charge current is now 3 times 10 to the 5th, about half of the previous TI case. But even more important thing is the charge conductivity is much higher in this material. The junction resistivity is much smaller compared to the TI case. So total power consumption is order of a magnitude smaller in this wire semi-metal case. And also we infer from the domain wall tilting angle, there is also a role of Jablonski-Moria interaction in this case. We can also study as a function of tungsten ditelluride thickness and effective spinor angle. We found it grows as we increase the tungsten ditelluride thickness. But if you now look at the length scale of this, it's very interesting. You can see this is order of what, 20 to 100 nanometer. So if you compare this with the previous, platinum case, look at this platinum case. It's saturated about, like 5 nanometer in a heavy metal case. But in this, the tungsten ditelluride case, you can see it sort of start to saturate in order of like 100 nanometer. That indicate effective, spin diffusion length in this material is also much, much longer compared to any heavy metal case. Then the other information is as we increase the thickness, it increase and saturates sort of. So that means it has a significant bulk contribution in the spin transport. Or we can now use so-called anti-notch shape, dumbbell patterning, and then we can only move only one domain wire from one location to the other and back and forth. So once we adjust the amount of the the current density in this rounded part is smaller, so the domain wire will always stop at the neck point. So then we can just move back and forth this domain wire, which can eliminate the extra energy necessary to nucleate domain wire. So we found about 3 times reduction in terms of the current density compared to no domain wire case, and this will give us the about 1 order power consumption saving compared to rectangular channel. And once we compare with the case of the platinum, we found about 20 times smaller power consumption. So again, this wire semi-metal is a very interesting topological, materials, but at room temperature we can switch, conventional 3D ferromagnet. So finally, I'm gonna just touch briefly about the magnon torque. As I mentioned in the earlier demonstration, we use this spin current generation layer, either using topological insulator or wire semi-metals. Then on top, we put this 3D ferromagnet, which is very relevant for real application. Then by applying the charge current, we can switch this magnetic layer. But the problem is because this bismuth-selenide or tungsten ditelluride have very large resistivity, a lot of current will go through nickel ion layer. It's a current shunting effect. Also, some of the problem is bulk transport issue. This is another current shunting in mostly seriously happening in bismuth-selenide case. So we try to eliminate this current shunting into the ferromagnet by adding this nickel oxide layer in between. Because nickel oxide is a good insulator, then the injected charge current will only flow through the bismuth-selenide once we isolate this magnetic layer only in the middle. So there will be no current shunting. Then only possible way to switch this ferromagnet is through basically magnon. So once we inject charge current, it will generate spin current in bismuth-selenide. Then this spin current should be converted into magnon in nickel oxide and propagate. And this magnon should somehow give a torque to this ferromagnet and switch this magnetic layer. So it's kind of wave-based switching. So we study as a function of nickel oxide here, and then we measure STFMR. Then initially, as we increase the thickness of nickel oxide in like 1 nanometer, 2 nanometer, we see just efficiency quickly quench to almost 0, which is kind of expected because if the nickel oxide is insulating property, basically it blocks all the spin current. However, as we keep increase the nickel oxide, we found after 20 nanometer, there is a peak at 25 nanometer, and then the efficiency is about half of, at the 0 nickel oxide case, which is quite substantial. So it's very surprising because 20 nanometer of nickel oxide is a really thick and good insulator. There is no way you can inject any, direct, charge current or spin current. So the only way to generate this torque is through the magnon inside the nickel oxide. So once we do very simple, exponential decay length fitting, less than 3 nanometer, we found 1 nanometer decay length in this very thin regime. And I think this is nothing to do with the magnons. It's just, modulating your interfacial spin transmission probability. If you look back, some other magnon report through nickel oxide using spin pumping or spin Seebeck effect, they reported monotonic decay as you increase the nickel oxide thickness, but there was very interesting peak at 1 nanometer. People found this 1 nanometer peak and then monotonically decay. On the other hand, we found there is a huge second peak, which is quite different. So we try to fit this thicker regime. Then we found the decay length is about 30 nanometer. So we deduce our magnon diffusion length is about 30 nanometer in our case. How do we understand this 1 nanometer peak? So I think we need to look at these material properties. Nickel oxide, below 1 nanometer is no longer an insulator. Actually, it's partially conducting, and you can see, the density of state, in the middle of the gap. But once we grow more than 1 nanometer, then the gap fully developed, and then it works as a good sort of normal insulator. So that's why I believe this peak at 1 nanometer is due to this basically modulating this transmission rate by adding extra materials. To prove our measurement is indeed a Magnon feature, basically temperature dependence measurement is a good way. And nickel oxide about 25 nanometer has a blocking temperature around 200 Kelvin. So once the material is around the blocking temperature, basically spin can easily fluctuate. So Magnon excitation will be higher at that particular temperature. So if you look at our 25 nanometer case, we can see the maximum efficiency of spin transmission happen at around 200 Kelvin. And depending on the thickness, it really mimic this blocking behavior. So by doing this, we confirm our measurement is really Magnon originated, spin torque. So as a quick summary, I show you basically spin orbit technologies, mostly for magnetic memory switching aspect. So initially I showed topological insulators, a very interesting candidate with a very large, high spin to charge conversion efficiency. And most of the behavior we can, attribute to the surface torque. One of the major issue is very large resistivity, inducing large power consumption. So in order to mitigate, we can use wire semimeters, because wire semimeter has a smaller resistivity, but at the same time, bulk can generate a reasonable amount of spin torque. Finally, if we want to eliminate all these large resistivity issue and current shunting problem, we can think about Magnon torque. In this case, there is no current shunting, but still at this moment, we had to inject quite a considerable amount of charge current to generate Magnons. If somebody can, come up with a new idea, we can generate huge Magnon population without, injecting, large charge current. I think that can really revolutionize the, future devices without, using even electrons. So we have to change maybe the name. No more electronics, because it will be some magnotronics maybe. So for this, I want to thanks to many of my group members also who contributed significantly, but now they became all professors in different institutes and also many international collaborators. Okay, thank you very much.
Okay, thank you, Professor Yang. Madam, you are muted.
Oh, okay. Yeah. So now can you hear me?
Yes, yes.
Yeah, we can hear
Am
you.
I audible? Yeah. So I would just like to thank Professor Yang for a very vivid presentation. And if there are maybe a couple of questions we can take, if anyone has, Professor Mudili, you told me that there will be some chat, but I don't see on my screen.
Maybe I can read out that question. There is one question in
Yeah.
the chat by Anuj
Yeah.
Kumar. How fast resistance changes in a topological insulator? So probably the speed of, have you measured that speed of change of resistance?
Speed of, can
How
you repeat
fast the
your question?
how fast resistance changes in topological insulator?
Resistance change, we haven't really measured resistance change. I don't see any particular region, it will be really slow compared to any other materials. I think basically it should be same as a typical, semiconductor or metal.
Okay. Madam, you're muted, madam.
Oh, okay. I'm sorry. Now can you hear me?
Yeah, we can hear you.
Okay. Yeah. So, Professor Yang, I would like to know what is your thoughts on why many other groups you said have shown that 1 nanometer nickel oxide is the optimal thickness for NIO, whereas in your case it showed a second peak at around 25 nanometer, right?
That's right. Yeah.
So why do you think, what was different because that would be much easier to control? So what is different in your case that is like in comparison to others that you got the
Okay.
second peak at 25?
Sure. I think, for example, if you look at platinum and YIG in this particular experiment,
Yeah.
YIG is a very good conducting metal,
Yes.
and platinum, and YIG is insulator.
Yeah.
Okay, they are, in terms of conductivity, is two different. Now, if you add a kind of intermediate material like a nickel oxide, which has some kind of very bad conductor, but it's much better than YIG. It's a sort of intermediate materials in the middle, so you can kind of think about it's like some kind of buffer, let the between the very conducting to very insulating, sort of is in the middle of the property, which can sort of improve so-called spin mixing conductance. So that's my speculation.
So is it a preferred layer that you would suggest instead of, let's say, tantalum or something like that? I mean, how is it, why the choice of nickel oxide itself? I am just asking, what is the reason? YIG, yes, it's a known insulator.
Sure. I think this behavior will happen very widely in materials. For example, even you use some other materials, I think you will see similar behavior depending on how you modulate your spin mixing conductance. And people try to measure those using mostly some kind of metallic insertion layer. But in this case, it works with the 1 nanometer. But as I mentioned, 1 nanometer is not a good insulator. Actually, it's just about the transition. So people thought when they inserted nickel oxide, they initially thought this is insulator. But no, actually, if you really measure the material property of 1 nanometer nickel oxide, it's not an insulator. So they added some kind of very dirty semiconductor in a way.
Okay. So it acts like a dirty semiconductor.
That's right. But however, in our case, I believe this indication, a peak at 25 nanometer must be, magnum, because there is no other possible way.
There is no other way. Yeah, no other possibility. That is true. Okay. Thank you.
Thank you.
Anyone else has any question? If not, anyway, we started late. It was really wonderful listening to you, Professor Yang. And we do hope that in future, whenever you are coming to India, you will find some time, because Pranab told me that you were here, but you couldn't make it to Delhi. So next time, please do visit us, and our students will really gain immensely from you. Thank you so much.
Thank you very much. Yeah.
Thank you.
Thank you, Professor Yang.
Thank you. Yeah.
So I guess you have to unshare. Yeah.
Let me see.
So our next, shall I start, Pranav? Yeah. So our next.
Yeah, you can start.
Okay. So our next invited speaker is Professor Lai from National Tsinghua University in Taiwan. Professor Lai is a very well-known person again in the field of magnetism, magnetic materials, and he received his PhD in 1997 from the same university, like I think Stanford University.
Stanford.
Yes, Stanford in 1997. Again, he is one of the very well-known names in this field, and his research work focuses on magnetic materials, spintronic devices, thin film, solar cells. He has also published about more than 200 peer-reviewed papers, and he is an IEEE fellow and MRS Taiwan fellow. So we are very happy to welcome Professor Lai to let us know about manipulating exchange bias by spin orbit torque. Professor Lai, are you around?
Professor Lai, we can see your screen. You can just make full screen and you can start.
But we can't hear him, right?
No, yeah. Yeah, he has to, he's muted right now.
Okay.
Yeah,
Can you?
now I can.
Yeah. So, okay.
Okay. I would like to see my screen. I cannot see my screen now.
Oh, okay. So, Pranab, see if you can help. We can see your screen.
We are seeing your screen and also your talk.
Just a moment. Okay. Yeah, because if I cannot see the screen, I don't. I cannot change the.
So I have also your talk. If you want, I can share it.
Yeah, but because I cannot see it from my screen, so I don't know where. Probably just wait a minute. I log. Yeah, I log in the system again.
You can stop sharing and share again. It will work.
Okay.
Okay. Yeah.
Yeah.
Yes. Yes. Very good. Very good.
Okay. Great.
Now it is great.
Yeah. Sorry for a delay. Thank you for the kind introduction, and I also like to thank the organizer for inviting me to give this presentation. I'm going to talk about the manipulation for the exchange bias by spin orbital torque. My name is Qi Lai from Tsinghua University in Taiwan.
I think you muted yourself somehow.
Professor Lai, you have muted yourself. We can't hear you, Professor Lai.
Can you hear me now?
Now we can
Yes,
hear.
yes.
Yes.
Okay, good. Okay. So basically, I'm going to talk two topics. The first one is for the three trilayers. It composed of ferromagnet, cobalt, contact with anti-ferromagnet, eluding magnets. And in this structure, I actually use the platinum as the spin current source. So I'm going to show you by using the spin orbital torque, we don't only change the magnetization of the cobalt, we also reverse the exchange bias between the cobalt and the eluding magnets. On the second topic, I am going to focus on the bilayer for the platinum magnets and the cobalt. So in this case, we use the platinum magnets as a spin current source as well as an antiferromagnet. So I'm going to show you for this kind of structure, we can modify the exchange bias. Okay, so here I show you the typical way we can actually induce the exchange bias in the bilayer of ferromagnet and antiferromagnet. Typically, we can deposit the film in the external magnetic field, or we actually can do the field cooling. In both ways, we actually have an external field to align the magnetization of the ferromagnet. And at the same time, we need to have some disturbance, even from the energetic bombardment of the atoms, or in fact, we have some kind of the thermal energy, so that we can reorientate the interfacial spins of the antiferromagnet, so that the interfacial spin can be aligned with the direction of the magnetization of the ferromagnets. And that's the typical way we can actually build the exchange bias. So in the first part, I'm going to show you in this kind of tri-layer, we can actually don't use any kind of the traditional disturbance. We can just use the SOT, spin orbital torque, to do the reversal of the exchange bias. Okay, here comes the layer structure. We actually have the three key components. Platinum used as the spin current source. Ferromagnet, cobalt, and antiferromagnet, eluting magnets. So you can see that, in fact, we have a quite large exchange bias. This is indeed in the perpendicular direction. So the exchange bias is around 1,000 Ørsted. The reason to get this kind of dual loop with a large exchange bias is due to whenever we deposit the cobalt on top of the platinum, we build quite a strong perpendicular anisotropy with two different domains. So when the eluting magnets deposit on top of the cobalt, the interfacial spins would be aligned with the cobalt magnetization. So you can see that basically we have two kinds of pinning direction in the S deposit films. And later on, if we do a little bit field annealing, we can select one of these shifted loops. Okay, here comes the SOT switching. So we actually pattern our device into the lumbar, and we use the focus mode to detect the magnetization information. And because this is perpendicular anisotropy film, so we need to have in-plane HX, which is applied along the current direction. So you can see that with the presence of HX, we can see a very beautiful magnetization switching from one side to another. Based on the polarity of the SOT curve, we can know that the spin current indeed from the bottom of the platinum. As you may know, the eluting magnet itself can also generate the spin current. However, in this case, we believe that the resistance of eluting magnets is much larger than the platinum. That's why when we pass through the charge current into these resistors in parallel, most of the current go into the platinum, and which generated the spin current. Indeed, we actually have the comparison samples, which we replace the eluting magnets by platinum. So you can see that in this case, we see the changes of the SOT polarity, which indicate the spin current coming from the top. So in our structure, we are pretty sure that the majority of the spin current comes from the bottom platinum. Okay, now we turn our focus to the direction of the exchange bias. As I say, if we slightly anneal our sample, we can actually pick up one shifted hysteresis loop, as I shown here. So the magnetization originally is on the positive direction. So we give the positive current, and then we switch the magnetization of the cobalt from the positive to the negative. But surprisingly, you can see that not only the magnetization direction changes, we also change the exchange bias direction from the negative to positive. And then we actually apply the current in the negative direction, we can actually change the exchange bias back to the negative direction. So you can see that this is quite effective manipulation of the direction of the exchange bias, which means by using the spin orbital torque, we don't only switch the ferromagnetic magnetization, we actually also can change the direction of the exchange bias. Well, you may argue that could this be due to the dual heating effect, because we actually need to apply not a very small current into the device. To address this question, we actually work on the system with ion magnets. The reason for ion magnets we used are twofold. The first one, ion magnets has much lower blocking temperature than eluting magnets. So you can imagine that if dual heating effect is significant, then we should see much clean and much clear evidence in this system. Additionally, ion magnets has a very little spin current source generated, so we can actually eliminate the contribution of the spin current from top of antiferromagnet. So in this case, we also see whenever we change the current direction, we change the direction of the exchange bias as we observed in the eluting magnet's case. Okay, now we actually change the bottom layer. Original bottom layer is platinum, which used as the spin current source. Okay, here we actually change it into the copper. So as you may know, copper has a very little contribution to the spin current. So we on purpose to have the thickness of the copper, which can have the same current density as the platinum. So in this case, when we run the current into the devices, the dual heating effect would be identical to the sample with the platinum. So if we can see any kind of changes of exchange bias in this system, then it tells us that the dual heating need to be considered. Okay, and in this case, as I mentioned, we actually have the two states because the exchange bias is slightly smaller than corrosivity, so that we can actually apply the external field to change the magnetization from positive to negative. Okay, so now if we run the current into the devices, because the Curie temperature of the ferromagnet is much higher than blocking temperature of the ion magnets. So when dual heating is important, you can imagine that we will have the flip of the ion magnets interfacial spin to be aligned with the ferromagnetic magnetization direction. If that is the case, then we should see the changes of the exchange bias. Okay, now let us put the current in. So based on the initial curve, we know that the magnetization still stay at the negative direction. That's what we expect, because in this system, we don't have any spin current source. So in principle, we should not see any changes of the magnetization direction. At the same time, you can see that no changes at all for the exchange bias. As I mentioned, if the dual heating is important, then the interfacial spin of the ion magnets should be reversed to the same direction of the cobalt nickel. But it doesn't happen because you can see that we still have a negative exchange bias, which means interfacial spin pointing to the positive direction. So even we give the different direction of the current, we got the identical results, which tell us that the dual heating itself may exist, but it definitely is not the dominating factor here. Otherwise, in this kind of system, we should also see the changes of the exchange bias. We further calibrate the temperature rise during the current applied. So for the eluting magnet's case, the critical current we need is 3 times 10 to 7 amp per centimeter square. So we can actually give the different current density, and at the same time, we measure the resistance. So we got the relationship between the resistance and the current density. And because this is the metallic system, so it's quite easy to calibrate the temperature with the resistance. It's almost a proportional relationship. So by using this kind of calibration, we put in our current density, we got the resistance, and then we can know what is the temperature rise during the current apply. So indeed, the temperature goes up to around 85 degrees C. But compared to the breaking temperature of eluting manganese and cobalt, it's about 150 degrees C, which means pure heating indeed exists, but its effect is much small, and which cannot significantly change the interfacial spins at the interface. Next, I would like to talk about the HX effect. As you may know, this is a perpendicular magnetization, so it's called Z-type switching by SOT. So for this kind of Z-type, we always need to apply the applied field along the current direction. So this kind of external field gives us the switching of the ferromagnet. Okay, so in this case, we are going to see how this HX affect the interfacial spins of the antiferromagnet. So in this sample, this is the hysteresis loop. We on purpose to use a cobalt nickel. So now again, we have two stable state at the zero field. So this is the so-called anti-parallel mode. And we run the current in, and we did not give any external field. Turns out that because no external field, we don't see the changes of the ferromagnetic magnetization. It still keep at the bottom, at the negative side. Surprisingly, we can see that the exchange bias changes from negative to positive, which means even we did not change the magnetization direction of the ferromagnet, we still can have the chance to disturb the interface, which make the interfacial eluting manganese spin to be aligned with the ferromagnetic magnetization. And then we, in fact, apply the HX and see, in fact, we also do the different direction of the current, and we got the same result. Okay, now we give the positive current, okay? So for the positive current from the switching curve, we know that we don't have any switching at all for the ferromagnetic magnetization. So again, you can see that the ferromagnetic magnetization does not change. However, again, we see the changes of the exchange bias direction. So you can notice that it seems to me that the interfacial spin of eluting manganese follow the magnetization of ferromagnet. So if we don't have the changes of the ferromagnetic magnetization, but the spin current still gives a large enough disturbance at the interface so that the eluting manganese change the direction to be aligned with the cobalt nickel. That's why, although we don't see the changes of the ferromagnetic moment, but we still see the changes of the exchange bias. So for the last test, we actually give the negative current. So for the negative current now, we actually change the magnetization from the negative to the positive. But you can see that right now, compared to the original state, we don't see the changes of the exchange bias. That's because the ferromagnetic moment right now pointing to up. This is the preferred direction for the eluting manganese. That's why we don't see the changes of the exchange bias. So from all this set of the data, it tells us that the reversal of the interfacial spins indeed depends on the ferromagnetic magnetization, regardless of the HX. So this is very different from the switching of the ferromagnet. the HX direction or the existence of the HX is quite critical to the switching of the ferromagnetic magnetization. But it seems to not be the case for the antiferromagnetic spins. On the other hand, we believe this spin current provides significant disturbance for the interfacial spins to be aligned with a ferromagnet magnetization. It's just like the field cooling. We need to give the thermal energy, but we already proved this is indeed not from the Joule heating, but the SOT itself can really provide significant disturbance. So the next question we would like to answer is how far this spin current can go and reach the interface between the ferromagnet and antiferromagnet, and it turns out can give us the changes of the exchange bias. So we increase the thickness of the ferromagnetic layers. Turns out you can see that up to 2 nanometer, we still see the changes of the ferromagnetic moment as well as the exchange bias. But if we further increase the thickness of the ferromagnet to 3.4 nanometer, we can see that we have the partial switch from the positive to negative for the magnetic moments, but we don't see the changes of the exchange bias. You can see they are both in the negative direction. So basically, the whole idea is the following. We actually put the charge current into the platinum and then generated the spin current. The spin current is absorbed by the ferromagnet moments, and at the end, it reaches the interface of the cobalt and the eluting magnets. So if the thickness of ferromagnet is too large, then typically the spin current may not have significant effects at the interface. One thing I would like to remind you is that the spin orbital torque is actually the divergence of the spin current. Although you can see that the spin current indeed gradually change to quite a small value. However, at the interface between the ferromagnet and antiferromagnet, it could be due to the different relaxation rate. So we have the divergence here. We actually has enhanced the spin orbital torque at the interface. So this kind of enhanced spin orbital torque may be the reason to see the significant disturbance of the interfacial spins by using the SOT. Okay, now I would like to focus on the second topic. This is on the bilayer for the platinum manganese and the cobalt. And the platinum manganese is antiferromagnet if it is ordered structure at a 1,0 structure. So we need to anneal the system at a high temperature to get the L10 structure. In addition, this platinum manganese can serve as a spin current source. So we would like to see the spin current source from the antiferromagnet itself, how it affects the exchange bias between antiferromagnet and the ferromagnet. Okay, so this is the layer structure we have. Again, this cobalt has quite a strong perpendicular anisotropy. So this is hysteresis loop along the perpendicular direction. So you can see that in fact we still can establish the perpendicular exchange bias, although right now this value is quite small compared to the eluting manganese case. This could be due to the spin structure because platinum manganese itself has a very little contributions of the spin lattice along the z-axis. So the perpendicular exchange bias is relatively small here. Okay, so I would like to draw your attention to this SOT curve. So this SOT curve, we start from this negative magnetization. So as I shown here, so the magnetization of the cobalt is sort of anti-parallel to the interfacial spins of the platinum manganese. So when we give the negative current, we can see a full switching of the cobalt from the negative direction to the positive direction. And because we did not change the antiferromagnet too much, so basically we see a quite similar hysteresis loop. I would like to emphasize that this interface will be very different from the cobalt and eluting magnets. As I mentioned, product magnets need to be annealed to become the older state. So exchange coupling strengths would have a distribution. For example, this one has quite a strong one, and this one has a very, very small coupling. In addition, we may have a different local anisotropy for the product magnets due to the annealing effects. So you can see that if we start from the positive magnetization, so this is more like a parallel state, we use the same current to give the switch to the negative side. Turns out you can find that we cannot get the full switching by using the same current density as the other side. The reason for this, we believe, is in some part of the interface, we have quite a strong coupling, but we also have locally has a quite a large anisotropy, such that this area, magnetization of the cobalt, would not be switched. But in some area, if we have a very strong coupling with a weak anisotropy, then we have the chance to also switch the antiferromagnetic spins at the interface. So it turns out in this kind of product magnet cobalt system, we cannot see the full reversal of the exchange bias as we show you earlier in the eluting magnets case. And we believe that first of all, we may not have a strong enough coupling between ferromagnet and antiferromagnet. Another thing is local anisotropy of the antiferromagnet is stronger in the product magnets case. So in the final part, I'm going to show you for the same system, product magnets cobalt, we want to enhance our exchange bias. So we actually work on the in-plane magnetization, which can give us a much better exchange bias. But in most of the cases, if we have an in-plane magnetization, for the SOT detection, it becomes much more challenging. People can use the MTJ to read out or use the LMOC to get the signal. But for LMOC, it's sensitive to the surface capping. For the MTJ structure, the process is quite complicated. So here I would like to show you one kind of different ways we can detect the magnetization switching in so-called Y-type SOT devices. So the device is shown here. We actually run the current in the X direction, and we measure the X direction resistance, is so-called RXS. So we can clearly see the anisotropy magnetoresistance effect, AMR effect. So you can see that whenever we change the magnetization, it has to close the multi-domain state. That gives us the peak of the MR curve. So by using this kind of curve, we can still get the electrical properties, the resistance, without this kind of a curve signal. So from here, we can also see the shift of the two peaks, which give us the value of exchange bias. So if we don't have any magnetization changes, like this blue line, then basically the AMR curve we are going to see is something like this, without any peak information. But if we change the magnetization from the negative to the positive, then you are going to see in the AMR curve, you are going to see this kind of shape of the single peak. And that tells us we indeed, by using the current, we can switch the magnetization in-plane. So finally, I would like to show you, by using this kind of detection scheme, we can find one quite interesting phenomena for the different interface situation. As I say, the product magnets is ordered the structure after annealing. So we on purpose did not anneal the sample. So these product magnets become paramagnetic, and it's purely spin current source. So you can see that AMI is quite symmetric to the center. So we need to apply the current above 40 milliamp to switch. You can see that this is unswitched signature. This is a switch behavior. Okay, so we need to apply 40 milliamp to switch the magnetization of cobalt. And then we anneal the sample to get the antiferromagnetic product magnets. But we can align the cobalt parallel to the interfacial spins or anti-parallel to the product magnets. So for the anti-parallel state, we can see that the switching current is much reduced from 40 milliamp to 30 milliamp, which means this existence of this interfacial spin from the product magnets help the switching of the ferromagnetic moments. On the other hand, if we have the parallel configuration, which means cobalt is parallel to the interfacial spin of the product magnets, even we increase the current up to 15 milliamp, we don't see any switching at all. This is similar to the previous perpendicular case. For the anti-parallel state, we always see easier switching than the case in the parallel state. So indeed, if we can manipulate the configuration in the antiferromagnet, we may have the chance to further reduce the critical current needed for the ferromagnetic switching. So here comes a summary of my talk. On the first part, I show you we can have the spin current generated from the platinum with a very strong exchange bias between cobalt and the iridium magnet. In that case, SOT does not only switch ferromagnetic moment, but also switch the exchange bias. You can get more information on this Nature Material publications. And for the product magnets cobalt case, and we found a quite interesting result. So for the interfacial spin difference, for the anti-parallel and the parallel spin configuration, we can see a very different critical current for the switching of the ferromagnetic moments. So which means if we have the chance to manipulate the spin configuration at the interface of the antiferromagnet, we may have the chance to further reduce the current for ferromagnetic moments. I would like to acknowledge my team members and also the Professor Lee from the physics department. Thank you for your kind attention.
Okay. Thank you, Professor Lai, for a very wonderful talk. And now the session is actually open for discussion. Pranav, do you have the chat? Maybe you can.
There is no question in the chat.
Okay.
But maybe I can start with one question.
Yeah.
So I was just wondering that you said the spin orbit torque is coming from the platinum layer, which is the bottom, whereas the exchange bias is the top, cobalt iron and the iridium manganese, right? So
Yes.
I was wondering if there is a thickness dependence on the ferromagnetic layer.
Yes, I indeed show this in one of the slides. If we, this one. So you can see that we change the thickness of the ferromagnet. This is your question, right?
Mm-hmm. Yeah.
Yeah.
I imagine if it is thicker, then you should not see this effect, right?
Yeah, we don't. You can see that for 3.4 nanometer, exchange bias are not changed because most of the spin current already been absorbed by the cobalt nickel. So it does not arrive the interface. That's why we don't see the changes of exchange bias. But because spin current can still locally change the magnetization of the cobalt nickel, so you can see that the magnetization can be partially changed for the thick cobalt nickel layers.
Okay. Thank you. So
No
there is
problem.
one question by Karthik Raman. Can you unmute and tell? Yeah.
Yeah. So thanks, brother. So I had a question on the first part, which is related to, again, this reversal of exchange bias. So
Yes.
since you're able to do this by essentially spin-off talk, so my question is, have you been able to observe any induced magnetic frustration in your system in terms of, say, spin glass behavior, interfacial spin glass behavior? Are you able to artificially generate it through this effect?
Can you repeat your question again? I didn't get the point.
So my question was, since this reversal of exchange bias is driven
Yes.
by essentially the reversal of the spins in the antiferromagnet as well.
Yes.
So in a way, it's a stochastic process of flipping the spins. So the question is whether you can induce magnetic frustration or disorder, giving rise to interfacial spin glass response in these systems.
So your question is, can it be possible make the interface to become completely disordered state? Is that the question?
Yes. So you can see a spin glass like exchange response in your system so that you can
Yeah,
experimentally.
that's a good point. I think there's a chance, but we need to try the window because, as I say in the second part, we need to consider two things. One is the coupling strength between ferromagnet and antiferromagnet. Another one is the local anisotropy of the antiferromagnet. So I think there's a window which the spin orbital torque can give large enough disturbance, and the coupling strength is something like in the middle. So turns out that you can have sort of a frustrated like a spin glass state at the interface. But it's really depending on the materials you use, the interface conditions.
Sure. Yeah, got your point. Thank you.
Okay.
Okay. If there are no other questions, then we would like to thank Professor Lai for this beautiful talk. Thank you, Professor Lai. Thanks.
Okay. Thank you very much.
Thank you, Professor Lai.
Yeah, thanks.
Just share the.
Professor Mudli, you can make one announcement.
Yes.
Yes,
Yes.
because you just make an announcement before the talk that on the delegate portal, there is a ask question link. So where they can press it and then they can write the question.
Okay, but we are not seeing those questions here. I only see some questions who are sent to me privately.
Okay,
But,
right. So maybe they are not, because we did the dry run also. Maybe you can just make an announcement that on the delegate portal, there is a ask question link where they can press and write the question. Okay, then this will be visible to them. Okay, thanks.
Okay.
So shall we move over to the next speaker?
Yes, Madam, can you introduce the next speaker?
Yeah. Speaker is Professor Saroj Prasad Dash, and I think many of us know Saroj very well. He was our MTech SSM student, and he finished his PhD in 2007 from MPI Stuttgart, Germany. We are all very happy to welcome Saroj. We all know the contributions he has made to Spintronics and eagerly waiting to listen from him, and then we can discuss. Welcome, Saroj.
Thank you, madam, for the kind introduction, and thank you, the organizers, for giving me the chance to talk about our work here. The title of my talk is Spin Galvanic Effects in Topological Material Heterostructures. So we use the two-dimensional platform, like here you see the graphene, and we, on top of that, we put different materials to investigate their spin charge conversion effects.
Saroj, are your okay, yeah. So we
Yes.
couldn't see the changed slide,
Yeah.
so that is what. Now it's
okay.
okay.
Yeah, it's working.
Yeah.
So most of you know that how the graphene behaves with electronic properties. It have this Dirac band structure. It's a first kind of material where people could measure the Dirac electrons. And after that, there was discovery of this topological quantum materials, where due to huge spin orbit coupling, so there is a band inversion taking place. And it can have different types of material like topological insulators or Weil or Dirac semimetals, depending on their crystal structure and symmetry, broken or intact. So for example, these materials, why they are interesting for spintronics community is that it have very nice spin textures. So for example, if you see the topological insulator, so it have this Dirac band structure in the gap. So it's a surface current which can flow where the bulk is insulating. And the spin texture is in this Dirac bands, it's perpendicular to the momentum. So it's spin momentum locking. So when you pass a current, you can create spin polarization on the surface of these materials. And similarly, the newly found Weil and Dirac semimetals, so they have also interesting band structures, like here is the two Weil nodes shown here, and this the conduction band and the valence band, they have this is called Weil nodes, where they touch, and it have a new novel type of spin texture, where the Weil point is also spin polarized. That means the bulk band structure is spin polarized, and also the bulk bands are connected by a so-called Fermi arc. So that is also spin polarized. So in comparison to topological insulators, where you expect the surface spin should contribute, in the Weil semimetals, the advantage is that the both bulk and surface can be spin polarized. So let me start first with graphene. So I want to show that graphene can be used as a very good spin interconnect. So you can transport spin very long distance because it have this high mobility for the electrons because of the Dirac band structure, and it can because it have low spin orbit coupling, the spin scattering in graphene is very low. So if you consider the basic spin scattering mechanisms like Elliott effort, Econoper, or hyperfine interaction, so they are very small for the case of graphene. So that helps to get very long spin diffusion length and nanosecond spin lifetime at room temperature. So this is, for example, we made devices on a wafer scale graphene, which is 4-inch wafer. So we take one piece out of that, and we can make channels with ferromagnetic contacts. So this is the graphene channel with ferromagnetic contacts. So we can transport spin over 30 micrometer at room temperature. So that is very good for communicating spin from one side to other. And how we detect that? So we put this ferromagnetic contacts, then we inject spin from this one contact here, and the spin diffuse, and we detect with another ferromagnetic contact. It's a transport geometry, and we see the spin valve measurements when the ferromagnets are parallel or anti-parallel. You can do another type of measurement by applying a perpendicular magnetic field where you don't switch the magnet, but you allow the spins to precess with Larmor frequency when they are propagating in the graphene channel. So you see such signals for the parallel and also for the anti-parallel, it's downwards. So you can find out the spin lifetime in these materials by using the spin diffusion, precision, and dephasing terms. So it's around nanoseconds. So how to use such a graphene? So we thought to make complex architectures where we can send spin current from one magnet and communicate with other magnet on any place in the graphene. So one can make very complicated circuits. So that was not possible before because we could not transport spins for so long distance. So now, if you have memory elements, for example, here a ferromagnet, so you can communicate this between this magnet and the magnet far away just by sending a spin current. So that's what we showed. So I just briefly showed some of the things so that we can make spin circuit architectures, and we can investigate some spin dynamics in the single layer, bilayer, and tri-layer graphene, and we find it to be very isotropic. And also we could enhance the spin injection efficiency from ferromagnet into graphene by using boron nitride tunnel barriers. And of course, these 2D materials can be used in magnetic tunnel junctions for studying TMR, tunnel magnetoresistance. So so graphene is good material for spin transport, but how to control the spin? So to control the spin, either you need to create spin orbit coupling or magnetic proximity effect. So what we did is we put some heavy elements like molybdenum disulfide, which is also 2D material. So it have a van der Waals interaction, so we could induce spin orbit coupling in graphene. And then similarly, when we put a 2D magnetic material on graphene, we could also induce magnetic exchange interaction in graphene. So I will not go in details in this talk here, but I will focus more on the topological side. But what we are trying to do is trying to make graphene circuits, and on demand, we can create magnetic exchange or spin orbit or any kind of exchange interaction in the graphene layers. Because it's just one layer, you can place anything on top of that, and you can change its properties. So that is the advantage to make 2D spintronic circuits. And if you look at the 2D materials, there are many kinds of 2D materials available, which you can think even also in the bulk. So coming back to the topological quantum materials, so these topological insulators and their spin textures are interesting for spintronics. And how we can use it for spintronics is that what we need to do when we apply a charge current, we can create spin polarization in these materials. So most of you may be knowing that what is spin Hall effect. So when you pass a charge current, so spins are accumulated on the ends of these materials. So, but if you have the spin Hall effect can come from different origins. For example, it can be intrinsic or extrinsic. But if it is intrinsic, for example, if the material is topological and it have a large Berry curvature, that can give higher, larger spin Hall effect. And if you have also Rasbach-Edelstein effect, so band structure is split. So when you pass a current, so if you take a cut at the Fermi level here, so you create spin polarization because when you apply a momentum to the electrons, you shift the Fermi sphere and you accumulate these blue spins more than these red spins because they have more in number near the Fermi level. And finally, the topological materials. So if you have spin textures like this, so you can create also the spin polarization. And theoretically, it is predicted that you can get a new type of spin polarization and even very large spin polarization in these topological materials. So why this is again interesting, how can we use this spin polarization? So that's already known from 2011 that when you have a heavy element like tantalum, platinum, tungsten, and when you apply a current, you create spin polarization, and that spin on the top surface can switch a nanomagnet. That can be read through by electrically, and you can also use it for spin orbit torque and for magnetic memory applications. And in India, there are lots of activities also in this direction in IIT Delhi and also Bombay. So maybe I miss some people here, but it's quite interesting and it can get some applications because in last year, in 2000, a few years ago, it has been demonstrated over a 300 millimeter integration of SOT spin orbit torque MRAM by IMEC in Belgium. But they are now using these heavy metals like tantalum, tungsten, and platinum. So if you want to enhance the efficiency so that you can switch the magnets with less current, that means you need to create larger spin polarization. And for that, topological materials are again interesting. So let me start with the topological insulators. So the topological insulators like bismuth selenide and their compounds, and so it gives a nice Dirac band structure at the gap here. So people have measured the Dirac band structure by angle result photoemission spectroscopy. And if you see in India also, Professor Ratnamala Chatterjee at Delhi and some other people at different places, so they are working on also the topological materials. Particularly, I want to specify that together with Professor Ratnamala Chatterjee, we have a India-Sweden collaborative grant, and we are trying to explore the topology and magnetism in these quantum materials. So why this is interesting, that it can have a nice spin texture, and that has been also measured by angle result photoemission spectroscopy. That could be spin result. So the polarization of these materials without applying any current, so it's around at different K points here is around 75%, what they measured. Okay, so how to detect spin polarization in these topological insulators? So you can use a potentiometric measurement. So for example, I am showing here a material is BSTS. So it's a compound of bismuth, selenium, telluride, and selenide. So you can characterize this by measuring the magnetotransport, and you can see that it can have a weak anti-localization, showing it have high spin orbit coupling, and the material quality can be checked by looking at the Subnikov d-Haas oscillations at higher magnetic field. Okay, so what we did in these materials, so that we pass a current on this flake and we create the spin polarization, and we put a ferromagnetic material contact here on top to detect the spins under the contacts. So what we see when we sweep the magnetic field, we change the magnetization of this ferromagnet detector. And when they are parallel or anti-parallel to the ferromagnet, we can see the switching behavior, and that also changes with the current direction. So that gives an indication of that we create spin polarization into topological materials by applying a current. And that could be detected up to room temperature. But I want to mention that it can have some artifacts that it can pick up the stray Hall effect from the topological insulator. So one need to carefully do all the control experiments, for example, angle dependence and putting some intermediate interlayer in between the TI and this ferromagnet to rule out any stray Hall effects. So this is the signal what we see. Now we wanted to see whether this is coming from the bulk of the material or from the surface states. So how to do that? So you have to either tune the formulable of these materials by gate voltage, so which was very difficult in our case because we are detecting the surface, and when we apply the gate on the back side, so we can just tune the back surface, but the top surface still is not affected because this we have these metallic samples. So what we did here is we took two different compositions. For example, this is bismuth selenide, and this is the BSTS. And if you see the temperature dependence of the resistivity for bismuth selenide, it's metallic. But for BSTS, it's more semiconducting, but below 100 Kelvin, it's more metallic. And if we plot the magnitude of such a signal, the spin signal, we say, and with temperature, so what we see for bismuth selenide, it's almost independent of temperature, but for BSTS, below 100 Kelvin, the magnitude of the signal is much higher. So if you want to compare with the literature, and this is the, let's say, band structure where this is the Dirac band. So if you are here in the Dirac band, so you can maybe having larger spin polarization, but if you are going towards the bulk, so you may be having opposite spin polarization from the Rashba bands. So that can cancel out the spin polarization, and that can affect the measurement geometry. So most of the people use this topological insulator also for the spin orbit torque. So that's where the application potential of topological insulator looks like. But what are the main challenges? So they could see very large spin Hall angles, and with different thickness, you can see thinner samples also give larger spin Hall angle. But the main challenge, what is the interface? So how is the interface between bismuth selenide and the ferromagnet? So if it is not well controlled, we may not have the topological surface states, because we know that so there can be interdiffusion between the ferromagnet and the topological insulator, because you have to prepare them by sputtering or evaporation. And also, you might have known that the topological insulator, if you couple with a ferromagnet, so it can open a gap in the surface states, and so it can also give this anomalous, quantum anomalous Hall effect. So for example, with RPS, people have seen that if they dope iron with bismuth selenide, you can open the gap. And if you couple the ferromagnetic materials with the topological insulators, so you can also see quantum anomalous Hall effect. So in any case, so the interface in this spin orbit experiments, it's not very clear. Then there was a proposal how to improve the interface. And people have used different layers like copper or silver, so that there can be spin transparency between the topological insulator and the ferromagnet. But there are some proposals like putting on the top between the ferromagnet and TI a layer of graphene. So you can look at this theoretical proposal, and it looks like that you can create a giant Edelstein effect, or the spin polarization and a novel spin texture in the heterostructure. So that's what we wanted to find out a few years ago. And we just started with putting a topological insulator on top of graphene. So this is just one interface here, what was proposed. And we wanted to see how the graphene property is affected by putting a topological insulator. And we could collaborate with theoreticians, so they could show that, of course, we open a gap in graphene due to proximity spin or bridge coupling from the topological insulator. So that can be few millielectron volt. And interestingly, there can be very nice spin texture. So this is the energy dependence of the spin texture, what has been predicted. So near the Dirac point of graphene, the spins are out of plane. And if you go away from the Dirac point, spins are all in plane. So that we wanted to test in our experiment. And because it's a graphene, we can change the Fermi level by applying a gate voltage, and we can check what is the spin polarization. So that's what we did. So this is the graphene layer, and the topological insulator is on top here. And we have this ferromagnetic contacts. So we inject spins, and they are traveling below the TI in the graphene layer, because we have some interface resistance, and we don't expect graphene to go to the topological insulator, because they have around 10 kilo ohm interface resistance. So what we see when we go close to the Dirac point, so this is the Dirac point of our graphene. So when we go close to the Dirac point, like 0 volt here, so what we see, we don't have any spin signal. But when we go away from the Dirac point, we have higher spin signal. So that means, so when we are, because our spins, the ferromagnet cobalt here, having an in-plane spin, so the in-plane spin can show where we can detect also the in-plane spin with this detector. So the in-plane spin polarization is higher in magnitude, but when spins are not in plane, so we should not see any signal. So that's what we also observe. So that means our spins must be perpendicular. And we want to do some further experiment to find out whether the spins are really perpendicular at this Dirac point, but it needs further studies. And we wanted to find out what is the spin orbit coupling strength in this material. So this is lots of formula, but you just identify that this is the Elliott effort mechanism, and this is the economical mechanism, which is how they are related to the momentum scattering. So one is directly proportional, other is inversely proportional. So you can combine these both effects because we can consider both effects to be present in our material. So we can come up with this equation by just using this. And we can plot this and find out what is the spin orbit coupling in graphene topological insulator structures. So only graphene gives hundreds of micro electron volt of spin orbit coupling. But if we make a heterostructure, it gives up to 1 milli electron volt. So orders of magnitude higher spin orbit coupling. And we wanted to test that whether the spin orbit coupling we created in graphene due to proximity of topological insulator really gives a band structure change. So that's what it is predicted. So you have graphene plus topological insulator, you create a gap, and also spin texture, which is a magnified version is shown here. The spin texture should look like this. So this has been already predicted in theory. And now if you measure at this point, at the conduction band or the valence band, so it looks like a RASBA band structure. So you should be able to create spin polarization. And you can do also the inverse experiment that if you send a spin current, so you can also create a charge current. That is the inverse if so that is called spin galvanic effect. So inverse of spin Hall effect, for example, or Raspa-Edelstein effect, for example. So we made a device like this. So this is a graphene channel, the black one you see. So this SEM picture is taken after measurement. So some parts are broken. And so graphene is here. You put a topological insulator at one branch of this Hall bar structure. So we have this ferromagnetic contacts perpendicular to this geometry and also parallel. And we have this gold contacts, the non-magnetic contacts in the Hall bar. So you can do measurements on both sides in the heterostructure of the TI, also on the only graphene parts. So what we see here. So this is a schematic of our measurement. So we measure two voltages here. One is, let's say, voltage V, what you see here. So we send spin current from this ferromagnet into graphene, and they are coming to the heterostructure region, and we measure the voltage. And what we see, I'll come back to that. But before that, I just want to show what we see with this ferromagnet. So this is we are injecting spins and they are coming under the TI and they are arriving on the topological other side of the structure. And because the ferromagnets are perpendicular to each other, we see the spin precession signal, which is antisymmetric. That's very logical. But when we measure across the heterostructure, actually, if it is only graphene, we don't see anything. We have also measured on only graphene. But when we measure with a topological insulator graphene heterostructure, what we see when we have an in-plane sweep, we just switch this magnet, we see such switching signals, which is quite large and it's at room temperature. But if we do a perpendicular magnetic field, for example, with like a spin precession, so what we see is a signal like this. So that means, so spins are in plane in this heterostructure, and we could convert the spin current into a charge current, and this is due to Raspa-Edelstein effect, or we can say it's spin galvanic effect. But how it changes with gate voltage? So that will be the true test whether we really created a spin texture in graphene. So when we measure in the conduction band or the valence band, we see a sign change. And that is what expected if you look at the spin texture of this band, because you are dealing with electrons in the conduction band and holes in the valence band, and they have different spin polarization. So that makes it logical that we could create spin galvanic or detect spin galvanic effect in graphene TI heterostructure. So then I think that could be a good platform to use a topological insulator and a graphene layer, and then on top of that ferromagnet. So maybe you can create larger spin Hall effect or spin orbit torque effects. Okay, so far so good. So I showed you how topological insulators can be useful. But next, how to deal with their problem with the bulk contributions, because they are highly doped and surface states are always masked by the bulk contributions. And next, we go to wild semimetals, as I already mentioned, that it can have bulk spin polarization and also the surface states are spin polarized. Also, in the morning talk, you heard from the Professor Yang from NUS that these wild semimetals can be having interesting spin textures and spin polarization can be up to 80% as predicted theoretically. So what we use the same material like tungsten telluride here. So what is the advantage of this material? Because it is the type 2 wild semimeter. Type 2 means it's a wild cones, it's be tilted. And you have the surface states, and it can be bulk spin polarization. This is the spin texture of these materials for different wild nodes. So this is one wild node with electron and hole pocket, and the spin texture as calculated by our collaborator. And what is the advantage of this material? As you already heard this morning, that it have a broken symmetry or the lower crystal symmetry. So that helps to induce spin polarization, which is called unconventional in nature. So the polarization can be perpendicular. So just to mention again, what are the experiments people have done with tungsten telluride. So actually we started at the similar time that people did this spin orbit torque experiments with low symmetry material like tungsten telluride permalloy bilayer, where they see out of plane anti-damping torque. So that will help in the industry application, that you don't need an external magnetic field to break the symmetry, and it can be efficient for spin orbit torque experiments. And similar effects has been observed with spin the switching of the magnet with tungsten telluride, and you have seen how this contribution comes from the bulk of this material. So what we did, we actually used such materials like few nanometer thickness from 5 to 20 nanometer. We see nice Subnikov D-hash oscillations, very large magnetoresistance. So that indicates the materials we use have very high quality. So then we wanted to test the charge spin conversion in these heterostructures. And how we do that, we again do in a similar device geometry, like we have a graphene layer and we put tungsten telluride on top. So how to measure spin to charge conversion, or the inverse effect? So you can either pass a current in tungsten telluride, and then spins will be injected into graphene. Then you can detect with the ferromagnet, or you can do the inverse effect, so that you can inject spins from the ferromagnet into the graphene. Then spin will be transported to tungsten telluride, and you can detect a voltage. So these measurements can give very, very accurate results, because all experiments are made in a non-local way, so that you are not having any charge current flowing to the detector. So here I show one of these experiments. So you can go to this paper for all the measurement results. So what I show here is the inverse effect. So we apply a current here with the ferromagnet, spins are injected into tungsten telluride, so you detect a voltage. And we say it's a conventional charge spin conversion, because the spin current, charge current, and spin, they're orthogonal to each other. It's actually following the conventional rule. And in this way, when this rule is valid, so we see such a signal when we apply a perpendicular magnetic field. So spins while going towards the detector for the measurement, they can precess. So you see such a signal. And from that, you can find the spin Hall angle is 1.3% and spin diffusion length around 8 nanometer. And if you change the magnetization direction for plus M or minus M for this ferromagnet injector, you can also switch the direction of the signal. So that indicates the signal is, of course, coming from the spin to charge conversion in tungsten telluride. But surprisingly, we could also observe a signal which is we call unconventional charge spin conversion, and that is when we pass a current perpendicular to this tungsten telluride, we could inject spins, and the spin current and the charge current, they are actually parallel to each other. That is the difference. That's why we call unconventional charge spin conversion. So how we detect that? So it's a similar measurement, same device, in the same device we could measure it, but we apply a current not just across the tungsten telluride like we in the previous experiment, but perpendicular geometry, so that current is going from tungsten telluride into the graphene. And we did several control experiments to rule out the conventional spin Hall effect. So what we see by this ferromagnet, we detect the voltage. So that's the resistance you see. We plot here divided by voltage divided by the current. So we see the switching signal when we do in-plane sweep, and we see these Hanley signals when we do out-of-plane field sweeps. So that indicates that spin polarization we created in tungsten telluride and injected subsequently into graphene are in the plane, because that's from the symmetry of the Hanley curves, we can find out the spin polarization coming out from the tungsten telluride. So these experiments are very basic experiments. So this you may not be used for practical applications, but it will tell you exactly the spin polarization of your material and the spin orientation also from the topological materials. Okay, we can also do the inverse effect. So as you do with the current here, but you can also measure the voltage. So your tungsten telluride can also inject spins and also can detect spins, as people do by a spin Hall or inverse spin Hall effect. And the spin polarization coming out to be 10% without any optimization. I think further studies have to be done to find out good spin polarization. So I would like to summarize my talk. So I have shown you that we could create charge to spin conversion in topological material heterostructures. So here what I have shown is the spin galvanic effects in the graphene and topological material heterostructures. And I could show you that tungsten telluride is an interesting material for spin orbit torque. And the spin polarization in this material can be both conventional and unconventional in origin. So, and I would like to thank my team members who contributed to this work and the funding agencies. And I thank you for your attention.
Okay, Saroj, it was really very lucid and expressed everything with very informative talk. We thank you for this beautiful talk. And now maybe Pranav, can you see the questions in the chat box? The talk is now open for discussion. So let me first request Pranav to see if he has any. Pranav, you have to unmute yourself.
Hello.
Yeah.
Yeah, I don't see any question right now. Saroj, you can check in your chat box in case you got any questions directly.
If not, then I have a few things to just
No,
ask.
I don't see actually.
Okay, then madam, maybe you can ask some questions.
Yeah. So maybe if anyone else has any question, I'll give you first an option to speak. Pranav, do you have any question?
No, I don't have any.
Okay. Okay. So, I think it is very illuminating the way you are conceptualizing and doing these experiments. I'm just interested in knowing that has anyone tried to do wild semi-metal thin films on, or maybe some wild semi-metal and in conjunction with graphene, because that seems to be a good point to try. The way you try to explain it seems to me that will really overcome many problems that you have with TI and graphene interface. Can you tell a little about that? approach?
Yes, yes. So, as you mentioned, that graphene is a material like it's a single layer. So if you
Yeah.
put anything on top, you can change its properties. So that is the reality, and we can find out what is actually happening to graphene by putting any materials. For example, when you put TI on graphene structure, as I have shown here, so you can induce band structure change, a gap, you open a gap. And I think similar things can be happened when you put this wild semi-metals on top of
Metals.
graphene, because they are heavy elements. So one thing is that for the topological insulator, we find maybe it's due to some, there was some interface resistance. So which helps that when we inject the spin current, so spins are not going to topological insulator. We can identify that because we, in the topological insulator, actually we cannot change the Fermi level by applying gate because it's highly doped. And when we see change in these signals, so that means it's coming from the graphene only. But we have to, when we deposit directly, so maybe because both are metallic, graphene and tungsten telluride, so it depends on the interface structure. How?
So
But
this is okay.
yeah.
So,
one
but do you think? Yeah, but do you like you all your examples that you have shown are all like this selenides or tellurides? Even
Yes.
for, let's say, you have chosen a wild semi-metal, but it is a telluride. So what I'm asking is, do you think that interface will be better, or I mean, maybe all these problems can be sorted out, whatever little you have, by using, say, intermetallic Heusler, sorry, half Heusler materials, because they may match with the cobalt type. That there was a layer which you have used, no? That, or was it in the previous talk? Yeah, it was in the previous talk. But you have also, I mean, you can tell us about this. There was a layer of cobalt, niobium, aluminium. I saw somewhere.
That may be the okay. So that may be the some of the literature I took.
Yeah. Okay. So from the literature you took.
Yeah.
So, but do you have any comments on that? So, because to me it seems that interfaces will be better if you have two intermetallics, right?
Yes. So that is for sure. Yeah. Also, you know that the Heusler alloys you are working for a long time. They are also very challenging with surface and interfaces. So
That
if
is true.
one can control everything during growth, that can be very interesting.
It should be, right?
Of course, every material have interface challenges. So maybe one can do some experiments and see, because the topological insulator and ferromagnet, they don't have perfect interface.
Yeah,
So,
that's
but
what
people see larger signals. So
Yeah.
whatever maybe the interface that can be found out later. So people report results that, yeah, it's good for everything. But then one can try to understand and control. But one can do experiments just to see how this looks like. Maybe you don't need a perfect interface.
Oh, okay. So you are saying maybe the perfect interface is not a big requirement, as you can see from here. Actually, where it is, yeah, you can see that it is the important thing is how the current is interacting with the heterostructure.
Because how is we can take a practical system and try to make it and test. And the world is not perfect always. So we can go to perfection at one stage for basic research. But when it comes to industry, they look for whatever works for them. Yes.
Yeah, I agree. I agree. But your talk was very beautiful, and I am really happy with the way you have proceeded in explaining your results. It was really feeling, I mean, I really am very happy about it. So all the best, Saroj. You are doing very good work, and we hope to see more successes at your end. So,
yeah, thank you very much. I should have been here because this is winter time. I used to travel
I know.
most of the almost every year. So, but wish
That
you
is true.
a good time and see you sometime.
Same to you. Same to you. I mean, actually, Yes. Okay. Anyway, I'll speak to you separately on that.
Yeah.
We will discuss. Very good. Thank you.
Thank you. Thank you. Bye.
Okay,
Yeah.
thank
Bye-bye.
you.
Bye. So we have now the last talk of the session. Braj Bhushan Singh. He is a DST inspired faculty in the School of Physical Sciences, Nisar, Bhubaneswar. I believe that Braj Bhushan, you too have a degree from IIT Delhi, right?
Yes, ma'am.
We are looking forward to listening to you. Please go ahead.
Thank you, ma'am. And I would like to thank the organizer and for giving me the opportunity to giving this talk. So already my previous speakers already, I'm audible, right?
Yeah, you are. You are.
Yeah, thank you. So my previous speakers already talked about a lot on the topological insulator. So my work is also related to the topological insulator, and also I would like to talk a little bit on antiferromagnets. So I'm working on how to increase the efficiency of spin to charge conversion, but my way is different. So let's look at, so these are my funding sources, DST for my Inspire Fellowship and the research grant, and this DA, which is giving the opportunity to host me, and CPIPRA project, which is a Indo-French project for the Skybion project, and Newton Fund we are getting for PNR experiment, polarized neutron reflectivity. So let's look the chart, how the spintronics has growing. So in spintronics, in the first generation, then people were trying to study how you can detect the spin, inject the spin, and accumulate the spin, and how to try to move the spins depending on the scattering. And then later in second generation, we try to manipulate it by different ways. There is damping, tunneling, and spin resonance. So that create a lot of devices. Hard disk is the great boon for us. And there are other, so spin resolved RPS is also another technique which is very important for now in the quantum materials, and spin STM. So that is in the second generation. But in the third generation, still we are far behind to develop a robust spin transistor, spin oscillator. So that can be a possibility that they can be possible by different new kind of materials like quantum materials or quantum spintronics, terahertz spintronics that's covered by this antiferromagnetic materials. And you can study the spin interference like quantum interference you have studied in the in superconductor. So that's how it is, tree is growing. So let's look at the spin Hall effect and inverse spin Hall effect that most of the people already aware about that. So if you have a high spin orbit coupling non-magnetic material, then if you have a unpolarized current, then you have environment of spin orbit coupling, then they scattered depending on their spin direction, and then they create a spin current. So that is only possible to detect using optical methods like Kerr microscopy and other things. So we need a here inverse spin Hall effect where you create by some source, spin source like electromagnetic wave, microwave, and there are other sources where you give a spin current in this direction, and then you can have the accumulation on one edge due to spin accumulation on the one edge, and other is negligible. So you have the voltage plus and minus, then you can easily detect this one. So the important parameters which can be defined, that how you can define a parameter, how much the conversion efficiency from spin current to charge current. And that regions, they are different, intrinsic, that is spin orbit coupling, their extrinsic defects and other things, so that can create larger spin Hall angles. So that's the major issue, how you can measure the intrinsic spin Hall angle, which cannot be coming from the extrinsic regions. That's another challenge. So let's look at the challenges now we are facing. So for realization of the power efficient spintronic devices, we need a high spin Hall angle. So, but that spin Hall angle given by spin Hall conductivity, sigma sh, and your resistivity. These are the basically interdependent parameter how we have to look. So spin, if you have large spin Hall angle, according to this expression, it looks that you need then you can have a lower current density, which is the magnetization, and then for device, you need a larger diffusion length. But this is not so easy. If you look at this table, so this one is directly proportional to the spin Hall angle, and sorry. And this is resistivity, and this is spin Hall conductivity, and P is the power efficiency. So you look different materials people have tried, and if you see the platinum, so if you are growing platinum by two different resistivity, then you can have different spin Hall angle and the conductivity. But if you look this one, there is a problem that how can you enhance the spin Hall conductivity at the same time without compromising with the spin Hall angle. So can new materials can be a solution, or new engineering of the interfaces can be a solution? So I'm looking to this part, can new materials can be, so I'm focusing the two primary materials, that's the topological insulator, people have already talked about a lot, and the antiferromagnet. That can be for the solution or what are the challenges. But so in the topological insulator, as people have already talked about, you have a system which has two kind of conducting channels. One is the bulk conducting channel, and that's called insulating most of the, and then you have the surface which is surface states, that's the spin momentum locked. So if you see the two-dimensional band diagram, then you can see these are the surface crossing states which can be utilized to spin to charge conversion. So these are the important thing which can be utilized to create high spin to charge conversion without compromising other parameter like spin Hall conductivity. So here, well-established bismuth selenide, and this having 300 milli-electron volt band gap, so you can tune easily. So we took this one. So if you see, this is the layered structure of the bismuth selenide. So one quintuple layer is around approximately 1 nanometer. So here, the important thing in our work is that if you see, most of the people have tried molecular beam epitaxy, and there are few groups that Professor Young has also worked on that using sputtering, and there is so there are 2 or 3 reports. So here, so we are using a new method, that's electron beam preparation, which nobody has used. The preparation can help. So let us see how it will affect spin to charge conversion. So for that, we have deposited this structure. So cobalt, iron, boron is the ferromagnetic material, that's normally amorphous, and bismuth selenide 10 nanometer. So the structural characterization is very important before moving to your spin to charge conversion measurements. So for that, we perform a X-ray diffraction. So if you look, there are only one type of diffraction planes this is given. It looks like this is oriented film for the 30 nanometer. But however, this is not the case. When we are going further, that's HR10 image. This is silicon oxide. So if you look, this part look crystalline, but however, other parts are amorphous. So if you are going in on the nanoscale to look on the more deeper, then it is looking that it is not the highly oriented. But if you look, there is no other planes in the X-ray diffraction. So that's very important. So why is it important? How it will affect? Let's look the paper that people have published, that you can have the topologically protected surface on the amorphous system also. So it is already theoretically reported. So a lot of things need to be explored. So in our case, how is it affecting? Is it negatively decreasing the spin to charge conversion or not? Let's look at. So for that, we have performed a ferromagnetic resonance. So this is our simple setup. So this is coplanar waveguide, and we are keeping the sample spin flip chip manner, and we are applying in-plane magnetic field and RF field provided by RF generator. So up to 17 gigahertz we can provide. So this is typical spectra, FMR signal. And then by fitting, we can find out damping parameter and other anisotropy and perpendicular anisotropic parameters, which will tell is there any enhancement in the damping. Then it will be region from the other effects like interfaces, but more probably on spin pumping. So this is frequency versus resonance, that is, and delta S versus. By fitting this one, we can find out. So if you look the damping, this is for bilayer 0.039. However, for single layer, it was 0.0067. So quite high. But this cannot tell you that there is a spin pumping, because interface may be rough, and then also can enhance damping by different scattering mechanism. So only thing is if we can see the any inverse spin Hall effect or not. So for that we have performed a measurement of the spin Hall effect. So if you look this, this is ferromagnetic resonance, good resonance, and at that resonance, if you see this is a voltage measured, we have performed measurement, then it is about less than about 3 microvolt, and then we perform a fitting doing symmetric anti-symmetric components, so that we can see that because ferromagnetic material is involved and there are other effects which can also contribute in the voltage, like anisotropic magnetoresistance. So normally if we in crude way we understand the symmetric component normally contain only spin pumping voltage. However, if you look our structure, this one, so there is a tantalum oxide, so there is a possibility the signal may also come from this one. So for that we have perform a single without any bismuth selenide, and if you look there is a signal which is not there like here. So it means the most of the signal is due to bismuth selenide, but this analysis is not so simple because we have to eliminate other effects. So how we can do, first we need to understand what kind of effects can contribute. So there is a anisotropic magnetoresistance, the origin is spin orbit coupling, and it is depending on the how your current direction and magnetization are in the sample. This is up to few percent. Similarly, planar Hall effect, anomalous Hall effect, and giant magnetoresistance. However, this is only possible if you have some multilayer structure and ratio is very, very high. In TMR, you need a either granular structure, which is having insulator, and then you have insulating tunneling behavior, and the SMR, which is also negligible. But question is, how will you remove them, or how will you disentangle with them? So let's look at, so this is a voltage versus field. So if you have FMR resonance, then you will have this kind of spectra. When we fit it with the symmetric, anti-symmetric, then you can distinguish with the two effects. But however, if you have a symmetric component, it also include AMR and AHE and other heating effect. Okay, asymmetric you already exclude by considering this one. But heating effect you can consider by just reversing the magnetization direction. But that's not always the case, because heating effect is also from the spin Seebeck effect and other effect, which is also following the similar angle dependent behavior like the inverse spin Hall effect. So in that way, we need to look at how they are behaving with the in-plane angle. So this is in-plane angle. If you have in-plane excitation, then if you look, so all the signals, this one cos 3 is basically your spin pumping voltage. So all the behavior is totally different. So it looks like that if you do the angle dependent measurement, you can exclude these effects. Therefore, we have performed a angle dependent measurement. This is for outer plane. This is not our case, but here also you can exclude these effects. So for that, we have performed angle dependent measurements. So if you look symmetric component and asymmetric component versus angle, and then we perform a fitting with that. So we included all the component, spin pumping, AHE, symmetric, and then we exclude other effects, and then we purely find out what is the spin pumping voltage. So in that case, this analysis is very, very crucial to avoid any kind of artificial measurement in the spin to charge conversion efficiency. Further, we need to see that really there's a spin Hall, inverse spin Hall effect is the cause for the spin to charge conversion in our case, or there are other mechanism. So for that, we have performed a thickness dependence. So we deposited 3, 5, 7, 10, 20 nanometer bismuth selenide samples, and we perform the interface analysis, so that looks smooth. So here is the 0.8 nanometer to 1.2 nanometer is the interface roughness of the cobalt iron boron or bismuth selenide. And then similar measurement of inverse spin Hall effect analysis would have been performed. If you look this the tables, all the component has been excluded. So this is spin pumping voltage, where we can see there is no specific trend up to this one is increasing, and bismuth selenide 10 nanometer sample is increasing. But however, there is a huge contribution from the AMR perpendicular. Perpendicular means this is decided by how your magnetic field is applied. Then we have performed Hall effect to measure the carrier current density, and then we calculated the Fermi velocity, and then we also performed relaxation time measurements to be how we can. But this I will discuss later. So this is the data in which we can see how is this. So this is damping versus thickness of the bismuth selenide. So normally, if you see simple ferromagnetic material with the heavy metal like tungsten, tantalum, platinum, then you will have a saturation of the damping with the thickness. But here there is no specific trend. And here is the spin mixing conductance, which define the spin transport across your ferromagnetic layer and your non-magnetic, basically here topological insulator. There is no specific trend. So it looks like that is not following the thumb rule of the spin diffusion theory. Then we have further performed the spin pumping voltage versus thickness, and then this will give you the spin diffusion length, which is 2.3 nanometer, and 1 quintuple layer is about 0.95 nanometer. And these people have already reported using RPES that your surface states survive up to 2 to 3 nanometer only. So it looks that it is not from the spin diffusion theory. Further, we have calculated the spin Hall angle. Look, here is also the no specific trend, because once thickness of a non-magnetic layer you increase, then your spin Hall angle should saturate. So it means there are some other mechanism which is following. So that is the one possibility that is called Raswa-Edelstein effect. So that is a possibility that it is possible. So we need to look at the what is the Raswas. So if you see, this is TI states. So if you have a cone, different spin configuration, and then you have a Raswa surface state, that's normally happen in the two-dimensional gas case at different K. So splitting. But when you combine these two, so it's become like this. So you have the in the three-dimension way. But if you look the two-dimension way this way, so you have a spin polarization in the K space when you have a TI, and then you have Raswa surface states at different K value. And then you combine this one, then they try to accumulate at the surfaces to make it, that's called spin accumulation. So different polarization. So, but if you come to the, when you say that what will be the your current density in the charge or in the spin. So in this direction will be your spin current density when you are flowing, because the spin direction is there. And then your current density will be along the x directions. So if you have TI surface, then it will be directly proportional to your Fermi velocity, and then relaxation time of the surface state. That's basically spin polarization of the surface states, and then the current density. So basically, and if you have a Raswa, then this will be, there is another parameter that's called Raswa parameter that is defined by the how your inversion symmetry strength is there. Then you combine, so there is a
Raj, try to finish up.
Yeah, so yeah. So in that way, so we calculated this one, and then we found that our spin to charge conversion is highest that we observe. So this is sputtered one that Nanolighter published, and this one is MB grown. So if you look, so this work recently published. So let's look at the antiferromagnet. We know when he was giving a novel lecture, he was saying it is useless, but it's interesting. But in here we can see So we are using Mn3 gallium as a non-collinear antiferromagnet. So it exists in 3 states: hexagonal and cubic. So and tetragonal. Cubic and hexagonal are antiferromagnetic, but hexagonal one is stable phase. So here we perform this one structure by depositing sputtering. Tungsten is beta phase because it can have a good mismatch, good lattice match with the Mn3 gallium. And then we perform spin mixing conductance, and then again we perform ISSE measurements. So if you look, this is our sample structure, and this is giving you nicely when changing the field direction. Then their signal strength is similar in that way with the black curve in here, and this blue one is the FMR signal. Then by disentangling other effect by performing this angle dependent, then we have calculated spin Hall angle. So we can see here the spin Hall angle is 0.31, which is comparable to the other non-collinear antiferromagnetic like iridium Mn3. And the spin Hall conductivity is comparable to the platinum. So it looks that Mn3 gallium can be a possible material for the high spin to charge conversion without compromising or spin Hall conductivity. So here I summarize. So we have successfully grown high quality bismuth selenide by different methods as people have not utilized. That's called electron beam evaporation. And then we have observed high spin to charge conversion, which is due to inverse transverse Edelstein effect. And then we have also performed a inverse spin Hall effect on Mn3 gallium. So Mn3 gallium, we are the first, we studied inverse spin Hall effect on Mn3 gallium. People have investigated on IRMN3 and Mn3SN, but we have performed here. So, and here is our collaborator. So I would like to thank to Professor Vankar, where he is my host there, and Professor Varman and Professor Pati for the PM, and where we are getting the bismuth selenide bulk samples. So here, and this is group my. Thank you all for kind attention.
Okay, thank you.
Yeah.
Our chair, madam, are you around? Well, maybe I can start with a question. So we are, of course, running a bit late. Just one question I was wondering, this Mn3 gallium, how do you know that it's actually in the non-collinear antiferromagnetic state? Is there any experimental evidence that?
Actually, it is difficult, but we have performed an anomalous Hall effect. There was a signal, very good signal on the anomalous Hall effect. So yeah, in that way, we can say it is a non-collinear. However, anomalous Hall effect is not always a, I mean, always correct method. There are other effects which can also give you an anomalous Hall effect. Yeah.
Okay, is there any other question from the participants who are on the right now? I don't see any questions on the chat. Yes, please.
Yeah, this is Anjan Barman. Nice talk.
Yes.
Yeah. Thank you, sir.
Yeah, it's nice talk. I just have a very quick question that, I mean, people have been measuring spin pumping or spin Hall effect by using, the inverse spin Hall effect.
Yep.
When they're using FMR techniques, which is good, but how about using the modulation of damping? Because that will disentangle many of these effects intrinsically. So you understand the point, right? So we have published a paper sometime back where we used both inverse spin Hall effect and damping modulation, and we found the damping modulation is a better method for it.
Actually, in damping, interface effect is crucial, right? So, I mean, yes, interface effect, if you can exclude by thickness dependent of ferromagnetic material, then yeah, it's possible. But inverse spin Hall effect, I mean, I will not say differ with you, but in my opinion, my experience says that inverse spin Hall effect can give you the better, I mean, signal. For example, I mean, our experience is saying we are depositing some layer cobalt, iron, boron, and tantalum oxide. but damping was enhancing. However, in ISHE, there was no signal at all. So, so it looks like there is no spin to charge
What you mean
converter.
is that modulation of damping, not just damp. The
Modulation of damping. The modulation of
damping
damping
may be
by spin
enhanced,
orbit
but
torques.
how much it changes with the current, that is a direct measurement of.
Oh, no, actually, sir, in FMR for that, in our system, it is quite difficult. I tried actually. I think I discussed with you while I was in meeting with you. It is difficult
Right.
because when you are flowing a current in a larger sample, right? So you need to flow larger current if you want to modulate with that. And people have shown in the MN3SN with the modulation, if you see this Professor Axel Hoffman paper, but I could not get it. I tried because our sample size cannot go below 1 mm. If you are going below 1 mm, then FMR signal is very noisy. So for that, you need a
Okay.
good signal. If you see this endo paper that you are talking about, so in that paper
Yeah.
also they have used a 100 micrometer wide. So if you have a device and you can sign with the electromagnetic, then it is possible. But our sample cannot go 1 mm. So you need to say 1,000 times more current you have to flow, and then signal and your sample can
Yeah,
work.
yeah. So you have to increase the current density. Yeah.
Yeah.
Right.
So yeah. So
Okay. Thank you.
yeah.
Okay, thank you, Braj. I think we'll have to end this session because the next session is going to start now. Sorry for the delay that happened due to some technical issues.
Okay.
But just 3 minutes, we're going to start our next session on spintronics.
Okay, sir. Okay. Thank you.
Uh, Hello. I think Madam left. I just wanted to thank HOD for chairing this session. And now we'll start our next session. But I think she has left, it seems. So let me see our next chair, whether they have joined or not.
hope that I can see my screen.
Subankar? Okay. So, welcome everyone. Hello, welcome everyone. I am P.K. Muduli and I will welcome to this session. And this session will be chaired by Subankar Vedanta. Subankar, can you introduce our first speaker?
Thanks.
Hello, welcome. Some noise.
Sorry. So should I start, Professor Muduli?
Yes, yes, please. Please.
Can you hear me?
Yes.
Okay, there is some noise in the background. I don't know.
But we are hearing. Please introduce our first speaker and so that you can start.
Okay, so good afternoon, everybody.
Yes, yes, please. Please.
Can you hear me?
Oh, it's some really noise.
Everybody? There is some noise in the background. Yep. Today
But
we
we are
have.
hearing. Please introduce our first speaker and so that you can start.
Okay, so good afternoon, everybody. Just give me 1 second. I'm sorry, I was in both. I think I was the problem maker. I'm sorry. Okay, sorry. Finally, good afternoon. I'm very pleased to introduce Professor Johan in the field of spintronics. Professor Johan Ackerman has a PhD in material physics from KTH, Royal Institute of Technology. Then he was a postdoc at University of California, San Diego, and he joined Motorola for a few years for the MRAM reliability. In 2005, he returned to Sweden to start his own research group at the Department of Materials and Nanophysics at KTH, Royal Institute of Technology. In 2008, he was appointed as full professor to the physics department at University of Gothenburg, while remaining a guest professor at KTH. He is also the founder and CEO of two startup companies that are NanoOsk, that is commercializing spintronic devices, and NanoOsk Instruments AB, designing and manufacturing spectrometers for ferromagnetic resonance measurements at cryogenic and room temperatures. His main projects are related to spin torque and spin Hall nano oscillators with particular focus on mutual synchronization, magnetodynamical solitons, and oscillator networks for neuromorphic computing. His research has been recognized through high-impact journal publications, having more papers, including high-impact journals like Science, Nature, and so on. And I'm excited and I'm welcoming Johan for your lecture. Thank you.
Johan, can you start sharing your screen? Well, he's okay.
Yes, thank you. Do you hear me?
Yes, yes, we can hear you now.
Okay. So let's see if I can get this to work. Thank you so much for your kind introduction. And I'm hoping this is showing now, is it?
Yes, yes, we can see it. Yeah.
for the kind introduction. I want to thank both the organizers and for the kind invitation to speak here, and also the chair and the organizers for their hospitality through the years. So I was in India 2 years ago, I was in India 1 year ago, and I sure hope I could have been there this time around as well. But unfortunately, that's not the case. But we'll do with this. So thank you so much. I will be talking about voltage control spin-hole nano oscillators, but I will also talk about synchronization of oscillators, because that's this is the combined topic. And I want to highlight or acknowledge our co-workers. A lot of the work that you will see today has been the thesis work of Mohammad Zahidinejad. He's now a postdoc in the group. You will see a postdoc and now research engineer Ahmad Awad, and graduate student Shreyas Muralidhar. And then we have theoretical support from Roman Kimin and Mikola Dvornik. Part of the measurements towards the end are done by Himanshu Fulara, and a lot of processing help to make these devices work as well has been given by Afshin Hushai. I also want to highlight our collaboration with Hidiono's group, now led by Shunsuke Fukami, where we have some stacks. So the second part of the talk will deal with results that we have together with them. The topic that we use, or the phenomenon that we use, is called synchronization. And this goes back to actually 350 years or more than that, almost 400 years. By the inventor Huygens, scientist and inventor, engineer, everything. He was the inventor of the pendulum clock. And what you can see to the left is him, and then you can see one of his patent drawings for a pendulum clock. And what you see to the right is his lab book, where he describes one of his experiments where he puts two pendulum clocks on a wooden beam on top of two chairs. And then he could observe that these pendulum clocks actually the pendula start to move together. They start to move in some odd kind of sympathy, as he described it in a letter to the Royal Society. And this is a very general phenomenon, that if you have oscillators that are self-oscillating, such as pendulum clocks, but also the devices that we work with, sometimes called auto-oscillators, they can adjust their phase and their frequency to some extent to interact with other oscillators. So these are two interacting pendulum clocks, and what I will show are interacting spin-Hall nano oscillators. To illustrate this, I've taken a movie here from the internet, where you can see synchronization of metronomes. So hopefully this is now visible. These are independent auto oscillators, 5 of them. And what this person is doing now is he puts them on a wooden beam, and he allows the wooden beam to move. So now the oscillators have some coupling to themselves, between each other. And it doesn't take very long until they decide to move in unison. So even though they have slightly different frequencies, the added interaction will make the frequencies turn into a single one, and also they will turn into phase. That is the phenomenon of synchronization. And what you saw here was the transient behavior, the synchronization time needed to get them to synchronize. Let's see if I can stop that. In the case of spintronic oscillators, synchronization was shown quite some time ago by 2 groups independently in 2005. So what you see on the drawing is a cartoon of 2 nanocontact spin torque oscillators. In the top, they have individual contacts, so the NIST group could operate these 2 oscillators independently of each other, and then through the spin wave interaction in the green layer here, they started to interact, and they could observe observation. In the graph down here, from the from the Motorola group at the time. You can see two such oscillators having frequencies in the 9 gigahertz range, roughly. They're somewhat faint, and then they start to interact and they merge together, and the power goes up. And although you can't really see it here, the quality of the signal, the line width improves. So that's how you can see mutual synchronization also in spintronic oscillators. But the oscillators I will talk about today are spin Hall oscillators. And we use the spin Hall effect. It's been talked about before in this session. We use relatively standard materials such as platinum and tungsten. What happens in those materials is if you pass a longitudinal current through that material, there are asymmetric scattering processes that are spin dependent, and they will set up a spin accumulation transverse to the longitudinal current direction. And in that way, you get now a spin imbalance building up inside this layer, and that spin imbalance, if you put an adjacent ferromagnetic layer on top of this layer, turns into a spin current that can be deposited into the ferromagnetic layer. That in turn results in a spin transfer torque on the ferromagnetic layer. So you can use that to switch the magnetization, or you can use it to provide anti-damping, which is what we do in this case, such that the magnetization itself in the ferromagnetic layer starts to auto-oscillate basically on its ferromagnetic resonance. Spin Hall nano-oscillators come in many different shapes and forms. The first devices were pillar devices from the Cornell group. Another type of device was a nano-gap device or needle device, depending on how you want to view it, where you have two gold contacts tapered or shaped into needles on top of a disc, and they focus the current such that you get high enough current density in a single spot. And both these systems can then generate auto oscillations. They involve quite a bit of fabrication, though. So when Demidov, Rushtin, and Demokritov in 2014 showed that you can do a simpler device called a nanoconstriction spin Hall nano oscillators, this is where we decided to also join this research topic, because the fabrication is so easy that it should be possible to do a whole range of different types of devices. All you need now is typically a bilayer, and then you make a single processing step where you make a nanoconstriction in that bilayer. But you can actually use single layers. Sometimes you can use multi-layers. But the key point here is that the processing is very simple. And you have optical access to the active region. You can also have electrical access to the optical region, and that's what we use. I will show in the second part of the talk, where we can put an electrical gate on that region. So with this first work in plane fields, we reproduced that work, and then we looked at what happens when you put these devices in out of plane fields. And this is simulation work done by Mikola Dvornik in 2018. What you see here, the red is high-intensity spin waves. Everything you see here is micromagnetic simulation. Everything that's blue is a nanoconstriction. The white is the etched away material. When you see something red or green or yellow, that is a higher spin wave intensity. But everything is still linear. These are the spin wave modes that exist in the nanoconstriction even before auto oscillation. And then on the axis, you have the strength of the applied field going from 0.6 Tesla to 1 Tesla, and the angle of the applied field going from 70 degrees to essentially perpendicular to the film plane. And during what happens in the material or in the magnetic layer when you do this is that the magnetization is pulled out of plane. So if you use permalloy, you have a saturation of roughly 1 Tesla. So if you put the 1 Tesla field at 85 degrees angle, you're essentially saturating the magnetization along 85 degrees. But if you put 0.6 at 70 degrees, the permalloy layer is more or less still in plane. It's more towards the plane than out of plane. So this dramatically changes the type of spin wave mode you have. So for example, when it's more in plane, you have strong localization to the edges. The more out of plane you go, you get to a more extended mode. The spin wave intensity moves away from the edge into the interior of the constriction, and it also after that expands out of the constriction. And it was our hope that this more extended mode would be beneficial for making multiple constrictions interact. So what you see to the right is a calculation of the effective field when you increase this perpendicular field. This is essentially the field landscape that first has a minimum at the edges, and that's why the spin wave mode resides there. But as you increase the field, you get more of a minimum inside the constriction, and that's why the spin wave mode moves in there. Now, it's interesting to pick one such condition. Here we pick 0.8 and 80 degrees because that's close to what we will use in the experiment later on. And this is just before auto oscillation starts. But once we increase the current beyond that, we get further expansion of the mode. So the mode has its center close to the edge. When we increase the current, the mode center, or the strongest auto oscillations, move inwards into the interior of the constriction, and then it expands. So this is in addition to what the field does. We can also change the mode profile with the drive current. And this mode expansion should then be beneficial for mutual synchronization, because independent constrictions will now start to feel the auto oscillations in the other constriction, because it expands more they expand toward each other. So first we confirm that this frequency dependence that we predicted actually holds true. So this is a 120 nanometer constriction in an out of plane field measured as a function of current. And as you can see, it has this monotonic frequency versus current dependence. First, it starts out being localized at the edge, then it starts to detach, and it expands away. And as it expands, the nonlinearity becomes positive, and the frequency goes up with current instead. So this behavior seems to hold true. The micromagnetic simulations are confirmed, and then we can start the more interesting measurements, and we can make devices that are now double constrictions with different separations. So here first I show 300 nanometers, and you can see that the two signals here start out being completely independent. This is while they're still localized to the edges. As they turn around, the modes expand, and then they start to interact. So you can see the interaction makes them blurry. So they are definitely perturbing each other. And then after some time, they decide to just be friends and have a compromise and start to auto-oscillate on the same frequency, which is roughly in between the two original frequencies. So they both made compromise, and they both now auto-oscillate on the same frequency with a much, much higher power. This can be extended to long chains of oscillators. I should also say this can be extended up to a micron of distance, even up to 4 microns if we taper the bridge. So for example, this bridge here is rather wide, but if we make it more narrow, we can manage oscillators to talk to each other up to 4 microns apart, because the modes expand into the bridge, and finally they interact with each other. What you see here are 9 constrictions, and electrically you can see the 9 constrictions maybe not all of them, but many of them show up here faintly in the electrical measurement. And then as they start to interact, the power of that single frequency grows, and finally also this last loner here decides to join, and the power is now some 50-60 times higher than the single power, and ideally the power should be squared the number of oscillators. And we have 9 oscillators, so should be 9 squared equal 81 times higher. We get some 57-60 times higher. That's relatively close, so we believe that all of them are auto-oscillating relatively well in phase. We can do something more. We can do spin wave microscopy, or using a tool or a technique called Brilliant light scattering microscopy. And that's what's shown in this middle figure. You can see the outline of the constrictions. And inside you again see the spin wave intensity, but this time it's not simulated. This time it's measured directly with a Brilliant light scattering microscope, with the BLS microscope. You can see that all the oscillators are energized, and they have some variation in power, and that comes from the variation from grains, for example, or lithography variations and things like that. But they're all auto-oscillating. And if you look at the frequency content, you can see that there is no variation in frequency content. They all auto-oscillate on the same frequency. And that's at a drive current when they are mutually synchronized to a large extent. Now, we have gone in this direction and continue to make longer chains. We have made 21 mutually synchronized spin Hall oscillators. We believe we even have 50, but the results have not been analyzed in detail. And this was part of Mohammed Saidinejad's thesis work, and we haven't really published this, but we think it's possible to make very, very long chains and synchronize them mutually. The reason for why we didn't continue this is, well, lack of time and interest in another possibility, which is mutual synchronization in 2 dimensions. So as the final part of his thesis work, Mohammed designed 2-dimensional arrays of spin Hall nano-oscillators. So what you see here is an SEM picture of 4 nanoconstrictions. And now the bridges are relatively narrow, to try to increase the interaction. But you have now 4 constrictions. We call this a 2x2 array. And we will, in this experiment, vary the width of the oscillators and the separation of the oscillators. So starting out with the 2x2 arrays, we indeed see that we have mutual synchronization also in 2 dimensions. So to the left is the smallest arrays, 50 nanometer wide and very closely located, so 100 nanometer separation. There you can almost only see the synchronized state, and they synchronize very early. In the as you increase the size, and in particular increase the separation, let's say we go to the biggest one where it's 300 nanometers apart, then you can clearly see the signals even after the modes have expanded. So they synchronize later on. So this behavior is consistent with the idea that separation will reduce the interaction and mode expansion will increase the interaction. We can then go to larger arrays, 4x4, so we have 16 oscillators. And in that case, the smallest still synchronize, but the biggest now show 4 distinct signals. The power in these signals are definitely higher than when the oscillators start out. So we believe that the oscillators here are partially synchronized, that they synchronize in chains. And what we see here are then 4 oscillators in unison, 4 oscillators, the other chain in unison, and so on. If you go to the smaller ones, we can also see these chains, but at some higher current, the mode expansion and the separation is smaller now than the mode expansion. So the chains themselves mutually synchronize. And that can be seen both as a higher power and a better line width. And if we go to 140 nanometers and 100 nanometers, they all synchronize again very early. Well, to prove that this is indeed the picture, what is actually happening, we can use the Brilliant light scattering microscope again. So we identify 4 signals here, 2 lower frequency and 2 higher frequency. And then we take line scans of the spin wave intensity. So the BLS microscope will take a line scan across all 4 chains, so along one row. And then we can first see that the frequency is not constant along that direction. And we can identify the frequencies as being the 2 lower frequencies, 1 and 2, are at the edges, and the higher frequencies, 3 and 4, are internal. If we do the same scan along a column or along a chain, we see first that the frequency is constant in that direction, and that frequency corresponds to the highest frequency, 4 here. So there are 2 conclusions one can draw. One is that the chains do indeed mutually synchronize before chains synchronize between themselves. And this is reasonable because the mode expansion happens along the direction of the chain and not towards a neighboring chain. So this is quite reasonable to expect. The second thing is that it seems like the interior and the edges behave differently. So although we haven't done that yet, one should probably modify the edge design a little bit so that the frequencies of the edges are closer to those of the interior. But that's for future work. Now, understanding how arrays synchronize, we wanted to see how far we can go. So here are 6 different arrangements. We go from 2 by 2 up to 5 and 6 and 8 and 10 by 10. So we have at most 100 oscillators. And if we look at the 5 by 5, we have a similar behavior as for the 4 by 4. There are chains synchronized here at 300 nanometer separation. The chains don't synchronize between themselves at that separation, but at 200 nanometers they do. If we do 6 by 6, then it's not possible to synchronize everything in the 6 by 6 case, but we still are quite certain that they do synchronize here for the smallest separation, 100 nanometer. If you go to 8 by 8, they also fully synchronize at the shortest distance. And if we then finally go to 10 by 10, we don't think we have complete synchronization in this case. And the way we can determine that is that the total power, the peak power, is very good. In these cases, it's well above 20, whereas here it's down at 12, so we don't think we have all the oscillators in unison. And speaking of power and the quality of the signal, if we look at the behavior of the quality in terms of the line width versus the number of spin Hall nano oscillators, we can see that the quality improves dramatically. So in the 4x4 array, and with the smallest oscillators and the shortest separation, we have 1 megahertz of line width. If we then go to 4x4, 5x5, 6x6, and 8x8, we see a 1/n dependence of the line width, and we get down to line widths as good as 60 kilohertz in this case. And at the operating frequency of 10 gigahertz, this corresponds to a quality factor of 170,000, which is 10 times higher than anything before. So mutual synchronization definitely improves the behavior here. There's a different trend also. It is that the larger you make the constriction, the lower the line width. And that we have shown in single oscillators as well, that the larger spin wave mode has a higher quality because thermal energy is not able to disturb it as much. And this just shows that this quality factor here is about an order of magnitude of the best value given by NIST in 2004. Of course, we use an isotropic magnetic resistance in these devices, so the power is still very low. We definitely have to move this star all the way up here using magnetic tunnel junctions so we can get both the good line width and the high power. Now I want to change to a slightly different topic, just very briefly. You probably all know about the work done by Julie Grolier and co-workers where they use synchronized oscillators to do neuromorphic computing. Very briefly, they have 4 oscillators that are in a chain. They have some interactions between these oscillators. They inject 2 additional microwave signals, which are the inputs here. And then they look at the mutual synchronization state of these oscillators as a function of the injected signal. And more than mutual synchronization, it's rather the injection locked state, I should call it, because it's not so much about mutual synchronization here as it is about locking to the external microwave signal. So as an example, the light blue color is the response of these 4 oscillators when there is no injected signal. So then you can see the 4 individual oscillators. Then they add a frequency A and a frequency B, and frequency B injection locks the 4th oscillator, whereas frequency A doesn't do anything. So this is one state. You have 2 frequencies. The resulting injection locked state is that oscillator 4 locked to injected signal B. And now you can build up a 2-dimensional map as a function of frequency A and frequency B. And you can look at the different injected locked states here, and that's what's listed here, going all the way from oscillator being injection locked to signal A or frequency A, to oscillator 4 being injection locked to frequency A, and oscillator 3 being injection locked to frequency B. And they then show that they can use this mapping as if they now interpret the frequencies they inject as the frequency content of spoken vowels, they can map, and they can match and detect vowels from the synchronized or injection locked state. So we wanted to check if we can reproduce this, and we're going to use the 4 chains that I showed before. So these will now act as 4 individual oscillators that can interact with each other. And then we will add 2 microwave currents, frequency A and frequency B, directly to this system and not through an external antenna. Our systems are quite similar, but there are important differences. A minor difference is that we have nearest neighbor interaction, whereas they have global all-to-all interaction. They have a shared microwave current that goes through all the oscillators. That's similar to the movie I showed, where all the oscillators share a beam, a wooden beam, so all oscillators feel all oscillators in that case. What we have is a primarily nearest neighbor interaction, but it will not make any important difference. Some other differences are size, for example, and simplicity. So the processing of this array is relatively simple. It's a lithography step in a bilayer. Here you need to make 4 MTJs. You may need to have microwave components that connect them to each other, and it's all a macroscopic arrangement, whereas here it's completely microscopic. Everything here is well below a micron in size. And there's no additional antennas. So there are some benefits of doing this. And we, as I described to you before, we have these 4 signals. We can injection lock them with an external signal. And at the end of the day, we can reproduce that kind of synchronization map, which is the core of the neuromorphic computation. I will then now jump to my second topic, and that's voltage control. And the first voltage control spin-Hall oscillator was shown by Urashtin's group at Emory State University, I believe, also at the time. And they showed how they could backgate a permalloy layer with relatively high, well, I shouldn't say that, but with some 5 volt in this case, and they could see a change of the frequency and a tiny change of the threshold current, but almost none. What changed was definitely the frequency, so they got some reasonable tunability from a voltage on top of the device. And we wanted to try this on our constrictions instead. And we changed the type of material here from nickel iron to cobalt iron boron, because it is well known that the anisotropy of cobalt iron boron, the perpendicular anisotropy of cobalt iron boron, can be tuned with voltage, so-called voltage controlled magnetic anisotropy. So our goal is to change and control the perpendicular magnetic anisotropy of the cobalt iron boron layer using a voltage gate on top of the constriction. And that's what you see in an SEM picture here. You have the constriction, and we have added a voltage gate on top of some insulating layers here. The result is indeed tunability. So what you see in the first plot here is the frequency versus current for this device when we apply 5 different voltages. So no voltage, and then both negative and positive voltages. And the frequency does change about some plus minus, I believe, total range maybe 80 megahertz or so. So here you can see that it's plus minus 20, 25 megahertz as we go from -2 to +2 volts. So that's a sizable change of the frequency of the device. But what is more interesting is that the threshold current changes a lot. So we can extract the threshold current by analyzing the power versus current, and then extract when the auto oscillations basically start. This is the inverse of the power. It shows an inverse behavior, and then it becomes, when it becomes auto oscillating, it changes behavior, and you can extract that point. And if you plot that point versus voltage now, you get quite a change in the threshold current. And this can be useful because then in an array, you can start one oscillator in a chain, or you can stop one oscillator in a chain just by changing the voltage directly on that device. Himanshu Fulara and Roman Kimin, they sat down and thought some more about this. So Himanshu made STFMR measurements, and he found that what is driving this change in the threshold current is a giant change in the damping. So there is this tiny change in the M effective, and that is the change of the PMA, essentially. But it leads to a giant change in the damping. So a small percentage change of the PMA leads to a 40% change in the damping. And that's a radical and dramatic amplification of the impact of the anisotropy. And the reason for this is the geometry of the spin Hall nano oscillator. So the spin wave mode in a PMA device in cobalt iron boron is already quite extended, and you can actually get propagating spin waves. I haven't talked about it here, but if you change the field angle in a cobalt iron boron oscillator with substantial PMA, you will actually get propagating spin waves. So you can go all the way from edge localized to the constriction to propagating in such a device. And in that in-between landscape between localized and propagating spin waves, there's a dramatic change in how much damping the spin wave mode feels. Because when it's localized, there are no external spin wave modes that the magnons can dissipate into. So there is no load, there is no dissipation on the oscillator more than its own dissipation in its region. But when you have propagating spin waves, you now have spin wave radiation. The damping of that mode is much, much higher. And if we tune from one mode to the other with a tiny change to the PMA, we can tune the damping tremendously. So it's not a damping of the material, it's the total dissipation on the spin wave mode. So some sort of effective damping, if you like. But if you interpret this as damping in an STFMR measurement, this is what you get. So the blue data curves are the blue data points here are the measured damping values, so extracted values from these STFMR data points or curves, and the red ones are simulated using micromagnetic simulations. And you can see with reasonable material parameters, we can reproduce the voltage-controlled damping very, very well. Now, how can we use this to our benefit? Well, I will soon end my talk here, and I will just show you some preliminary data that we put on arXiv in September, and which is currently under review. Here is a device made by Mohammed Saidinejad where he has a chain of 4 oscillators, and then he puts 2 voltage gates on them. In this case, although we have done many, many different types, he puts the gates slightly off the nanoconstriction. And that is to control, he wants to control the coupling between the oscillators. He doesn't necessarily want to change the frequency of one oscillator, but he wants to change the damping in the bridge connecting 2 oscillators. And when he does that, he can indeed reach voltage-controlled mutual synchronization. So these are 4 oscillators that at low voltage or high negative voltage are mutually synchronized into pairs. So F1 and F2 are this pair of oscillators synchronized and this pair of oscillators synchronized because the voltage is controlling them differently. And then as you tune, sorry, F1 is above here and F2 is below probably. And then as you change the voltage, you go to 0, they start to interact. Then if you go to positive voltages, the interaction increases such that you get full mutual synchronization of all the 4. So the power goes up tremendously and you reach the state of a complete mutual synchronization. And I think with that, my time is up. And I hope I have showed you some interesting new results on how we can use voltage control to gate spin Hall oscillators and control their threshold currents, their mutual synchronization with each other, and potentially we can now put this into much larger arrays so we can do more advanced neuromorphic computing. So with that, I thank you all for your attention.
Thank you very much, Juan, for this wonderful lecture summarizing many interesting results. So it is open for any questions from the audience. I do not see any question turn up. Do you see any?
No, it might appear in the chat directly to
Until
Juan.
it comes, I like to ask one question, the simple one. So in the middle of the lecture, by 5, 6 by 6, and so on. So I think you showed for the 6 by 6 or some reason you did not see these oscillations in a coherent way. So was there a particular reason that this number of arrays, the matrix actually matters?
So in the 6 by 6 case, in the smallest arrays, they do show complete synchronization here, and then they do break up. Well, one could have hoped that maybe they would synchronize here, but they didn't. So I have no particular good answer for that. But they didn't behave different in any other way, I would say. The mechanisms that are at play here are something that we haven't that we should more. But I think it's a statistical phenomenon that if you have 2 oscillators and they mutually synchronize, that's all they have to do. They have to compromise and find one frequency. The fact that the difference in frequency comes from imperfections, lithography or material. If we now make 100 oscillators, we're going to get much bigger differences from the worst oscillators in that array. So the lowest frequency and the highest frequency among 100 oscillators would just be more farther apart. And not only that, they are not directly interacting. They're interacting through other oscillators. So there's nearest neighbor interaction. And there are statistical arguments that if you have a ferromagnetic chain, you will not get complete order in one chain if you only have nearest neighbor interaction. And you know, it's a similar argument here, that if you have nearest neighbor interaction, it would be statistically harder to synchronize larger arrays. And I think that's what the mechanism is. We haven't worked it out, but we should in the future.
Okay. Maybe I can ask one more question. If you go the slide before, where you showed the device structure, so there was this W with maybe a few more slides. The width of the device. Yeah, okay, this is the width. So you have actually taken different width and the P, but there was other device which were like this wavy like thing, and you have repeated like many. That was.
Are you thinking about this device here?
Yeah, exactly.
Okay, so these are longer chains, yes.
Longer chains, yeah. So the width of this like triangle, okay, this amplitude of the triangle, how does it matter actually? If you make it smaller or longer, then how does it affect the final behavior?
Yeah, there are probably different ways it affects it, and there are other things you can vary. For example, that angle is 22 degrees for no particular reason.
Okay.
If you would change it to 45, you would probably change the spin wave mode slightly. But more importantly, when it's 22 and when it's wide like that, then you are effectively spreading out the current quite a bit. So you get well isolated oscillators. If we wanted to improve synchronization, it would be smarter to make that bridge more narrow, because then you get a higher current density also in the bridge. It doesn't spread out as much, and current density equals anti-damping. So even though you are not above threshold for auto oscillation, you are now helping the mode to expand just from anti-damping. So although this device looks good when it has wide pointy bridges like that, it would be smarter to make the variation smaller, so the bridge more narrow. And that's what is essentially done in these arrays. We could have made them more pointy, of course, but that would have, we think it's beneficial to have the current density also relatively high in the bridges themselves.
Okay, thank you. So I do not see any more questions.
So Bankar, there is a question from Professor Tamalika Banerjee. Maybe you can ask directly.
Well, I do not see. Please read that. Somehow I am not able to see.
She raised the hand.
Okay. So, Tamalika, please go ahead.
Well, maybe not.
No, she raised hand, but how do I allow her to speak? Can you do that?
No, she can directly do it by unmuting, but I think she's muted. That's why. But I had actually one question. Maybe I can ask why. That in the last part that you showed, it seems that at 0 voltage you already synchronize, and when you change the polarity of voltage, you desynchronize in one polarity, and then
yes,
it looks like at 0 it's already synchronized.
It's almost already synchronized, and the mechanism here is if we put -2 volt on them, we change their frequencies, so they definitely desynchronize. If we put positive voltage on them, they are we're making them become closer. So the intrinsic frequencies of these are probably at 0 volt are probably quite different, but they do interact. So exactly at 0 volt here, I wouldn't say you have a well synchronized state. You have a strongly interacting state, but they are not really at one frequency. So with these voltage gates, we are either making that frequency difference bigger by going negative voltage, or we're making it smaller by going positive voltage. And then just a little bit of positive voltage makes them really synchronize.
Yeah, it's very interesting actually. Yeah.
Okay.
Well, thank you very much. I think we'll have to go to the next speaker.
Thank you
Thanks a
so
lot.
much again for everything here. Okay. Bye
Thank you
bye.
so much, Johan, for this excellent lecture. So clapping for you.
Thank you.
Okay. So we move to the next speaker now. Hidekaju Kurebayashi. Can you connect your computer and
He's already online. You can just introduce and you.
all right.
I'm here.
Yeah.
Can you hear me?
Yeah. So good morning to
Yeah.
you.
Good morning to you too.
Yeah. Konnichiwa.
Konnichiwa.
Yeah. So Professor Kurebayashi is an associate professor in electronics and electric engineering at UCL. He also leads a spintronics group in the London Center for Nanotechnology. His main research interest is in spin orbit phenomena and spin wave physics in low dimensional and low symmetry materials in which he believes novel transport effects emerge. He was awarded a number of scholarships for his PhD, the Nakajima Foundation Scholarship, Overseas Research Studentship, and Cambridge Overseas Trust Scholarship. His PhD research won the runner-up in Abdul Salam Prize in 2007. He was an awardee of the Young Scientist Prize by the Minister of Education in Japan. His research has been recognized through high-impact journal publications, about 50 publications, which includes a numerous high-impact journals like Nature Material, Nature Nano, and Nature Physics, Nature Communication, and so on. So with this brief introduction, I request Professor Hidekaju Kurebayashi to start his lecture, which having the title Controlling Magnetism and Exchange Interaction Mechanisms in van der Waals Ferromagnet. Yeah, please start your lecture.
Yeah, I just tried to share my screen.
Yeah. Yes, can you start sharing
I just
the
tried to do
screen?
this. Can you see my screen now?
Yes, yes, we can see.
Great. And I just do full screen.
Yes,
Does it work?
yes. Yeah.
Good. All right, thank you very much for introduction, your detailed introduction. I'm pretty humble about this. And and also thank you very much for inviting this really exciting conference and then online. I haven't visited India in my life, but I'm really looking forward to do so in the very near future after this very crazy time. So my name is Hidekadu Kurebayashi from UCL, and I'm going to talk about something about like controlling magnetism with van der Waals ferromagnet. So during this conference already, this topic has been briefly touched upon by Professor Dash. So I don't need too much about the introduction, but I just talk about what I think important for this topic. And this work has been done by the collaboration between UCL, this is my university, and also mainly the NUS, that is National University of Singapore, Gorky Edders group. In particular, I just want to highlight the two young scientists, Ivan, the postdoc in Gorky's group, and also my PhD student, Saif Khan, who both did a fantastic job to push this really new topics into really fruition. And then I'm here just to talk about what they did in their experiment or research. Okay, so let's move on to the first slide. All right, so I just briefly introduce what is the 2D van der Waals ferromagnet. I imagine that like audience are familiar with kind of like spintronic 3D ferromagnet, such as permanent cobalt iron boron. But this 2D van der Waals magnet is basically just like a graphene with van der Waals gap, and with some atoms got like magnetic moment. So that's the only difference, but that's a big difference because then we can put a lot of spintronics idea and the concept into this materials or devices we want to make. Now, I just want to say that typically, just the player of this material is like a 3D transition metals, And then electronic structure looks like this, and not always like this, but just sometimes, chromium has got 3D prostate, and because of the strong control, you have 3 polarized like a T2G state, and then that gives you a local magnetic moment. And if you bond these local magnetic moments strong enough, then you can create a long range ferromagnetism between these materials. So that's the bottom line, and nothing more. And so then I just want to describe a little bit about what's the difference between 3D version of any homogeneous magnets, metals, and so on, and this new type of ferromagnet. And just simply, I just want to highlight that this really, you can see that this is 2D nature. You have a plane of materials, and so that there is some anisotropy between in plane and outer plane. So that always gives you some interesting future I will touch upon later. And also then individual, stack or, atomic coordinates got some interesting low symmetry coordinate. So that gives us a really interesting response term in the conductivity tensor, for example, and that related to, similarly effective spin Hall angle and so on and so forth from the spin texture in the momentum space. So that's bottom line. And also not only just the response function in to the electric field, but also that also affect obviously this free energy term, which is, for example, magnetic anisotropy. So what's the difference between these two is like a 2D magnet, so 3D ferromagnet. It is homogeneous, therefore sometimes it's favorable for having really like low damping and so on. The 2D magnet, it's interesting, and it's got lots of potential in terms of controlling, or spin current or spin orbitronics and so on. And finally, just want to say that these magnets can be stuck on top of each other like this, and we don't need to worry about lattice constant. If you want to make really epitaxial films, if you're a grower, you're so much obsessed with the lattice constant matching, lattice matching of the individual layers, but this individual van der Waals materials can be grown, not grown, but just fabricated by just exfoliation, which you don't need to worry about stack. So that's a number of, enormous number of, variations of a stack where you can design your new, functionality in terms of spintronics. All right, so then what's the materials looking like? So I just pick up the few, main players. One of this is like chromium, germanium telluride. And again, I don't want to tell too much about it, but just this is, again, just talk about this is layered materials, and the chromium carries magnetic moment, and this is a demonstration that this magnetism can be sustained down to, bilayer confirmed by, magnet optical, current rotation experiment. So, and that's actually really inspiring, and afterwards, many scientists started to work on this topic. And so this, I just want to highlight, this is bilayer. I think this group also tried a single layer, but I'm not sure that they have succeeded to see any sizable, magnet optical response from this single layer. And also, this is chromium iodide or chromium chloride, and this is some variation of this materials. But then a striking thing is these materials can also sustain ferromagnetism or magnetic order down to single layer. And because interlayer coupling is antiferromagnet, so if you make a bilayer, then you can create antiferromagnetic response where you don't see any strong response when you apply the magnetic field. But because this interlayer is weaker or weak, normally that is 100 times smaller than atomistic antiferromagnetic crystal, because this is reasonably far away. Then you can actually break this or make this transition from antiferromagnet to ferromagnet with the magnetic field which can be achievable within the lab. So that's additional controllability, so that we can play these two transition between these two in our devices stuff. And the 3 layers go back to the ferromagnetic regime, so that you can see them single nice hysteresis here. All right, so that's exciting. And another thing I just pick up is that not only just magnetism, but also we can select or pick up some conductivity by choosing a different type of the 2D ferromagnet. So I already introduced the two groups of these, which tend to be more insulating. But if you do a bit more about like iron or more transition metals, or even just 2D metal dichalcogenide, and then that can transition metal dichalcogenide that can give you more metallic behavior, so that we can play with conductivity and also within these materials too. And of course, this conductivity can be coupled to the magnetism. If there is no conduction electrons, then the only way to couple is more like a direct exchange, or just super or indirect exchange, such as super exchange coupling. Or you have slightly doped within materials, then you can be couple these to individual moment by some conduction electron, which can be hopping around to the different ionic states of the ferromagnetic ions. And if you go really dope more, and if you delocalize and bond-like transport, then you can start thinking about these magnetism and transport that are happening in the same side. Then we can assume that this can be described by direct exchange interaction within the materials, which is with this metallic regime. All right, so that's a nice playground. Again, I just want to emphasize. And the topic that I want to describe is then if we can tune this magnetism by just simply conductivity or carrier density, and then carrier density could be controlled by something like electric field. That was the topic of the previous speaker and the speaker before. Then we may be that's on the magnetism, but also this is carrier density as well. If that's more like semiconducting materials. And then we can talk about we can control this carrier density by electric field, or even just a chemical doping. That's what I'm going to talk about today. All right, so then there's some earlier work than me, or just at the same time we're working on this, but we are not fast enough to publish it. So this is one et al. Talk about the putting the gate on the back. So this is silicon oxide insulator, and then there's a back gate structure, and then putting chromium CGT, we call it. This is chromium germanium telluride. Then they measure this magnetic behavior by Morg. They can see some slight change of this magnetism. So this is the side of the magnetic moment scaled by the side of this Morg signal, and as a function of the voltage. And you can see that there is some subtle change when you increase the voltage up and down. And that's as much as they can see. And I just want to emphasize that this carrier density they could have tuned was 10 to 12 square per centimeter. And at the same time, we're working on a slightly different gating technique. This is called ionic gel gating, which can give you much stronger electric accumulation or depletion. And it tends to be more like 10 to 14. So this is 100 times bigger impact on the gating effect. So we are interested in, if you push further, what we can see apart from the subtle change of this side of the magnetic moment. And for the completion, I just want to highlight that similar technique has been done by the different materials, and then this group has achieved the room temperature ferromagnet by gating the thin film of this materials we normally call FGT. All right, so as in title, I just want to control the magnetism by electric way. So what controlling means electrostatic or either chemical doping, and the magnetism we want to control is exchange energy or exchange interaction mechanism. This is very related, or even just magnetic anisotropy, we will see. And the material that we want to focus on has been already introduced, that is chromium germanium telluride. And some highlight of this is ferromagnetic semiconductor states. The gap is not that big, and undoped material is like really insulating behavior. And then magnetism can be sustained by having a chromium between these two, and then tellurium is here, and the chromium is just connected through tellurium. So this is what we call super exchange coupling. And then the key point here is the magnetic easy axis is out of play, like this. Okay. All right, so this is some schematic for the device, and this is some optical images. So this is we put like 20 nanometer of chromium, so CGT by exfoliation, and put in gate and or the contact and the gate next to it, and then we just put the ionic gel to try to electrically gate to tune carrier density. So this is a typical source drain current as a function of voltage. And if you increase the voltage, you can see the large increase of the current. And if you just go down, and you can see that on the negative side, this is a Hall-Doped regime. It's not a good action. So we decided to focus on only the positive voltage side. In other words, electron-doped regime. And then we can just confirm that from Raman that after the cycling, this electronic structure, chemical structure or vibration structure doesn't change, which means that like we don't destroy or contaminate any lattice in this process. And what's interesting is that we start with 20 nanometer of CGT. It's a relatively thick flake compared to like fewer monolayers of this kind. However, when we gate it and when we accumulate large amounts of the electron at surface, what we found out later is that because of the strong Coulomb interaction, electron already sitting here try to push the electron downwards, and we can actually accumulate large amounts of the carriers only at surface, as thick as like 1 nanometer, which can be calculated by the simple equation like this. So although we start with like two relatively like 3D type of bulk ferromagnet, we achieve to see the really almost a 2D structure, and then we try to sense what's happening in terms of magnetism through this layer, because we're only sensing the magnetism by the transport. I will show you. And this is the resistance versus the temperature. So this is simple transport measurement. And then if we don't have any gating, so this resistance behavior is really insulating or semiconducting behavior. But once we apply the relatively large electric field or voltage, we can see that this temperature dependency changes into more like a metallic behavior, which is pleased to see. And by measuring the whole voltage or whole resistance, and we are able to quantify the carrier density by the slope. But the pristine one, in fact, this is relatively Hall-Doped, very small amount of Hall-Doped regime. But once you doped, or once you apply the electric voltage, you can see that the carrier density we achieved is 4 times 10 to 14, which is something we wanted at the start of our project. Again, which is very nice. All right, so I think everything is set. So we try to see magnetic transport result. So what we have done is apply the magnetic field outer plane for this particular set of data. Then we sweep the magnetic field back and forth. And you can see that we can see really jumpy behavior, but what we can confirm is really nice hysteresis, which is a signature of the magnetism. And then that can go up to, up to 180 kelvins. Although the bulk of Curie temperature bulk CGT is about 64 Kelvin. So this is very nice because we already, this is almost a sign that we increase the Curie temperature of more than 100 Kelvin by just applying the electric field. All right, so a little bit more detail about this magnetic resistance. Now, instead of like measuring back and forth in the outer plane, now we measured this magnetic resistance as a function of the angle, outer plane angle. And we can see that, again, this is very jumpy behavior, but as soon as you tilt the magnetic field from the outer plane, we can see that this hysteresis really shrink down to a smaller magnetic field. And then that behavior continues down to in-plane angle. And then we so it's very difficult to use some like a phenomenological model to explain this, but because what we know is because of this like domain wall propagation or nucleation depinning. So what we discussed this data by looking at the field where this back and forth resistance matches together. In other words, we believe that at this point, this magnetic field is high enough to complete the switching process, so which is called saturation field, we call it. And if you plot this value as a function of angle, you can see really peaky behavior at the center of this point, which is the outer plane angle. And very, again, phenomenological description can be explained this. So if you try to explain this by the single domain model, Wolf model, then this behavior of saturation field doesn't match well with what the theory predicts from the single domain uniaxial Wolf-Wolf model. However, if you start to introduce that this is multi-domain and let's think about domain wall energy, so this kind of 1 cosine gamma is just angle, outer plane angle, then that can nicely fit to our experimental observation. So what we can tell you is that at least this switching is involved or associated with the domain wall component, which is, I think it's not surprising, but it's nice to see that we can confirm from our experiment. Okay, so that's the almost summary of the experimental results. So we just show this field as a function of the temperature. And then you can see, so this is the pristine means one extracted by FMR measurement. So you can, the value is negative, which means that outer plane field is favored. And then that does quickly die at the temperature of about 60 Kelvin. But as soon as you apply the voltage, you can see that this field is really faster with the positive, means that magnets trying to polarize in plane, favor the in plane direction. And then this one, if you increase the voltage, then you can really push this Curie temperature up to more than like 200 Kelvin. So that's nice to see. And just a bit of demonstration. If you apply 3.1 voltage, 170 Kelvin, we don't see any hysteresis, but if you just crank up to 3.79 voltage, we can make this hysteresis, which means that we can turn on and off the magnetism by the electric field. All right, so the interpretation, that's very important as a scientist. So undoped regime, this is more like semiconductor. The only activated exchange coupling is a super exchange, as I already explained. So what it means by that is this is what's happening is that in the super exchange coupling is that actually one electron is just excited into an above high energy state, and then now they start to hop around. So this is very inefficient in terms of process because this is involved excitation. Now, when you start to gate and you now push this Fermi level down to up to this conduction band, then you don't need to excite the electron like this, but it's already electron there. And then this electron can hop around through the tellurium. And this is exactly what we call it double exchange coupling interactions. And then that's much stronger compared to the super exchange. So therefore, you can boost the exchange energy by using this process. So in other words, we can control this exchange mechanism by just apply the electric field in a 2D magnet, which is nice. Right, so then our theorist DFT calculation can support this concept. So this is just measuring the free energy when they forced to have this FCGT in the antiferromagnet or ferromagnet, and they calculate the difference. So then you can see that when you dope, and this difference can increase the large number, which means the exchange energy is enhanced by the doping. And also magnetic anisotropy, which we saw the sign change in the experiment, we also see some interesting change as a function of the doping. So in low doped regime, this outer plane field is favored, but when you increase the voltage and then if you hit some threshold, you can start to see that magnet try to be in plane. As you can see that this sign change of this value is changed. So they confirmed that by calculating the polarizing magnetic moment one outer plane direction, an in-plane direction and subtract it to see the difference in energy, which is in a couple of milli electron volts. Okay. So, all right, so that's the interpretation. And then now I'm going to touch upon a little bit on the chemically doped regime. What I can tell you is that, first of all, we can dope this 2D magnet at the, to dope this some of the alkaline metal between this van der Waals gap, or within the van der Waals gap, which is something you can do with only in a 2D van der Waals magnetic materials. So then we don't perturb this entire lattice of flame and magnetic interaction too much, but then we can dope heavily on these materials. So that's the techniques, what we call intercalation. And difference between these two electric and chemical doping is that in electric doping, we induce a carrier density, and also at the same time as we observe, we have a huge amount of electric field at the surface. And also as a result, in our experiment, we have some sort of 2D confinement. So then we don't know which element can cause the Curie temperature increase, or domain wall propagation, and so on and so forth. It's nice to see all of them, but we cannot pin down which one causes which. Whereas when we do a chemical doping, what we can at least exclude is these two components. We don't have electric field because this is kind of homogeneous doping, and also this is a bulk material, therefore we don't have 2D confinement. So only we are left with is this carrier doping. Therefore, by comparing the results of this chemical doping and electric field doping, we may be able to understand a bit more about what we observed in the first experiment. So that's the motivation. All right, so we put this materials into the van der Waals gap. And then this is resistance versus temperature. And you can see that so this is an undoped regime. So we can see a nice shooting of this insulating when you hit this around Curie temperature, which is a typical signature of CGT. But when you dope it, although we cannot get the metallic behavior, but at least we can see that resistance goes down and temperature dependence is really, really moderate, so that we can still do some transport measurement at low temperature. Right, so this is a typical resistance versus, it's basically magnet resistance versus magnetic field. And you can see that it's rather than like a jumpy behavior, you can see like a peaky behavior at center. So that's already giving us some difference. So this is a measurement at 15K. And I just show you the temperature dependence of peak size. And we can see that the peak is gradually decreased but sustained up to around this region, around 200K. So it's hinting that maybe we can also increase the Curie temperature by chemical doping. Let's look a closer look on this magnet resistance. So this is the measurement where we just sweep the magnetic field back and forth with a different angle with respect to the in-plane, so outer plane. So then we can see that when you do the in-plane measurement, this peak is narrower, but when you do the outer plane measurement, peak is wider. So that means a larger magnetic field to complete the switching. So that means we call it the outer plane as a hard axis in our context, which is the same as the consequence of the electric field. So let's look a little bit closer between these two. So what we can tell you is that we can increase the Curie temperature and also the switch of the magnetic anisotropy by the doping. However, the hysteresis loop is very different. One is very jumpy, and the other one is like a central peak type of things. Even we don't know whether this is coming from magnetism because we don't see much of the hysteresis here. We will confirm that this is magnets in the next few slides. But anyway, so this is different. So what I can tell you is a magnetic switching phenomena is very depend upon either electric field or dimensionality. But then Curie temperature and also magnetic anisotropy seems to heavily depends on carrier density. So that's the conclusion we have with these two sets of the results. So finally, I just want to flush out whether really this is coming from magnetism. So because this is bulk materials, we can measure some like a volume-related measurement, such as FMR in a waveguide. Right. So then this is just a reference. This is the FMR as a function, frequency as a magnetic field, and then this is the undoped CGT. I just want to show you this is a typical hard access behavior of the FMR when we measure the magnetic field in plane. Right. So we have some rotation regime that's the V shape is kind of hard access behavior, shall we say. Now, when we measure the FMR for doped regime, this V shape is gone, basically pushed to this 0. So that means this is the easy axis in a layman term. And then what we can see is that, we can see the central peak, but also we have some satellite peak. We don't know yet what it is about. It may be the spin wave, but we don't know. We will find out later. So that's what we are saying. And let's think about the temperature dependence. So this was, by the way, this 15 Kelvin, and we've gone up to 150, 200, 240, and then this peak, it just disappeared about somewhere between 240 and 250. So surprisingly, this can sustain the magnetism up to 240 Kelvin. So that's really interesting. And this is just a peak analysis, and it can nicely fit to the Kittel formula so that we can extract some magnetic parameter out of it. We will show you maybe when we publish this paper based on these results. And pretty much that's it. So I hope that I convince you that electric field and just doping in both ways, like electric field or chemical doping, can really change the magnetic properties in the studio ferromagnet. This is nice playground, and this is just one result, and we can really do lots of different things on this path. So this is just about magnetism, and we are still working on the spin transport part, which we again are very interested in, and there are lots of things to do in the future, just from the single materials, but from the many materials too. And with that, thank you very much, and I'm happy to answer any questions.
Oh, thank you so much, Hidekaju. So it's a great lecture, very interesting results. Is there any question from the audience? At the moment, not. So I will probably ask one or two questions. So the samples which you have made the nano or microfabrication for the devices. So it is just the CGT is basically a peel off from a single crystal, or you have grown a thin film?
Right. So this is the beauty of the 2D material. So I probably use this schematics. So Ivan, the postdoc in NUS, he did exfoliation. It's basically like graphene, 2D material.
Yeah, okay.
Okay, so this exfoliation put down on the silicon oxide substrate about 20 nanometers, and then put there on the electrode by e-beam lithography. So that's the process.
Understood. I wonder if you try to grow this CGT by some deposition technique, some physical vapor deposition.
Yes. You can grow these by MBE.
Okay.
And there are lots of exciting experiments along the path, because they grow CGT in MBE and then connect it to grown topological insulator on top, so that you can probably see the time reversal symmetry broken of the TI by doing so. So you can grow by MBE, and I believe that you can grow by CBD as well. So it is possible to grow by chemical or physical deposition processes, not only just the mechanical exfoliation.
Okay. Last but not least question from my side. So when we call about this 2D magnetism, so it is just limited to one monolayer, or we can take few monolayers and it will be still 2D, quasi 2D, so to say.
Are you talking about my device or
Well, in general, in general.
Yeah, so, all right. So that's the excitement. Maybe just well, right. So all right. Maybe I don't know which one. So right, we can try this. So they coupled intro layer, so within the plane, and that seems to be strong enough to sustain the ferromagnetism for the particular materials, at least at the low temperature. Now, that's already enough. But then when you put the additional layer, then there's an interlayer coupling, and that can boost the additional, action coupling. So that is additional element. And if you make it more like the localized, metallic, band-like Stoner criterion type of things, then this could be important to boost more ferromagnetism, I think, in a three-dimensional way.
Okay, thank you so much. Are there many more questions, Pranav? Do you see that?
Yes, there is one question from a student, Himanshu.
Okay.
Why the resistance suddenly increases below 100 Kelvin for the undoped sample?
So I believe that's so there are two things. Electric one. So this is, by the way, this maybe just I didn't mention, this is log scale. So although this is like a gradual increase, then actually if this is a linear scale, just really the increase. And just when I move on to the chemical doped one, let me just try to go. I think he was talking about this, your student.
Yes.
Himanshu.
Yeah.
And then if you move in, no, this I didn't ask my student to put in the log scale, but I should have done this. But if there's a log scale, it should be more gradual increase. But this is interesting. Some people think that this is more like a multi-insulator. So some people are looking at critical behavior at this temperature. This coincides with the ferromagnetic transition. So there's an interesting behavior happening there. But I would say that this is in general typical behavior as an insulator or semiconductor. So why that is why maybe just I said this is unusual, but then this is rather highlighted because we just plotted a linear scale. Apology to that one.
Okay.
So I was just wondering, have you measured the damping constant of this material, because you showed the FMR?
Sure.
But,
We measured.
How
we measured means that you can see that we are able to quantify the damping, and and then damping is large, as you wouldn't be surprised. So if you think about spintronics devices, this is a way, this is not the immediate interest, but then that could be, I believe, overcome by finding new materials, and new material in this research domain is really important research topic, and I'm sure that lots of new material will be discovered, and then we can exploit that.
Okay. Yeah, I was just wondering one more question maybe about this electric field control magnetism, or you showed this change of magnetic anisotropy. Can we call this as a BCMA, or you think BCMA is different?
BCMA, voltage control magnetic anisotropy.
Yeah, people like observing the.
All right. I can tell you. So I believe that that it's more like a ultra thin film of the ferromagnet, and then they change the electron number at the surface, and they can change the outer plane magnetic anisotropy, which I would call it like interfacial effect. However, the thing that we observed is a bulk effect. So that's a stark difference. So I don't know if you call it BCMA, but this I just want to highlight that this origin or mechanism is very different.
Okay.
Probably this is more similar to gallium manganese arsenide. Although I don't know how much magnetic moment has been sort of magnetic anisotropy has been perturbed by that in a quantitatively way. I know that Chiba et al. Did it, but I don't think they didn't observe the switching over the EZ axis. I believe.
Okay. Yeah, it's very interesting to show this switch.
Yeah, I think so. We are very excited about it, and then yeah.
Okay, so we move to the next lecture. Thank you so much, Hidekaju, for your excellent lecture. I clap for you. I'm sure others want to join.
Thank you
really
very much
nice.
for your praise. Yeah, all right. I will unshare my screen. Yeah, thank you very much.
So we go to the next speaker, Professor Ashwin Tulapurkar. Ashwin is here.
Yeah, can you see me?
Yes, I can hear you.
Okay.
Hello, Ashwin. So I think he is also a very known person in our spintronics community. But as a matter of formality, I say a few words about him. So Professor Ashwin Tulapurkar is working as a professor at the Department of Electrical Engineering at IIT Bombay, Mumbai. He obtained his PhD degree from Tata Institute of Fundamental Research in 1999 on the topic of hyperfine interactions. He subsequently worked at AIST Tsukuba in Japan, then Stanford University, again back to Japan, Tata University, and then he moved, I think, as an associate professor at IIT Bombay. His research interests are spin-based phenomena and magnetic materials. He has published more than 70 papers in internationally reputed journals and also has a few international patents. So with this brief introduction, we are very much looking forward to your new results, what you have published this year. And yeah, please take over, Ashwin. Thank you.
Thank you, Chairman. It was nice kind of you to introduce me. So I will share my screen now. Okay, so is my screen visible now?
Yes, it's working fine. Yeah.
Okay, so thank you again, Shubhankar, for the introduction. And I would also like to thank Pranaba and the organizers of this conference for holding this beautiful conference. And I see a very lot of interesting talks on spintronics in this conference. So thank you for that. And thank you for inviting me here. Okay, so today I'm going to talk about how we can generate charge current from oscillating magnetization. So typically we know that if we use Faraday's law, we can generate charge current if we have a magnetization which is oscillating. So I'm going to talk about a new effect by which we can generate charge current. And this work has been done in collaboration with between IIT Bombay and AIST. So the first four names here are the students from IIT Bombay who have worked on this, and then we have some researchers from AIST. Okay, so the outline of my talk is the following. I will start with some introduction to how we can control magnetization, and then I will talk about the various reciprocal effects in spintronics and how we can measure these effects. And then I will talk about what would be the reciprocal of VCMA effect. Okay, so I will start with this typical slide on dynamics of magnetization. So essentially, if you have a magnetic moment, then we can use the LLG equation to describe the dynamics. The first term here is the precession, and the second term gives us the damping. And so then in 1996, a new term was introduced by Slonjewski and Burge, which is called as spin transfer torque. And now by using the spin transfer torque, we can control the magnetization. So apart from using the magnetic field, we could also use the spin current to control the magnetization. And there are various ways by which we can produce spin current. So a simple way is that if we have a magnetic tunnel junction, and if we apply a voltage across it, then this produces a spin current. And then this spin current is absorbed by the free layer here, and then that produces a spin transfer torque. The other way of producing spin current in a tunnel junction is to use spin dependent Seebeck effect. So what you can do is you can maintain the free layer and the pin layer at two different temperatures, and this temperature gradient gives rise to a spin current because of the spin dependent Seebeck effect. And again, we can use this spin current to control the magnetization of the free layer. Okay. Now, other way of producing spin current, which is very popular, is by using spin Hall effect. So in this effect, what essentially we do is we take heavy metal like platinum or tungsten, and if we pass charge current through it, then this generates a spin current, which is perpendicular to the charge current. And now this spin, now if we have a tunnel junction on top of, let's say, platinum as shown here, then this spin current is incident on the free layer, and then the free layer absorbs the spin current, and we can change the magnetization of the free layer. So this is how spin Hall effect works. Now, similar to the previous slide where we had used the heat effects, here also we can use a temperature gradient across a layer of platinum to generate spin current. And then this would be a spin nurse effect. Again, this temperature gradient through platinum produces spin current, and then the spin current is absorbed by the free layer. And okay, and by this we can control the magnetization dynamics of the free layer. Now, apart from that, there are also various other ways by which we can control the magnetization. And this is important because if you take any spin device, then essentially what we are trying to do is somehow control the magnetization. Okay? So then we can use it for memories, logic, or even making oscillators and so on. So the other way of controlling magnetization is by using strain. And so essentially this relies on the magnetoelastic effect. So as shown in this picture here, if we have a piezoelectric film and if we apply electric potential, then that generates strain because this is a piezoelectric substrate. And then the strain couples to the magnetism through magnetoelastic effect, and we can change the anisotropy of this nanomagnet, and then we can induce switching in it. Okay, so now apart from that, the other way of controlling magnetization, and this is what I'm going to talk on today, is by using voltage control of magnetic anisotropy. So this effect was first discovered in 2007, where by this group, where they used liquid electrolyte to apply electric field to a thin layer of ferromagnet and insulator. And then in 2009, this effect was shown in the case of magnetic tunnel junctions by this group from Japan. And since magnetic tunnel junctions are very important for the spintronics devices, this was immediately picked up by various groups, and a lot of research has been carried out on this effect. So this is the slide from this paper which was published in Nanotechnology in 2009. So here you can see that there is a thin ferromagnetic layer here, which is about only 2 to 4 monolayers. And on the top, we have insulating barrier. And now if we apply a potential difference across these layers, then that generates electric field at the interface between the ferromagnet and the insulator. And through this electric field, we can control the electronic orbitals at the interface. And then this can change the anisotropy of the ferromagnet. So as you can see here, by applying a plus voltage and a minus voltage, they could change anisotropy from making it more anisotropic to less anisotropic, and that was reflected in the hysteresis of magnetization. Okay, so the way this effect works is the following. So I showed you this equation before. So this is the LLG equation. So now there is no spin current here, and what we have is an effective field. And this effective field has contributions from the external field and anisotropic field. So typically, if you take a nanomagnet, you will have an in-plane anisotropy. So for example, here I have taken the x-axis to be the Icee, and then we also have out-of-plane anisotropy. So this I have denoted by h perpendicular. So both I have constants, so which would mean that the x-axis is the Icee axis and z-axis is the out-of-plane hard axis. So now by applying a potential difference across the ferromagnet and the insulator on the top, we can change the magnitude of h perpendicular. So this, for example, we can change the in a linear way by applying voltage. So if you apply a positive voltage, then anisotropy will increase, and if you apply negative voltage, then anisotropy can decrease. So essentially, by controlling the anisotropy, we can also use it for switching, as well as we can also do some kind of coherent control. If this voltage is oscillating, then that would mean that effectively I have an oscillating magnetic field. And now this oscillating magnetic field can induce magnetic resonance, which can be measured. So this is the experiment again done by the group in Osaka University. So again, you can see that here is a thin layer of ferromagnet. So actually this is a magnetic tunnel junction. And then we have a thin layer of magnesium oxide here. And when we apply a voltage, yeah, we have also spin current. But apart from that, we also have the VCMA effect. And in this particular experiment, they have shown that the VCMA effect comes from the VCMA effect. And by this VCMA effect, they could drive this ferromagnet into a resonance. And then by using the spin torque diode effect, they could measure that signal. So you can see peaks at various frequencies which correspond to the resonance which is induced by the VCMA effect. So essentially the point is that we can use VCMA effect both for switching as well as for coherent control of magnetization. Okay, so now if you look at the various effects in spintronics, there's always a reciprocal effect. So for example, if you look at the spin transfer torque, so this picture shows the spin transfer torque. So we have a spin current which comes on a ferromagnet, and then this ferromagnet starts rotating. So inverse effect, and this inverse effect is that if the ferromagnet is rotating, then the rotating ferromagnet creates a spin current. So this is called as spin pumping. Similarly, if you take the spin Hall effect, in spin Hall effect, we have charge current which passes through heavy metal, and then this creates a spin current. Now, if you do the inverse experiment, if you pass spin current, generate charge current. So this is now the inverse of spin Hall effect. So you can see that in spintronics, whenever we have one effect, we always have an inverse effect. So for example, for spin Sipek effect, we have, for Rashba-Edelstein effect, we have inverse of that as well. Then for effect, we have Sipek effect. Then for magnetoelastic coupling, we have magnetostriction, and correspondingly, we also have inverse of magnetostriction. And all these inverse effects have found many applications in devices. Okay, so it's very interesting from the physics point of view as well as from the devices to look at the inverse effects. So now the question is that we have a VCMA effect, and what would be the inverse of this effect, and how will you observe this inverse effect? Okay, so this is the question that we are looking at. And so for this reason, we started doing some experiments in collaboration with AIST. So we deposited a stack, okay, a multi-layer stack as shown here from it. It has one ferromagnet, thin ferromagnet about 1.2 nanometer, and then we have a magnesium oxide there. So this is not a typical stack which is used for tunnel junctions. In magnetic tunnel junctions, there are two ferromagnets, but in this particular stack, there is only one ferromagnet. Okay, so this is an important difference. So first, we characterize this film by using an ESR spectrometer. So you can see our absorption spectra, and also we did this measurements as a function of angle of magnetic field, which you can show in this inset. And we can fit this data using the LLG equation, and we can extract various parameters. So for example, found out that the damping in these films were about alpha was 0.03, and the perpendicular anisotropy is 400 Oersted. So what it means is magnetized in plane, but typically the out of plane field is very large, okay, maybe few kilo Oersted. The structure, this anisotropy has become very small. Okay, so we need only 400 Oersted to make this film out of plane magnetized. Okay, so then we started our experiments to measure the inverse VCMA effect. And from this stack, what we did was we fabricated pillars which were of dimensions 3 micron by 80 micron. Okay, so these are very elongated pillars. and we need such kind of pillars to really get a good signal. Okay, so this is really an elongated long pillar. Then you can see that also auto, and then on the top of that we deposited SiO2. So now all the samples are insulated, and then on the top we deposited waveguide. So essentially now our device has two ports. So this is port 1 and this is port 2. The port 1 is connected to the tunnel junction formed out of cobalt boron, and port 2 essentially is a waveguide. Okay, and they are insulated by a layer of SiO2 here. So as a first step, we should make sure that whether this film shows VCME effect or not. So what we have done is essentially we measured only one port measure. So we measured the S22 parameter. So essentially we pass RF current through the port 2 and measure the reflection, and then at a particular value of magnitude the resonance, which corresponds to the ferromagnetic resonance. So this is at a particular field and frequency. We have seen this resonance. The function of magnetic field also we measured, and this can be fitted to the Kittel's equation. And then what we did, we applied a DC voltage to port 1. Now, as a function of DC voltage, the peak in the resonance field shifts either to positive side or negative side, depending on whether the voltage is positive or negative. And this shift essentially indicates that we have a VCME effect, because the resonance field depends upon the anisotropy. Application of voltage that is reflected in the shift of these peaks. So as a function of different voltages, we measured this shift and we found that the shift is linear, which is expected from the VCME effect. And we found out that the VCME coefficient is about 100 femtojoules per voltmeter. Okay, and then from this data, we also extracted the damping coefficient and perpendicular anisotropy and so on. Okay, now in the next part, we measured the scattering parameters of the device. And the idea is the following. So let's start with the S21 measurement. So whenever we do S21 measurement, to apply an oscillating voltage to port 1, and we are going to measure the signal which appears at port 2. Oscillating voltage at port 1. Okay, this is going to create an oscillating voltage across this junction. So essentially, excite the magnetization by the VCME effect. And once the magnetization starts to oscillate, this waveguide is going to pick up the signal through the inductive coupling, and then I get a voltage here. Okay, so this is how I get S21 signal. Now, if you look at the S12 signal, so while measuring S12, apply oscillating voltage to port 2. So essentially, an oscillating current flows through this port, and this creates an oscillating magnetic field. Okay, so this is the Oersted magnetic field. Now, because of that, again, this flow magnet can undergo, it will start oscillating, and whenever it oscillates, it creates a charge voltage here, okay, which is detected in port 1. And this is nothing but the inverse VCME effect. So this will show you that when the magnetization is oscillating, it is charge voltage, which must occur through the inverse of VCME effect. Okay, and that's how we are getting the signal here. So you can see that I have two steps here. And on the right hand side, I have the inverse of these two steps here. So if this is the first step, the inverse of the step is, if this is second step, the inverse of that step is the first step here. Okay, so this is how we can measure the inverse VCME effect. So what we did was we measured this effect for different values of magnetic fields and also different orientation. So we can see that this was our ferromagnet. So we can apply the field either in XZ plane or YZ plane or any arbitrary angle. So first we applied the field in the XZ plane. Now, and we swept the field. And then we can see that in the S12 and S2 peaks, which appear because of the resonance at a particular value of magnetic field, the frequency was fixed to about 5. And now you can observe that there is certain symmetry between S12 and S21. So both of these signals are symmetric with respect to magnetic field. So which means that if I simply invert the magnetic field, the S12 or And not only that, the S12 and S21 are same signals. Okay, so there is no difference between S12 and S21. Then we measured the height of this signal like Z plane, and we found this kind of a signal. So again, I will show you later that this kind of dependence can be explained on the basis of inverse VCMA effect. Okay, so we'll talk about it later. Okay, we change the plane, and then we found out something very different. So essentially now the symmetry between S12 and S21 is anti-symmetry. Okay, so which means that if I change the value of magnetic field, the signal changes sign. So if I go from plus 1200 volt state to minus 1200 volt state, you can see that the signal has changed sign. And similarly, if I look at S12 and S21, then they are equal if I invert the magnetic field. But in both the cases, you can see that if I invert both the magnetization and the magnetic field, then the signal remains same. So now this is consistent with the generalized Onsager reciprocity. Now you can see that in our sample, there is no spin transfer torque because we have only one ferromagnet. And rule out any contribution from the Oster magnetic field. So essentially, the Oster magnetic field will not give you, this kind of a dependence, and also it will not this signal. Okay, so essentially, we think that the signal comes from the VCMA effect and its inverse. Okay, so the next question is that how do we get the inverse VCMA effect? So we can get it from simple thermodynamic arguments. Okay, so I will give you these arguments. At the thermodynamic potential of a ferromagnet, so essentially the electric field is coupled to the magnetization, and in general you can write it in this form, okay, where this lambda is now a third rank tensor. And if you want effective field, you can take the derivative of this by magnetization. So then you will find out that there's the effective field which is proportional to electric field. And this is nothing but the VCMA effect. So this is the usual stuff. But of course, for our experiment, we don't have such a third rank tensor. We have only one component of it. So we can simply take some lambda times electric field along z direction into mz square. Okay? And then we get effective field in this form. Okay, so this is the usual VCMA effect. Now what you can do is, if you take the derivative of this by electric field, then you will get this d. Okay, so this is the displacement derivative by mz, where I get magnetic field, same potential. If I take derivative by electric field, then I will get the displacement density d. Okay, so I can do that, and then I will get this as the displacement field, okay, d. And when I do that, I need to be careful. So I have multiplied by a factor of ratio of these thicknesses, and whenever we take the derivative of this, we have to take derivative per unit volume. Now this was per unit volume of ferromagnet. So here I need per unit volume of the dielectric. So I need to multiply by this kind of factor. And then once I know this d, if I take the derivative of this by time, I get the charge current density. Okay, so this is from Maxwell's equation. So then I can take derivative of this by time. So essentially I have to take derivative of mz by time. Okay, so that gives me the charge current. And if I multiply by area, then I will get the current. So now this is our model, that if we have a ferromagnet in contact with MgO and we have VCMA effect, and then it creates a charge current. So this is the current source whose value is given here, and this is the internal impedance of the current source. Okay, so this is how we can explain, or this is how we can model the VCMA effect. And this also tells you that if I change the magnetization from, let's say, mz equal to 0, mz equal to +1 or -1, I will get a charge accumulation on this capacitor. Okay, and this is the charge accumulation. And of course, the charge accumulation will decay because of this parallel resistance. But if we use a very thick MgO, then we can neglect this resistance and capacitor. Okay, and in fact, we can use it to measure the inverse VCMA effect. Okay, though we have not done that, but it is possible. Okay, so now actually it is not difficult to calculate this S21. So if you look at S21, essentially we are applying an oscillating voltage, and then this voltage creates FMR, and then we measure signal inductively. Okay, so it is not difficult to really calculate this effect, and you can see the details in the paper. But essentially, if you look at this signal, what we find out is that we get a factor of sin theta into cos theta. Okay, so this is because how the VCMA acts, we get a factor of sin theta into cos theta, and to some factor which depends upon phi. Okay, so whether the field is in the XZ plane. So if we assume that the field is in the XZ plane, then we get sin theta into cos theta dependent. So which means that S21 is symmetric. If we apply the field in the YZ plane, then we get one more factor of cos theta. So the dependence is sin theta into cos theta. So this gives us antisymmetric behavior. So this is exactly what we have seen in our experiment. So this confirms that the effect is coming from the VCMA effect. And similarly, if you look at the angular dependence of the signal, so this simply is given by sin theta into cos theta. So you can see that the signal and maximum somewhere in between. So essentially, we can neglect the O-state field and assume that this signal is simply coming from the VCMA and its inverse. Okay, so now if you see what we have done is we have derived or we have argued that the inverse VCMA effect should exist from thermodynamic arguments, but the same effect you can also derive in a different way. So what you can do is you can look at the dissipation generated by a VCMA effect, and one can get the inverse VCMA effect. So the idea is the following. So I have this tunnel junction with ferromagnet and a MgO layer. Now let me assume that I have a voltage wave which is incident on this. Now because of this impedance, I get a reflected wave. Okay, so this is fine. But when this voltage wave is incident on this tunnel junction, because of the VCMA effect, the magnetization, and because of the damping, we get additional resistance. So essentially, I should now represent this by ZMTJ in parallel with. Okay, so now this Z magnetic we can find out from the dissipation. So the dissipation is simply given by alpha times some factor into square of dm by dt. So all these factors you can easily find out, and then you will. Now this dissipation is related to the real part of the Z magnetic. So you will get the real part of it. Okay. And once you know the real part, you know the imaginary parts are Hilbert transforms of each other. So essentially you can find out what is the Z magnetic. So here this is Y magnetic, so which is essentially inverse of Z. Z magnetic is given by this factor. So now what we do is the following. So the idea is now following. So let me assume that I have only one port. Okay, so I have this tunnel junction, and I have this kind of signals coming in and going out, and I have the Z magnetic. So now what I want to do is get rid of the Z magnetic and represent the effect by a voltage source as shown here. And this should be done in such a way that I get the same reflected voltage wave. Okay, if you can do that, then VCMA effect, or then you can say that the inverse VCMA effect is represented by a voltage source here. Okay, and which will give me the correct reflected wave. So this is simple idea behind the model that I have shown you before. Now this, so the previous one was assuming that I had only one port. Okay, but even if you have two ports, so remember that in the experiment we have two ports, so I can also apply voltage here, I can also apply voltage here. Okay, so in general, I can have two excitations. I can excite the magnetization by voltage here or by current here. And so that's why, instead of using the scattering, it is better to use these hybrid parameters. And the idea is that if you look at the magnetization excitation, it comes from the voltage here and the current here. Okay, so essentially you should take voltage and current as two independent variables. Okay, so and again the idea is same, that I have a tunnel junction in parallel with I have a magnetic impedance, and now I want to get rid of this Y magnetic and this part which comes from the top electrode, and then represent this by a current source. Okay, so previous slide I represented it by a voltage source. So that was a Thevenin equivalent, but I could also use a Norton equivalent, and I can simply represent this by current source. So this is how you can the inverse VCMA effect. Okay, so now okay, I'll just quickly show that what would be the applications of this or VCMA effect. So one effect is obviously that we can generate charge current from oscillating magnetization. So this is something good. So which means that I can use this effect as a new probe of magnetization dynamics. So typically when we probe magnetization, we use tunnel junctions. Okay, so we need a free layer, a fixed layer, we need a bias current, and so on. But if we use this effect, then we don't need any bias current or a fixed layer. Okay, simply we can use this effect to probe the magnetization. Now this effect can also change how spin waves propagate or how domain wall moves. And I strip of ferromagnet, and on the top you have MgO layer, which gives rise to the VCMA effect. And now suppose a spin wave is propagating in the sample. So essentially, if you look at each small section of the ferromagnet, the magnetization is oscillating. Now this oscillating magnetization by the inverse VCMA effect will create an electric field at the interface between MgO and the ferromagnet. Now this electric field is going to have a back action. So this electric field is, so there is going to be some kind of a back action from the inverse VCMA effect, and this is something that we are trying to calculate right now. But I guess this is going to be an effect which should be taken into account. Okay, so with this I will summarize my talk. So what I have shown you here is that we can measure inverse VCMA effect, and what we have done is essentially we made a device which has 2 ports, and by measuring the scattering parameters, we showed that the scattering parameters follow the reciprocity. So that means they are equal if we invert the magnetic field and also the magnetization. And inverse VCMA effect we can represent by a circuit model. So essentially we have a current source and then we have an internal impedance. And one point I would like to mention here is that so this effect we have argued that it can be shown that this effect must exist by using thermodynamic arguments. And we also showed that this effect must exist if you simply consider dissipation. Now the other way is that we can also look at the reciprocity of these parameters and also argue that such an effect must exist. Now if you compare the effect to the spin transfer torque and its inverse, which is spin pumping, and so in the case of spin transfer torque, there is no thermodynamic potential. So we cannot use the argument that I have given you before. But we can use the argument of dissipation, or we can use the argument of reciprocity. And so if you know the spin transfer torque, then from that we can easily derive the expression for spin pumping effect. Okay, so with this, I would thank you for your attention, and I would like to thank all my collaborators and also IIT Bombay for supporting this research.
Okay, thank you so much, Ashwin, for this very nice presentation showing your recent results. So are there questions, Pranav? I cannot see anything.
Yeah, there is one question by Professor Kurevasi. Maybe you can unmute and ask.
Hi, can you hear me now?
Yes, yes.
Oh yeah, thank you very much. It's very fantastic attempt. And then I'm very interested in, and one thing I just want to ask you is that when you have a precession of magnet, and obviously one thing you have to be very careful is a magnetic induction caused by magnetic field variation by this.
Yeah.
And that can clearly give you charge current.
Yes.
Do you know the symmetry of, because I understand that your claim is really based on your symmetry, sine theta, cosine theta symmetry.
Yeah. So okay.
Do you know the angle dependence of the this induction current to exclude this possibility?
Okay. So so if you have So yeah, so I think that's what I talked about here. Okay.
Maybe I missed that.
Yeah. So if you look at the Oster field contribution, it is not expected to show this kind of behavior. Okay, it will show a maxima somewhere, and then it will go to 0. Okay, but the fact that we see the signal is 0 at the 2 points and it becomes maximum. So I think by this we can rule out the Oster field. And other thing is that so if you look at this is symmetric, but if you now change the way we are applying magnetic field, then the signal becomes anti-symmetric. So I think this is also not expected from the Oersted magnetic.
Can I? Sorry,
Yeah,
this is a following up question. Is that okay? So in terms of this line shape, that depends on the phase between these two. So that means that depends on the length of like microwave line, because when you have a longer microwave line, your symmetric part becomes anti-symmetric part, and so on and so forth.
So the length is actually quite small compared to the wavelength. So the length is about 80 microns.
So that's the assumption. Okay.
Yeah. So this wavelength will be maybe 10 millimeter. You know, the microwave wavelength.
Yeah.
If it is due to the phase, then it should change the line shape with the frequency. Right? Did you see that? If you go to another frequency, maybe the line shape may change.
Okay, so at each frequency, we have done some kind of a calibration. So if we do the calibration, then so the signal is not very great in this geometry, but quite strong, and we could clearly see a peak and a dispersion for each frequency.
Okay.
Was that a question?
Yeah, sort of. I have another question. I was wondering, how is this second port connected actually? Because if it is isolated from your magnetic structure, why do you get a magnetization signal when you measure S22?
No. So when we measure S22, it's simply like a usual FMR experiment. We have a waveguide, and on below we have a ferromagnet. So it's like a usual FMR signal.
Which is like observation. Okay. Okay. Understand. Okay.
And,
so because you are.
So that's the reason that this is very long, because if you make a small sample, this FMR is very difficult to see. So that's why we had to make a long sample, about 80 micron long, to get a good signal.
Okay, so can I ask one question?
Yeah, sure.
You have more questions?
Yeah, if I can ask one more question. Yeah.
Okay, please.
So I was just wondering, when you say inverse VCMA effect, VCMA effect, you apply voltage, you change the magnetic anisotropy. Now, when you say inverse, you change magnetic anisotropy and generator voltage. So what is how you change the magnetic anisotropy here?
No. So I think we should really think in terms of the AC signals. So if I think in terms of AC excitation, if I apply AC voltage, VCMA, I create AC oscillations of the magnetization. So now if I have oscillation of magnetization, I'm going to, by inverse, to create AC voltage.
Okay.
So I think it's better to think in terms of the AC voltages rather than DC effect. Also, if you look at this final conclusion, so this current source depends upon the derivative of magnetization. Okay? So the magnetization has to be oscillating. Then only you will get this current source. Otherwise, there is no current. So you need to think in terms of the AC effect only.
Okay. Shubhankar, you can ask your question.
Okay, so I think we are already quite over time. But one quick question, Ashwin. So this cobalt iron boron, what you are depositing, is it anisotropic? Because usually what we grow is just isotropic.
Okay, so this is not deposited by me actually. So this stack was deposited in AIST.
Okay.
And you can see that they have also put a thin layer of iridium here.
Okay.
So essentially, they found out that if you put some kind of a dusting layer of iridium, that enhances the VCME effect. So that's why if you look at this VCME coefficient, it is quite large. Okay, so otherwise it could have been like 10, but because of that special dusting layer of iridium, it has increased.
Iron layer of 0.2 nanometer. That's also like a dusting layer, isn't it?
Yeah, I think so. Yeah. So I think this is something that structure that they have optimized, and this is what they have found works very well.
So the sample is finally like perpendicularly magnetized, or what?
No, it is in-plane magnetized.
Okay.
But you need only 400 oersted to make it perpendicularly magnetized.
Okay, so it is probably quite around to the spin reorientation transition region.
Right, yes.
Okay. Okay.
So essentially, if you look at this curve, the fact that this is decreasing, this shows that the sample in plane is easy axis.
Yeah.
So if the in plane was hard axis, this curve would have gone up.
Yeah, you're right. Okay. Thank you. So thank you so much, Ashwin, for your excellent lecture. We all enjoyed it.
Thank you.
And I'd like to thank all the speakers again for giving really wonderful lectures. Are there more lecture, by the way? I think no.
Thank you, Shivankar, for chairing
Yes.
this session.
Yeah, thank you, Pranay, for giving this.
This session is now closed, but we'll have another session at 5 o'clock. So we have a break, but this break is for the poster session. In case you want to attend the posters of other sessions, because our poster session is for this symposium is tomorrow.
Okay. We'll take a small break. Thank you so much.
Yes.
Okay, so we'll meet at 5 o'clock.
Yes, thank you. Bye.
Bye-bye.
Thank you.
Thank you. Bye.
Hello, Professor Dill. Yeah, if you want to taste, you can maybe do the tasting now. We'll be starting.
So if I just go to my presentation,
and you have to click that share below.
Yeah, I'm just finding the appropriate thing. Just one moment. The share is okay. Let me see. It has some problem. It won't let me share. So I need something out. Okay.
Can you see the share button below?
Yeah, it's grayed out. So I've just gone to my settings, and it's telling me now that I can change the settings, but Cisco systems, I need to restart the software. Will this be running without anyone there? So can I? This link is still running. So if I quit the software, I can come back.
Yes, it will be running.
Okay, thank you. Right. So I'm.
Himanshu? Hello. Hello. Yes, we are seeing your screen now, but your audio is muted. Okay, yeah, it's coming at the full screen. Oh, you can see it clearly. But somehow you are muted. I think you can unmute and yeah, it's working fine. But I cannot hear you. Somewhere there should be a way to unmute. Cannot hear. I think you have to go down in that WebEx and click unmute. Your screen is visible. You can see your screen. Everything work fine. I think
How's that? Hear me?
now now we can hear you. Yeah.
Yeah.
Somehow you muted. I don't know why.
Yeah, no, it was, and the problem I've had is it wasn't clear. It's not off the top of the screen. So yeah. So anyway, how are you, and how's your young family?
Yeah, we're fine.
And the situation in
Yeah.
India is not so good, I think.
Yeah, it's in Delhi we have third wave of COVID right now, and
Yeah.
we are probably at the peak of the third wave.
Okay. Yeah, we're going through a second wave, which is we're possibly coming off the peak. Yeah.
Hi.
Hello.
Hello, Professor Chaudhary. He's the chair
Hi.
of our session.
Okay.
Hello.
Hello. Very nice to meet you.
Same here. How are you?
Very well, thank you. Yes, I was just comparing notes between COVID in the UK and COVID in India. So
yeah.
The UK
It's more or
government,
less same.
Yeah, the UK government has not handled it very well, I think. So we have a very high number of cases. Okay, but it's improving now. Yeah.
Okay. In India also we are witnessing third wave in Delhi particularly.
Yeah.
And this wave is much worse than the previous two cycles.
Yeah.
But I guess at several places the things are identical. Yeah.
Yeah. Yeah. But I think some countries have done better, handled it better. I think
sure.
South Korea and New Zealand and maybe Germany as well. But the UK, Brazil, USA, maybe India have not handled it so well, I think. But it's very difficult. Yeah. Yeah. But are you back in? You can go to work normal? You can go to your lab? Everything is normal for work?
And, only the research scholars are permitted to come to the institute. And other students from masters and BTechs, they are not permitted as of now.
Okay.
Even for PhD also, the recent entry students are not allowed to enter in the campus.
Okay.
Because we have to maintain distancing and the chance that it can reoccur rapidly if we allow all students.
Yeah. Yeah.
So this has been in the case since past 2-3 months.
Okay. So we've been able to get into our research labs, students since June, but we have a small number of undergraduates can come in for some teaching, some laboratory work, and for some tutorials and problems classes. They can come into the department, but we don't have any lectures. The lectures are all done remotely like this, and everything is pre. Yeah.
But you mentioned tutorials in person, right?
Yeah.
Tutorials in person.
Yeah. So socially distanced, people are wearing a mask, and they're 2 meters apart, and the number of people we have them in a very big room, so it looks really crazy. You know, you have 6 people in the tutorial. Yeah. Professor at the front.
The group size is small in tutorial. Perhaps by maintaining distance, it is safe. But I think finite risk is there, even there also, being closed room.
Yeah, yeah. So we where we can, we have ventilation. We open we worry about the ventilation. We have the windows open, but this time of year it's very cool. So
quite challenging.
Yeah. Anyway, so you're going to introduce me today, are you?
Sure. Yeah, Pranav has shared some information with me, and in fact, I remember when you were here in India, I think 3 years back or so. You gave a talk here. So
I think we met.
Information.
Yeah, we did meet, I think, didn't we?
Yes.
Yeah, I remember. Yeah, you look familiar to me.
Thank you. So there are 2 talks in the sessions only. I think yours is invited, and follow-up is a oral presentation, 15 minutes.
Yeah.
And I think 18 hours starting, we have a evening lecture. But now, where is this lecture? So it is a common link for everyone?
Yeah, that one is evening lecture in live stream on YouTube.
Okay.
Yeah, I think it's only in the, but you can also join via WebEx, but that link, I think it is not, I don't have that link with me.
I'm just going to turn my screen sharing off. Is it still sharing at the moment?
Yeah, it is still sharing.
So I'm going to turn that off, if I can.
So I
don't know how. Stop sharing. So it's and I would like to try and share it again, just to make sure it still works, and then I'll stop sharing. Okay, if that's okay.
Yeah.
Okay, is that? You can see that?
Yeah, we can see
Yes.
that.
Okay, perfect. I'm going to stop sharing that now, and I'll share it at 5 p.m. or five minutes.
Okay.
Yeah.
Just yeah.
So you can have some tea or coffee and then return
Yeah.
over.
Okay.
Yeah. So
Half an hour.
I was going to take a quick coffee break, go through my talk briefly, and then come back in half an hour. Okay.
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 Then.
Thank you.
See you.
Bye.
Thank you for sorting this out. It's great. It works. Everything is smooth apart from me. So yes, thank you very much. Okay.
Okay.
See you.
Bye.
Bye.
See you after half an hour. Okay. Bye.
Bye.
So we can connect after half an hour. If you want, you can disconnect. Okay.
Yeah. Because this link was not working in morning. Only I think.
There was some real issues actually. We had to wait almost 20 minutes before the link started working.
Okay.
But right now this is also live stream on YouTube, so maybe we should not talk here.
Yes, I was actually seeing that. Okay, I think we can then come back after 20 minutes or so, 25
Okay.
minutes, 4:55, just to see everything's okay. Okay then.
Hello. Professor Chaudhary, are you around?
Hello. Hello, I'm around.
Okay. So maybe Professor Atkinson, are you around? I can see him. So with 3 minutes we'll start.
Okay.
Hello.
Yeah. Yeah.
Hello.
Professor Atkinson is around.
So you here you see only very few participants, but actually this is embedded in another site, or the main conference site, where all the participants are able to watch this live, and they can ask questions which will appear here in the chat window.
Okay.
This is just for information, in case you are wondering why there are only few people here.
Yeah. Saroj is there.
Yeah, I think he forgot to log out.
Huh? And Professor
He's
Komi
there,
is
but
also there. Himanshu. Yeah. Okay.
okay, maybe you can, Professor Chaudhary, you can start introducing the
Okay.
speaker, and we can
Okay.
start.
Okay. So I welcome to the participant for this symposium on spintonic devices for memory and computing. I understand this is a third session of the first day of symposium, and I have the privilege to chair the session. And in this session, there are two presentations. The first one is an invited lecture from Professor Dell Atkinson, and it's a 45-minute lecture, and it will be followed by the second contributor presentation by another speaker from KIT Japan, Utkarsh. And to begin with, I would say that I have the honor to introduce the speaker, Professor Dell Atkinson. I welcome you for the symposium. Professor Dell Atkinson is a Royal Society Industry Fellow, and he's a full professor at Durham University since 2014. He has been appointed as an inaugural Sir Gareth Roberts Professor of Applied Physics in April 2017, when it was began at Durham University, and recently he has taken up as a role of head of the condensed matter physics division at Durham University. Professor Atkinson has a wide variety of research skills and experience in both academia and industry, and this expertise extends over more than 2 decades. And he has worked extensively in the area of magnetic materials, thin films, thin film metal semiconductor oxides for flexible electronics, and nanocomposite pressure sensitive inks for sensing applications, among others. His work is extensively published in numerous papers of very high international repute, and these include Nature, Science.
Professor Chaudhary, you got muted somehow.
Oh, I'm sorry. So,
just for the final part, I think your last sentence.
Yeah, he has 4 patents to his credits, and currently Professor Atkinson work focuses on flexible spintronics, spin orbit torques, and microwave properties of magnetic materials. And today he is going to deliver this invited lecture on spintronics for integration with the flexible electronics. Professor Dell Atkinson, you may have 40 minutes for your talk, and I would request you that reserve 2-3 minutes time for taking some questions following this lecture. Professor Del Atkinson.
Thank you very much. Firstly, can everybody hear me okay?
Yes, yes, we can hear you.
Okay, so I'm going to share my screen. I hope this works. I did test before. Yeah. Okay, so people can see my screen?
Yeah, it is visible. Please, go ahead.
Is it full screen now?
Yeah, it is full screen.
Okay, so good afternoon for those of you east of Greenwich, and good morning for those of you who are west of the Greenwich timeline. So it's still the morning in the UK here for me. Thank you, Professor, for your very kind words of introduction. And I would like to thank Professor Maduli and the organizers for inviting me to speak at this event, which is about emerging electronics. And this event, as I said, is about emerging electronics. It's notable that many of the talks in the other sessions are about the rapidly developing field of flexible electronics. And so what I wanted to do today, I would like to focus not so much on the details of the spintronics research that I do, but want to highlight the opportunities that spintronics has in flexible electronic applications. So how we can use spintronics applied to this exciting new development of flexible electronics. So I would like to tell you about the opportunities, but I'd also like to raise some of the challenges and the issues that spintronics faces in the integration of that. Okay, but first, we continue in exceptional times. So I'm sitting here in Durham, and if you know the United Kingdom, here is London, and Durham is about 350 kilometers north of London. And Durham is a very beautiful historical city. It's a UNESCO World Heritage City. So if you're traveling to the UK, you should, if you have the opportunity, come to visit Durham. It's a very beautiful city. I work at Durham University. The university is also a very nice, highly ranked university, both nationally and internationally, particularly for physics. Okay, so now let's get back to the science. Well, let's make a start on the science. Of course, we're never working alone, and I'm representing a lot of people here. I get the opportunity to present this talk, but I have my colleagues who help me with the supervision and the management of the research in Durham. I have postdocs in Durham, PhD students in Durham, and we have various collaborators. Within this talk, I would particularly like to thank my collaborator, Shubhankar Vedanta at Icee, and particularly within that, the results I'll be discussing today, examples of the results are coming from my PhD students, and also the help that I got from Sugata and Srijani in Icee when I was visiting there in 2017. I would also like to thank Tom Hayes at Warwick University and my colleagues at Porto as well for some of the work that they've done, which contributes to this talk. So, returning to the science, with that in mind, what I would like to discuss is the opportunities and the challenges for spintronics. So what is the outline of the talk? We hear a lot about flexible electronics, but I'd just like to give a very brief introduction to what we mean and what we understand by flexible electronics. So if you're not familiar with it, then you have the opportunity to understand what that means, and then that will give you the opportunity to see where spintronics can fit within that area of technology. I'll then go on to talk about some of the opportunities for spintronics. I mean, spintronics is particularly good for making highly sensitive sensors. We can measure magnetic field. If you have a temperature dependence, you can create a temperature dependent sensor. We know a lot of magnetic materials are sensitive to stress, so you can create sensitive stress sensing as well. And of course, in electronics, we need processing, but we also need some memory. And flexible and spintronics provides us with a very nice range of real, robust, non-volatile magnetic memories, MRAM, such as MRAM. However, the spintronics we have at the moment is largely based on ultra-flat silicon or silicon dioxide-based substrates. It's linked with integrated with CMOS, etc. The substrates in those cases are very, very smooth, and we have issues associated with integrating spintronics with the flexible electronic materials themselves, or the substrates themselves. There are a range of challenges, and I'd like to talk through some of those challenges as well. When it comes to the materials challenges, I mentioned the substrates. There are many challenges. I would like to talk about substrates, and particularly the difficulties of flexible substrates in terms of spin transport, which includes damping. I'm thinking about spin pumping in this case. Interfacial DMI, which we know is critical, for example, with chiral domain walls, and also with the development of interfacially introduced skyrmiols. Proximity-induced magnetization is also really sensitive to the structure at interfaces. So if you move from a rigid, ultra-flat substrate to a flexible but perhaps more rougher interface, then you will potentially change the proximity-induced magnetization. The role of proximity-induced magnetization is still in spintronics is still a subject of debate. Some people have said it has no relationship at all to spin Hall magnetoresistance. Other people say it's important. Whether it plays a role in spin transport more generally across interfaces is not yet fully established. There are arguments on both sides of that. So I just wanted to give you an example where other people have suggested DMI and proximity-induced magnetization are linked together. I want to show you I want to give you an example of that and show you that we have to worry about these things when we move to flexible substrates. Okay. And so those previous examples of the challenges, those are coming from existing work, so they're not necessarily on flexibles themselves. What I would like to do is demonstrate some of the things that we do see when we make materials. We make materials for spintronics on flexible substrates. And the things I'd like to talk about in that case is the development of perpendicular magnetic anisotropy, the development of anomalous Hall effect, and also what's critical for many applications in spintronics is the smooth propagation of domain walls. We think about if we think about DMI and we think about trying to measure the Dalichinsky-Murai interaction with domain walls, we need that smooth propagation of domain walls. And if we have applications of devices based on the propagation of domain walls, we need those domain walls to move smoothly. So we need to understand what are the magnetization behavior, what is the magnetization behavior looking like on flexible substrates compared to our previously very smooth, rigid substrates. So those are the topics I'll be covering today. So I'd like to start with an introduction to the flexible electronics themselves. So the two images you're looking at now, what you can see are a series of discrete electronic components on this, and they're on a flexible substrate. But in both cases, this is not really strictly what we mean by flexible electronics. These circuits are flexible and they can be deployed in, you can change the form factor of the object, but the electronics themselves are all based on silicon and they're robust, they're rigid silicon materials. This was the first kind of step towards flexible electronics. This has been around for many, many decades now, but this is not what people really understand and mean by flexible electronics. What they really mean is the direct building of electronic components and electronic functionality into flexible substrates. So here at the bottom, this is some organic light emitting diodes that have been made on using a roll-to-roll process, a flexible process. In this case, this is flexible electronics, but actually in these cases, this is often printable materials. So you're using printable functional materials. That would be printable conducting materials, printable semiconducting materials, printable organic light emitting materials. So in these cases, when we talk about the printables, we have we often we're working with organics. We're working with things which are solvent based, and you can print them using effectively conventional inkjet type printing processes. I think in reality that there will be big challenges for ever integrating spintronics into these roll-to-roll flexible printable electronics, but that is a challenge for the community to look at, and that's one of the reasons I want to highlight today. There are opportunities. If you see opportunities, we should be doing research in this area. The other thing I would like to talk about, and this is work that I'm involved with, actually, not all flexible electronics is done on this roll-to-roll basis. There are companies who are taking flexible substrates, but they put them onto a rigid platter. So in this case, what you're seeing here is that this is a wafer of polymer that was supported on a glass substrate, and all of the semiconductor processes you would do for patterning and lithography, etc., those are all done on this flexible substrate. The materials are then deposited by conventional electronic processes like sputtering or thermal evaporation. And in fact, in this case, the electronic material is, which I'm coming on to in a moment, the electronic material is directly sputtered onto these substrates and it's patterned using photolithography. This is a true flexible electronic design, and this is where we really have the potential for integrating spintronics, because if you can design spintronic devices and then integrate them, instead of integrating them with silicon as you would in conventional CMOS electronics, you integrate them with the electronic circuitry, which is directly thin film electronic circuits directly spotted onto these surfaces. Then we have the opportunity for integrating spintronics, thin film spintronics, into flexible electronics. And I think that's where there's a big opportunity. And I'm saying this, there is already probably more than a decade of work going on where people have been looking at introducing different aspects of spintronics. This is not completely new, but what I'm saying is it's a really a nice and large opportunity. So just as an aside, those flexible electronic materials, previously we talked about silicon, and silicon is very well known, and it's long dominated the electronics industry, and it will do so in the future forever. However, there are opportunities for other materials, and these are the metal oxide semiconductors. These are already being very widely used in transparent transistors, the indium gallium zinc oxide family of materials, which were invented and developed by the Nomura and Hosono group. They did a very nice review of this about 10 years ago, and we've also been working in this area, and we also reviewed this, but we were looking more generally at metal oxide semiconductors and the device structures as well. So this is an established established science. The semiconductor stuff is well established. There are companies developing these things. There are products out there already. So what it's a case of is bringing some spintronics and beginning to integrate into those material systems. Of course, the applications are very exciting, and applications are very wide-ranging. So you may, for example, want to have a flexible material which is flexible in the sense that you make it as a flat surface, but then you curve it and then it becomes fixed, as in this example here, which is it's an auto zoom. It has all electronics in it for zooming and for a camera integrated within those glasses. There's sensing technology in a flexible substrate, which would obviously, in this case, you can see would go into a shoe. So it's able to detect pressure patterns when people are walking to look for disabilities and issues associated with how people are actually walking. Of course, there's been a lot of noise and a huge amount of activity with flexible display screen technology. And also here, as you see, flexible lighting. These may be flexible in the sense of needing to be moved, opened and closed, and we know that there are issues associated with repeated use of that, or it may be that you need to form it into a complicated shape. So it's flexible in the sense that you make it and form it once. But for all of these applications, you have electronics, and those electronics need processing. So you need the transistors, and also, of course, if you're processing information, you need to save information. So we need memory as well. Many of these applications, such as this shoe here, are also looking for sensors as well. So if you can make a pressure-sensitive sensor, then maybe, which is magnetic-based, maybe then you have an opportunity for integrating spintronics into an application such as this. But the largest application for flexible electronics is likely to be the Internet of Things. What do I mean by the Internet of Things? I think we all have heard of it. It really describes a network of physical objects, things that are embedded with sensors, with software and other technology for the purpose of connecting and exchanging data with other devices. And the thing about the Internet of Things is we want to connect ever smaller, ever cheaper, and ever less, and ever less technological devices. So we will be needing very low cost electronics. And in order to do that, we need flexible electronics. So flexible electronics, I'm suggesting, could benefit from spintronics. The Internet of Things offers a huge potential. This is some research just showing the volume in terms of the total revenues, and we're in the hundreds of millions of dollars revenue by the time we get into the mid-2020s associated with flexible electronics. And what we should be thinking is we can integrate spintronics where that's appropriate as well. Okay. So that's the driver, I think, for why we should be interested. And what we need is, as I said, we need electronics. So we need spintronics coming in where we need data storage. We need spintronics coming in where we need to process data if we do magnetic logic. We need spintronics technology for sensing. And we can do all of those things. We know we can do them on silicon. Some of those things have been demonstrated on polymeric substrates. We need to demonstrate these and integrate them with existing flexible electronic circuits. So that's also happening, and that is the opportunity for spintronics. There was a very nice paper by Denis Makarov and his colleagues way back in 2016, reviewing what he calls shapeable magnetoelectronics, looking at exactly this problem. And he identified, again, a whole range of applications where we can see potentially magnetic technology, magnetic thin film technology, spintronic technology coming in to the application of some of these materials here. And there's a whole wide range of things. There's thermoelectric, so we have spin-Seebeck effect. Maybe there's some opportunities there. Wireless transmission, well, maybe we can use high-frequency behavior of thin film magnetic materials to help with either absorption or screening of materials, etc. And of course, magnetic sensing for position, magnetic sensing for magnetic field. There are a whole range of options where spintronics could join with the existing sensing technologies and the existing electronics technologies that are already on flexible electronics. It's an exciting and dynamic field. So those are the applications in general. And I think if we look, as I said, just to summarize, we know spintronics is very good at sensing. We know spintronics is very good at memory, either typical parallel memory like magnetic random access memory. I don't think we're going to see, maybe we will see racetrack memory, but we have serial memory, some shift register type applications may be possible as well. We don't always need a huge amount of memory or a huge amount of sensor technology to be useful. What we need is to be functional and it to be possible to work in collaboration with flexible electronics. So magnetic memory is probably the big one, and the work I'm doing with companies is interested in magnetic memory for flexible electronics. Magnetic logic is another possibility, although most of these companies are developing thin film semiconductor technology to do the logic, do the processing. So magnetic logic is probably less relevant. Thin film inductors, they already exist. People already make those on flexibles, but actually you can think about thin film inductors and thin film antennas for energy harvesting and energy conversion as well. So that would be helpful. So it's not strictly spintronics, but it's thin film magnetics. And similarly, of course, we know that electronics can be sensitive to RF radiation. So we know, for example, if we make spintronic devices, if we make spintronic layers of multi-layers, we can increase the absorption and the damping in the gigahertz regime. So maybe there are opportunities for RF screening of materials as well, which would be very nice and very helpful. As I mentioned, there are people doing and demonstrating practical things. They tend to be done in isolation at the moment. What we need to see is people integrating with flexible electronics. This is a very nice paper that demonstrated that you can do spin orbit torque switching in magnetic materials. The problem with this kind of application is you still need very, very large in-plane magnetic fields in order to create the switching event. So from an applications point of view, whilst this demonstrates the principle, it wouldn't necessarily be directly relevant to an application. And what I want to do is to come on to talk about some of the challenges now that we face. So we have opportunities, and some spintronics has been demonstrated that we can transfer some of these ideas and put them into flexible electronics, but there are challenges, and I'd like to summarize and discuss those challenges in the remainder of this talk. So the challenges are interesting. The first thing we need to do is make sure that whatever we do with our spintronics, the materials are compatible with the materials and the production processes used in the other parts of the flexible electronics processing. And these could be many. If you're doing a roll-to-roll printable electronics, then you would need to have some form of printable spintronic device. This would be a very big challenge. If you're using more like thin, flexible flexible substrates as wafers, and you're doing conventional lithography, etc., then you need to map onto those production processes, and thin film deposition works very well in those cases. However, the substrates for flexible electronics are typically polymeric substrates. People will probably be very familiar with Kapton. Kapton is a polyimide. It's a very commonly used in the electronics industry for putting down making simple flexible interconnects. You put conductors on top of it and it's bendable and flexible. It has good, reliable flexing properties. Polyethylene naphthalate is another substrate material that's been used by people, and that's also been very quite heavily used in flexible electronics. So you need to make sure that your materials are compatible with those substrates. You know, if you get delamination, then you have problems, for example. But a big problem for those substrates is the heat treatment. If you tell me that you need a heat treatment of 500 degrees C to develop an anisotropy, or you need to go to 600 or 400 degrees C to develop an exchange bias, or you need to go above the amorphous recrystallization temperature to change the amorphous material into a crystalline material, and you're going above 300 degrees C, if these materials are built on flexible polymeric substrates, these processes are probably not going to be compatible. There may be some substrates that can work at higher temperatures. You may push the substrates to slightly higher temperatures, but as a general principle, any heat treatments that you might need, whether for changing the magnetic properties or developing anisotropies, etc., they need to be achieved at low temperatures. So this is a big constraint. This is something that is a big challenge for a lot of activities. This is different to what you'll have with CMOS. CMOS, you can go to higher temperatures, and you're only worried when you start getting really above 500 degrees C or higher. In this case, we're worried when we go above 300 degrees C. The other huge constraint, the really big challenge, is that these applications are likely to be very low cost. That means you need very cheap designs. So you want cheaper materials and you want cheap processes. When it comes to materials and processes and designs, what this means is you need to think about the number of layers that you have. So if you think about a typical TMR or GMR structure, we think of it as 3 layers of material. We have 2 magnetic layers and then some interlayer of a conductor or an insulator. In reality, there are many, many, many layers of different materials. This is really challenging. One company I'm familiar with, they have in total 5 materials they can work with at one time. So if 2 or 3 of these are the semiconductors and the electrical contact materials, you have maybe a couple of materials that you can play with. So you have to think smart in order to make these things really integratable with flexible electronics. You can make a 26-layer device on flexible and it may work, but if it's not compatible with the processes for integration with flexible electronics, then it's not really a very suitable device. So actually, this opens up new challenges, but to make things simple. So we always think, if you say, I need to make a sensor, then okay, I'll make a giant magnetoresistor. If I need to make a memory cell, I'll make a tunneling magnetoresistor. Actually, you can think in completely different ways. If you need to make a memory cell, you need to read out something. If you use the anomalous Hall effect and you have a perpendicular material, you can measure the anomalous Hall effect, and that will tell you whether the magnetization is pointing up or pointing down. Of course, the sensitivity isn't there compared to GMR or TMR, but it may be a practical solution for flexible electronics. Anything you make, of course, as well, needs to be robust. So you will always see these pictures of people bending their substrates. If you make a fantastic spintronic device, but you can't flex it or deform it and bring it back to its original behavior, it's not necessarily very suitable. So it needs to be robust in the application. If it's something you're going to be flexing and it's a bending sensor, for example, you need to make sure that when you bend it 10,000 times, it's functional after that. Now, the biggest challenge, and the thing I would like to focus on now in the last 10 minutes or so, is surface roughness of those flexible substrates. This is probably the biggest issue, I would say. Because, as you know, in spintronics, much of thin film magnetism and spintronic physics depends on the interfaces, and it depends on ultra-thin films. If we think about outer plane cobalt films, we're often thinking about sub-nanometer levels of cobalt. If we think about an alumina oxide barrier in a TMR structure, we're talking about sub-nanometer level of thickness of those materials. So we're dealing generally with very, very, very thin materials. So if we have a rough substrate, we need to worry about how that substrate will affect the magnetization behaviors and the physics that we get. That's what I'd like to talk about now. So some of the challenges, the surface roughness. If we look at silicon, if we look at this atomic force microscopy image, you can see there is some roughness. It's it's very high frequency roughness, but this is a very, very smooth material. This is silicon dioxide on top of a silicon wafer, and it's very, very smooth. And when we make substrates on this, when we make spintronic devices on this, that roughness is not usually a problem. This is polyethylene naphthalate. This is, and you can see the structure is very different. You can see some striations running along the length, and this is quite common because of the way it's manufactured, part of the manufacturing process. And then you see it has these large scale features. Individually in local areas, it can be very smooth, but there are large scale features. So the substrate topography is very different from the substrate topography of conventional rigid silicon dioxide substrates. And if we look at the cross sections, you'll see all this high frequency but very, very low noise. Here you see these large features up and down within the material. And this is not just for polyethylene naphthalate. There's an example here. So this is polyimide here, this is Kapton. This is a flexible electronic grade of Kapton that we're talking about here. And you can see the roughness here, the RMS, which is the average roughness. And here is the silicon at the bottom, and it's typically a quarter of a nanometer or something, a couple of hundred angstroms at the most, typically. And it's really very constant and uniform as well. Whereas if you look in different areas on a polymeric substrate, actually you see big variations. So these error bars are giving us some indication of the variability as well. So it's not just that the roughness is large, but the region to region variability is more significant than it would be on another substrate. So we need to worry about that. So as I said, we need to be compatible with fabrication processes such as annealing temperature. We need to focus on low-cost simplified materials. But one benefit is in most flexible electronics, the feature sizes are not very small. We may be dealing with micron scale features in cutting edge CMOS now, where sub 10 nanometer feature sizes. In flexible electronics, the features are usually much bigger than this. The lithography is a much larger scale. If you're doing printable electronics, again, the feature sizes are much larger because you're doing the printing. So we're not constrained in the same way by the feature sizes. So that is a benefit that we have when we're trying to make some of these devices. Okay, so interface physics in spintronics. Of course, there are many. Spin transport, damping, which I would put into spin transport as well, interfacial DMI, proximity-induced magnetization. So let's look at the first of those. Magnetization damping, if we have a system like this where we have a ferromagnet and we're pumping spins from a ferromagnet into a non-magnetic layer, there's spin transport across that interface. There's also spin transport in the situation where we have the spin Hall effect, or from rush bar, we can generate spin orbit torques. And again, in this case, we move the pure spin current is propagating, in this case, from the heavy metal into the ferromagnet. In the case of damping, it's moving from the ferromagnet into the heavy metal. But we need to understand this. Does this behave the same way when we transfer from rigid substrate to polymeric substrate? We know this is a problem. So here, it really depends on the details of the interface, and the damping depends on this spin mixing conductance here. And I can show you, I don't want to focus too much on the details, but the important thing is, if we change the structure of this interface between the ferromagnet and the copper or the iridium, if we change that interface from an FCC-FCC interface to a HCP-FCC interface, we see a huge difference depending on the crystal, on the interfacial structure. That would be a problem when we transfer to spintronics. So this is just showing the change in the crystal structure. When we're very thin, we have a FCC crystal structure. When we're very thick, we have HCP crystal structure, and we can see the atomic spacing here. And we change when we're very, very thin. So 1/T here. When we're very thin, we have face-centered cubic structure, and when we're much thicker, we have an interface which is hexagonal closed pack. Oh. If we go to the results for this, and we look at those interfaces, I beg your pardon, we have 4 interfaces. We have FCC onto copper, we have FCC cobalt onto iridium, we have HCP cobalt onto copper, we have HCC cobalt onto iridium. So we have 4 interfaces. And if we look, here is HCP cobalt onto copper, HCP cobalt onto iridium. And if we look at the result for that, you see there's almost no difference in the spin mixing conductance. So the ability to propagate spin across that interface doesn't really make much difference. However, if we look at FCC cobalt onto copper or FCC cobalt onto iridium, we really see a huge difference. So you can compare red and green in both cases. What we can see is that when we very subtly change the interface, in this case by changing the crystal structure, we massively change the spin mixing conductance. So we change the ability to propagate spins across that interface. So the nature of the interface is really, really critical. So anything that we try to do on flexible substrates, we need to make sure that we can control the interface to allow good spin transport across the interface. If that interface is very rough, then we would have a problem. So we need to worry about that, okay? We see some big effects. This was published a long time ago, and if you want more details, feel free to go to this paper. Also, so I was talking specifically about FCC HCP interface there. Even if we make 2 layers, so here is platinum with cobalt on top and cobalt with platinum on top. This is the spin mixing conductance, and you see the spin mixing conductance is different just because of the detail of the interface. When you change the interface, you change you very subtly change the detail of the spin transport across that interface. So if you move from a rigid substrate to a flexible substrate, you could have a problem with that. You may say, oh, but I work with amorphous materials, and amorphous materials, it doesn't matter. Well, actually it does. This is platinum with cobalt grown on top, amorphous cobalt iron boron, and then we have cobalt iron boron with platinum on the top. And again, you can see that we see big differences in the spin mixing conductance between the different interfaces. These are nominally identical structures, but actually you get different spin transport depending just on which way around it is. And that is related to the detail at the interface, the local detail at the interface. Proximity magnetization and the interfacial Dalizinski-Mariah interaction also depend on that. That's quite important. So if we take an interface here and we add some iridium or gold to this interface, we can actually change the interface. We should change the proximity polarization, and we should change the Dalizinski-Mariah interaction, and I can demonstrate that's what happens. So when we look at the magnetization in the platinum, this is the proximity polarization using resonant X-rays. This is a kind of XMCD technique, but in reflectivity. So we're doing reflection. And you can see in the graph here This is magnetic contrast. This tells us about the magnetic signal coming from the platinum. And what we see is that when we introduce platinum, and when we introduce a spacer layer into this structure, here is the analysis. This is the magnetic signal in the platinum. You see it's maximum at the interface, maximum at this interface. This is cobalt. If we introduce some detail at the interface, you see that the magnetization of the platinum, the proximity-induced magnetization goes down a lot, very, very quickly, just by disturbing the interface, by putting in a few angstroms of gold or of iridium at the interface. We bring down this proximity polarization. So the proximity moment in the platinum goes from this to this. And as I said at the beginning, there is some evidence that proximity polarization may play a role also in spin transport. So this would be something else we have to worry about. There's also a question of whether it plays a role in Dalizinski-Mariah interaction. So with the same samples, we can look at the Dalizinski-Mariah interaction, and we can quantify that using Brillouin light scattering. So here, there's almost no gold in the system, and you see Stokes and anti-Stokes here. And we've flipped these curves over, so you can see there's no offset due to DMI in this case. That's because we have two layers. We have DMI coming from the bottom layer and from the top layer. If we introduce some gold to the top layer, we will reduce the DMI in the top layer, and we will see DMI from the bottom layer. And that's what we see. So as we introduce more gold, the DMI becomes apparent, and you see it here. Okay? And what we conclude from this is that actually the interface is very sensitive to DMI. The interface is very sensitive to proximity-induced moment. The interface is very sensitive to damping as well. And we need to worry about this and control this when we're making materials on flexible substrates. So let's look at some of those flexible substrates in the last couple of minutes. Perpendicular magnetic anisotropy, of course, we have interfacial perpendicular magnetic anisotropy. We know about this for a long time. It's arising from the surfaces, and you have symmetry breaking at the surface. You have a volume anisotropy and an interface term, which depends on the thickness. And typical materials are these cobalt platinum materials. These materials are ultra thin, typically less than 1 nanometer. If you get to 1 nanometer, that's on the thick side. These are the kind of materials that people are using in most spintronic devices. So you can see if we have substrate roughnesses which are of the order of 1 or 1.5 nanometers, then when you get into this regime, we have to worry about this. Okay? Can we make perpendicular anisotropy? Yeah. The other thing is maybe we need to think about other materials, and there are people interested in rare earth transition metals because they have bulk anisotropy. They don't rely on interfaces, so you can actually make these materials a few nanometers thick, or we make some of these materials 100 nanometers thick, and they have outer plane anisotropy. So you can use these materials, and we want to show that we can do these on flexible substrates. So that's what I'll talk about now. So here is a comparison of rigid silicon dioxide and polyethylene naphthalate. You can see in this case, we have a nice anisotropy developed, perpendicular anisotropy developed for the polyethylene naphthalate, while for the silicon, there's still no anisotropy, but we have very thick platinum in this case, 1 nanometer of platinum. Here is another example, and if we look, you can see the hysteresis loops. We're comparing polyethylene naphthalate substrate and polyimide with silicon. So the behavior is similar, but not identical. So it's good. We can get outer plane anisotropy, but it's not identical. There's another example here. This is platinum with MgO, and you can see in this case we have 5 nanometers of platinum at the bottom, and that matters. If you go for very thick layers of platinum, it can make a big difference. So if we compare, for example, platinum cobalt here or ruthenium cobalt here, what you can see is the silicon dioxide is always having a higher coercivity because the anisotropy is usually stronger. So we have higher coercivity, but the trend is the same. You see it goes up and then reaches some peak and comes down. This trend is well established. This is the coercivity, but it's an indication of the anisotropy as well. So we know we can establish this outer plane anisotropy. That's good. And we have a whole load of parameters you can see. So on silicon, you can see the thicknesses here and the average coercivity. So we can get very strong anisotropies when we're in this region here. You don't get such big anisotropies when you're in this region here. So let me just jump to my conclusion. 2 more slides, I beg your pardon. This is the anomalous Hall effect. You can see we have it on a polymer and not on polymer. And if I go finally we need to make sure we can propagate domain walls. And if you put domain walls on rigid substrates, you see very nice circular domains. We call them bubble domains, and they're expanding. These are some examples here. That doesn't happen, unfortunately. We get similar shape hysteresis loops, but the domains look very different. This is a polymer substrate. So if I just go back to this, you can see beautiful circular domains. The domains nucleate and then they expand. In this case, on polymeric materials, if I start this, you'll see the magnetization is reversing. And the behavior is much more complicated. The substrate is much more dominant in controlling the reversal. So if you were trying to make a domain wall device, this would be severely problematic for you. So that's not such good news. Here is the nice bubble domains you see on a rigid substrate. This is on polyethylene naphthalate, much more complicated structures. So in conclusion, what I'd like to say is I hope I've introduced these opportunities for spintronics for integration, particularly for sensors, also for memory devices. But I've highlighted some of the challenges as well. The substrate in particular is a challenge, the annealing temperatures that you can have. A lot of spintronics is about interfacial effects, and that is we can probably overcome most of those interfacial problems, but we have to worry about those interfacial effects for spin transport. And the magnetization reversal behavior is much more complicated when you make them on these flexible substrates. So that's not such good news. The interfacial effects is quite good news. The magnetization reversal behavior is not such good news. Thank you very much for your attention. Thank you.
Yeah, thank you, Dr. Del Atkinson, for the beautiful talk. Now the session is open for questions.
There is one question from a student, Avinash Chaurasia, is asking, in order to create a stack of the film, do you really need epitaxy of the film with the flexible substrate? If yes, what are the possible polymer substrates?
So if you're trying to do, I don't think molecular beam epitaxy would be convenient for this at all. So if you want to do something which is currently using epitaxy, then I don't think flexible substrates will be suitable. So that goes back to my very first point about it has to be, what you want to do with this spintronics has to be compatible with your material. So if your material is very, very perfectly structured, if you needed to do, for example, L10 phase on platinum, I don't think it would be possible. If you need to have something which is, if you need to have MgO, if you need to have crystalline MgO, I don't think that will be immediately compatible. That would be a big challenge. So the substrates are polymeric. The polymeric substrates are by their nature amorphous. If you could put some kind of seed layer onto the top of that, maybe with a seed layer or some kind of buffer layer, might allow you to do some molecular beam epitaxy, to do some epitaxial growth. But I don't think, as a general principle, epitaxy is very well aligned with flexible electronics.
Sure.
Yeah.
I have a quick question, Professor Atkinson. With regards to transport properties, is it possible to differentiate between the intergranular contribution as opposed to intragranular contribution? Because the transport properties depend very much on these two components. And for a flexible electronics, if you try to give a stress to the substrate, you would basically play with the intergranular contribution in the transport properties. Some kind of estimate in some properties, if anybody has done.
Yeah, so this would be, if you're talking about a grain to grain, then yes, of course, that you're modifying that, and if you flex your substrate, then the places where it will flex will be at the grain boundaries. If you have an amorphous material, if you have cobalt iron boron, for example, or a rare earth,
that is different.
then that would be different. But of course, it still changes the physical structure, and that will change the electronic structure. And if you change the electronic structure, then you will change some of the characteristics. So if you we see, for example, if we take a material with an outer plane anisotropy and we measure it, bending it or bending it the other way, we change the anisotropy. If we were measuring the resistance or the Hall effect, we will see a change in the Hall effect that we would measure in those cases. So that everything is sensitive to the flexibility of it. Yes.
Yeah, you nicely explained that aspect. Yes. Mudali, are there other questions from?
There is no other question. I just had this technical question. In the case of cobalt, when you vary the thicknesses, you see this phase change. How did you make X-ray measurements of very thin films? Because thinner films is very hard to get any signal. How did you, or was it synchronous based measurements?
You're talking about the crystallography measurement?
Yeah, where
Yes,
you have FCC to SCP transition.
Yeah. So we had to count it out. It is very difficult for those ultra thin layers. Yeah. So usually it's very difficult, but we counted it out, and we looked at the in plane diffraction, so you get a bigger signal from in plane diffraction.
Okay.
Yeah. If there are no question, then I can have last question. You talked about recovery in the talk. Recovery. I mean, after you flex the substrate, then there's recovery.
Yes.
Did anybody study about this damping constant before recovery, before flexing, and after flexing?
No, it's a good question. I haven't seen anybody looking at that yet. Most people have been going directly for devices rather than looking at some of the fundamental physics. So this would be an interesting area to study. If you could deposit these materials onto flexible and then study them, yeah, that would be interesting, I think.
Yeah, okay. So if there are no questions, let us thank the speaker, Professor Del Atkinson, for the beautiful talk on this spintronics for integration on flexible electronics. Thank you, Professor Del Atkinson.
Thank you very much.
Thank you.
So with this, we move to the next talk. This is an oral presentation from Mr. Utkarsh Shashank from KIT, Japan. And the title of the talk is High Charge to Spin Interconversion in Sulfur Implanted Platinum. Mr. Utkarsh Shashank.
Yes, we can see your screen. Please go to the full screen mode.
Hello, everyone. I'm Utkarsh Shashank, a PhD student from Kyushu Institute of Technology, Japan, and I belong to Fukuma Laboratory. The topic of my presentation is high charge to spin interconversion in sulfur implanted platinum. So, why is there a need of high charge to spin? Yes, sir. Am I audible?
Yeah. Yeah, please go on.
There was some delay, but it's working now. Please go ahead.
Okay. Is my screen visible, sir, the top part?
Yeah.
Why?
Yeah, it's visible, Utkarsh.
Okay, so why is there a necessity of high charge to spin conversion? The pre-existing magnetic RAM memory is based on a magnetic tunnel junction, which of course the revered professors already explained it to us. It basically consists of a fixed layer, which is a ferromagnet, and a free layer, which is also a ferromagnet. Now this tunnel barrier, the MGO or any tunnel barrier, is sandwiched between these two ferromagnets. Now it's based on spin transfer torque, in which we polarize magnetization in the fixed layer, and this further exerts a torque on the free layer. Now what it does is that the tunnel barrier that we have is sensitive, it's vulnerable, and maybe a few nanometers thick, So the repeated use of read and write path damages the tunnel barrier. So to overcome this, we have a spin orbit torque MRAM, in which we place a spin orbit coupling material below the free layer, which is a ferromagnet. What this spin orbit coupling material does is we drive a charge current. That charge current gets converted to a spin current, and that spin current exerts a torque on the free layer, which is used to switch the magnetization and record the data as 0 or 1. Since we use a different read and write path, there is fast writing, and we are also protecting this tunnel barrier. Now, I mentioned about this charge to spin conversion. There are various ways to do it, and one of the most popular ways is spin Hall effect. In spin Hall effect, we drive a charge current density through a heavy metal which has a higher spin orbit coupling. Now, what happens is that as we drive this charge current density, the upspin and downspin comes on the either sides of the heavy metal, and what happens is that this charge spin gets converted to spin current because of spin Hall effect. Now, one of the prerequisites is that the JS, JC, and sigma should be orthogonally perpendicular to each other for this spin Hall effect to happen. But I mentioned about this SOT MRAM. One of the prerequisites is that apart from having a high theta SH, what we should also have is that it shouldn't have a higher resistivity, because once it has a higher resistivity, it may lead to higher power consumption. So these materials have a high theta SH, but what they have is a higher resistivity. What is left is only platinum based alloys, which have low resistivity and also a very high theta SH. So we focused on platinum to maximize the theta SH further, where PT already has a high theta SH and a not so high resistivity. Previously, it has been modulated via oxidation by varying the deposition condition, and with the varying of conductivity, they can get a different theta SH. Third is by playing with the interface factor. And fourth, the most commonly used is by alloying, in which PT has been alloyed with various materials. Now, the crux of this thing is that not only a high theta SH is important, but it shouldn't have a high resistivity as well. Because these both combination, once we play with these both combinations, what we get is a higher spin Hall conductivity, which is required for switching mechanism. So on similar lines, we employed low energy sulfur ion implantation in platinum, in which we took a platinum heavy metal and covered it with oxide and allowed sulfur ions to pass through the oxide and reach the platinum. After that, we removed oxide via argon ion milling and grew permalloy on top via DC sputtering. Now, the purpose of oxide layer was because we wanted to protect this platinum from least perturbance, as oxide layer stops most of the sulfur ions, and the leftover sulfur ions is uniformly distributed in platinum. To study this theta SH, we have this charge to spin conversion, and to study that, there are various popular methods. So we employed spin torque ferromagnetic resonance, that is STFMR, and to know its on-Sager reciprocity, that is the spin to charge conversion, we used inverse spin Hall voltage measurements. So first I'll talk about STFMR. So in STFMR, we have a bilayer structure, a heavy metal ferromagnet. In this case, we have PTS and IFE. What we do is we drive an IRF current via signal generator. And what it does is that once we pass this IRF, it's basically a charge current density, which gets converted to spin current density via spin Hall effect. Now, what this JC, this charge current density has an Oersted field associated with it due to Ampere's law. And what they both collectively do is, like this JS, that is the spin current density, it exerts a damping like spin orbit torque. And this HRF exerts an Oersted field torque. Both damping like spin orbit torque and Oersted field torque collectively drive the magnetization precession in ferromagnet once the external magnetic field matches with the Larmor precession frequency of the ferromagnet. And this is recorded as a ferromagnetic resonance signal, which is Vmix, which is actually a product of the IRF current and the change in resistance due to anisotropic magnetoresistance. So for PTS NIFE and PT NIFE, we could obtain the V-mix spectra. For PTS and IFE, we could see a high clear symmetric signal as compared to PT and IFE. This high symmetric signal comes from the damping like spin orbit torque, which implies a higher JC to JS conversion, which can be seen in this LLG equation, the modified LLG equation. Now, to measure this charge to spin conversion, we employed the line shape analysis, which is using the symmetric and anti-symmetric components of the deconvoluted spectra to measure the theta SH. So for PT and IFE, we could see a spin Hall angle of 0.09. But whereas for PTS and IFE, we could see an approximately 3 times increase in theta SH from 0.09 to 0.27 at 300 Kelvin. But we performed this by varying, but we did this measurement for the angle of IRF and H external at a fixed 45 degree. So the question is, does line shape analysis at only one complete angle, on only one angle, gives the complete picture? So to understand this further, to know the complete picture, we performed in-plane angular STFR measurements in which we varied the angle between IRF and H external from 0 to 360. Now, for line shape analysis to be followed, there are two conditions. First is the mirror symmetry, in which the symmetric and anti-symmetric component, say at 40 degree, exactly reproduces at 180 minus 40, that is 140 degree. And the second is the two-fold symmetry, in which the symmetric and anti-symmetric at 40 degree exactly reproduces at 180 plus 40. So for PTS and IFE and PT and IFE, we could see that there was no break of symmetry of torques, and both mirror and two-fold symmetry was followed. This implies that we can apply line shape analysis to evaluate theta SH for such systems. Additionally, we also fitted the symmetric and anti-symmetric component to understand the torque symmetry. Now, we could get a cos phi sin 2 phi behavior, where this cos phi comes from the SHE induced torque, and the sin 2 phi behavior comes from the AMR. So, but there's a catch here, like the symmetric component in any STFMR signal may also have a spin pumping contribution, which was explained beautifully in the previous talks. So how to rule out the spin pumping contribution? How to be very sure that line shape is, the theta SH that we get from line shape is correct? So to rule out that spin pumping contribution, we perform line width modulation via DC biased STFMR measurement. It is same as STFMR measurement, except that we apply an additional IDC current along with IRF to modulate the line width DH. So, and based on the polarity of the IDC, we can get two different behaviors. So say for example, a negative minus 0.25, we could get a smaller line width delta H, which further increased for 0 milliampere and got further enhanced for 0.25 milliampere, which can be seen here that we have a smaller delta H, which goes on increasing at 0 and goes further increase at 0.25 milliampere. Once we change the external magnetic field H external, we can get an opposite behavior, which once we get both the behaviors, we can conclude that there is no heating effect, and this is purely a spin Hall effect kind of phenomenon. So for PT and IFE, we perform similar measurements, and by seeing the slope of effective damping versus charge current density, we could calculate a theta SH via line width. For PTS and IFE, we could get a theta SH of 0.35, which matched previously with our theta SH via line shape, almost matched, of 0.27. For PT and IFE, we could get a theta SH of 0.1, which almost matched with our theta SH via line shape. Now we got this high theta SH, but to understand this mechanism, we wanted to understand why is there an increase. So for that, we performed temperature dependent STFMR measurements, in which we measured this charge to spin conversion by varying the temperature from 10 Kelvin to 300 Kelvin. At 300 Kelvin, as I mentioned earlier, we got a 3 times increase in the theta SH, but the most interesting result came at 10 Kelvin, where we could see a clear 8 times increase in this theta SH value. Further, we plotted the spin Hall conductivity, that is sigma SH, as a function of electrical conductivity, as the longitudinal conductivity. So we could see an invariant behavior in which the theta SH was independent of sigma XX. Such an independent behavior implies that the phenomena is intrinsic spin Hall effect in the metal conduction regime. Furthermore, for PTS and IFE, we plotted sigma SH as a function of electrical conductivity, but now we could get a completely different behavior in which the spin Hall conductivity is no longer independent, but instead it scales as a factor of 1.7. Now, such a scaling of 1.6, 1.7 implies that the phenomena is still intrinsic spin Hall effect, but now it's in the dirty metal conduction regime. Also at 10 Kelvin, we obtained a very high spin Hall conductivity of 8.32 into 10 to the power 5, which is higher amongst PT and its reported derivatives. Such a high sigma SH can be useful in low power SOT MRAM switching. Now, after studying this charge to spin conversion, because we wanted to ensure the spin transparency, interface was smooth and everything. So we wanted to confirm this, that is there an Onsager reciprocity also. So to measure the spin to charge conversion, that is the opposite effect, we employed spin pumping inverse spin Hall voltage measurements, in which we drive a microwave current through this CPW. And because of this IRF gets converted to HRF. But now in ISHE measurements, we exert an out of plane HRF. Whereas in STFMR, it's in plane HRF. Once the precession starts in NIFE, the JS is pumped back to PTS, and this JS gets converted to JC via inverse spin Hall effect. This JC is measured in the form of an ISHE voltage. And for PT and IFE, we measured this ISHE voltage. But furthermore, for PTS and IFE, we could see a clear 3 times increase in the ISHE voltage signal. And by checking the mean of this spin pumping ISHE voltage, we could see an approximately 3 times increase in the spin to charge conversion as well. So the summary of our work is as follows. We designed a new spin Hall material, PTS, by using low energy, 12 kiloelectron-volt sulfur ion implantation in platinum. We obtained an 8 times increase of theta SH at 10 Kelvin and a 3 times increase of theta SH at 300 Kelvin. We obtained a very large spin Hall conductivity of 8.32 into 10 to the power 5, which is higher amongst PTS and its derivatives. And after confirming this charge to spin efficiency, we also confirmed the spin to charge conversion via spin pumping inverse spin Hall voltage measurements. Thank you for your kind attention.
Yeah, thank you, Utkarsh, for a very quick and clear talk.
Thank you. Thank you, sir.
Taking the time. Now it's open for questions from audience. Are there any questions, Pranav?
No.
Professor Atkinson would like to.
Yeah, I would like to ask a question. What's the percentage, the atomic percentage of sulfur in the platinum?
Yes. Thank you for your question, Professor. Yeah, so actually we did measure. So we used ELS measurements, and by using the Fourier transform, that's by using the intensity aspect ratio, we found that most of the sulfur ions stopped around here, and we found 10% of sulfur in platinum, which is that's why we optimized this everything, and we could see a uniform 10% sulfur.
Okay. So my next question would be, how would it depend upon the sulfur content? If you went to 20% sulfur or 5% sulfur, is that going to improve it again or make it worse? Is 10% optimized?
Yes. Actually, sir, this work will be an extension, and that's what we are working. It's hard to say now, but yeah, It's an interesting question, and yeah, probably the next step would be seeing a concentration dependent and possibly a thickness dependent to understand this more deeply, like how this could affect with the concentration, how the resistivity, because the most important parameter that we play with is the resistivity. Once the resistivity changes, you can change everything. So yeah, it's in the line, sir. But thanks for your question. But sorry, that's all I can say.
It's very nice work. If I may just have one more question, if that's okay, Chairman?
Yeah, please.
Yes,
Professor. So what exactly is the physics that's happening? Why is the sulfur doing this? Can you just explain again? Maybe I missed it at the beginning.
Yeah, actually, there could be two possible reasons. First is like what happens is once this resistivity increases in any in the heavy metal, it's no longer a metal conduction regime. It goes to the dirty metal conduction regime. I forgot the paper, but there's this very recent paper by Professor Zhu. He has gave a very nice graph in which he's explaining the shift as we move to higher resistivity. So what it happens is that once this scaling happens, like a scaling of 1.7, which is no longer dependent, it becomes a 1.7 scaling is there. So this implies that the phenomena is still intrinsic spin Hall effect. It isn't extrinsic or side jump. It's still intrinsic spin Hall effect, but it is still in the dirty metal conduction regime and not in the pure metal. So what could happen is possibly a charge scattering is enhanced at a lower temperature, and as a result of which there is a higher spin orbit coupling. But to give an exact pinpoint answer, I think we would need some band structure calculation, like which I'm not aware, sir. I'm like.
Thank you very much. It's nice work. Thank you very much for your answers.
Okay.
Yeah, one quick
my
question.
Yes.
Utkarsh, what is the criteria for choosing sulfur as a implanting ion?
Yeah. It's a very good question. Actually, what happened is we've been following the different groups, what they've been doing. So the first motivation was that we saw a natural oxidation of platinum, which is another most important thing is that in these things like for example platinum and gold, they both have a higher atomic number, which we know that the spin orbit coupling scales as a z to the power 4, like higher atomic number means higher spin orbit coupling. So this was already explored. What we wanted to explore was a lighter atom, say for example the chalcogens or the lighter elements group like oxygen, sulfur. So we wanted to understand, like, because there are based on these papers we could understand that not only the spin orbit coupling but the charge scattering and the way we can play with the interface also matters in increasing this final theta sh. So yeah, the work by Professor Achan could have been one of the motivations for us to proceed with sulfur as it falls in the same group.
Okay. I wish I could ask more questions, but I think due to time constraint, unfortunately we have to stop here. And because this is 10 past 18 and the other talk is, I think, has just begun.
Yeah. So I
I
think
would
we'll
like to,
stop here.
yeah. I would
And
like to thank both the speaker and yeah, Professor Mudli, you can take over.
Okay, thank you, Professor Chaudhary, for sharing this session. And that's the end of
My
the
pleasure.
Spintronics Symposium for today. And there is a plenary talk right now. And I have sent the YouTube link in the chat window. So you can follow that link and watch the plenary lecture by Benki Venkatesan from NUS, National University of Singapore. So that's all for now, and I think we'll have to close it.
Okay. So
thank you.
Thank you, Professor Atkinson and Mr. Utkarsh. Okay, we can
Thank you,
close
Professor
the symposium.
Atkinson.
Thank you everyone for your kind attention. It's
Thank
been
you.
a pleasure.
Bye.
Bye.